Your Six Sigma project is in the Analyze phase. As you work to discover what's wrong with an existing process, you want to prioritize your actions and efforts to maximize improvement. How will you choose what to do first? FMEA, short for Failure Modes and Effects Analysis, is a non-statistical technique used in the Analyze phase for identifying problem areas, potential failure modes, and prioritizing improvements to products, processes, or services. You should already be familiar with the basics of FMEA from your prior Six Sigma experience. You can access the content on FMEA process and benefits after this video to review FMEAs. Of the many types of FMEAs, the two most commonly used by Six Sigma practitioners are the Design FMEA and the Process FMEA. Six Sigma's focus on improvement tends to make these the most useful in accomplishing project goals. A Design FMEA, sometimes called a DFMEA, analyzes the design for potential failures that could arise as a result of weaknesses in the design of the product rather than due to its processes or manufacture. If both FMEAs are used, the Design FMEA is usually done first before production begins. The Process FMEA, sometimes called a PFMEA, is used to identify the failures caused by weaknesses in processes such as transaction, assembly, or production processes. It's typically conducted during production. You can access the content on Design and Process FMEAs after this video to review the two FMEAs. The line between these two types of FMEAs can be blurry, and the potential for overlap, as well as the limits of overlap, should be acknowledged. One distinction between the two types is the presumptions each makes about the other. During a Design FMEA, it's presumed that both process needs and design intents have been implemented. And during a Process FMEA, you presume that the product meets the intent of the design. Another important point to note is that while a Design FMEA considers the technical and physical limits of the production process, it doesn't use process characteristics to overcome design weaknesses. When you perform either type of FMEA, you may choose to include some overlapping elements in the analysis. For instance, a Process FMEA doesn't need to include failure modes, causes, and mechanisms that originate in the design, but the team may choose to include some design issues. And likewise, a Design FMEA doesn't need to include process-related failure modes and causes if their effect and control is covered by a Process FMEA. Yet the team may choose to consider some process issues in the Design FMEA. You should also be aware that a Process FMEA can originate from a process flowchart. As a result, it may include some product effects from the Design FMEA when appropriate. The worksheet used to perform the analysis is similar for both Design FMEAs and Process FMEAs. A FMEA worksheet typically includes 8 columns. An additional column or columns may be used to record revised information. Don't confuse failure modes with causes. Note that separate columns are used to record them. A failure mode is any way in which the design or process being analyzed may fail to meet its intended function or requirements. A cause is a weakness in the design or process that may cause the failure mode. You can access the content on the FMEA worksheet after this video to review the information on FMEA construction and layout. Key to the usefulness of the FMEA method is its ability to help you prioritize improvement efforts. FMEA uses the Risk Priority Number, or RPN, to compare and prioritize potential failure modes. Before you can calculate an RPN value for a failure mode, you need to rate its component values, severity, occurrence, and detection. Each component of the RPN value has a specific purpose. Severity describes the perceived seriousness of the failure mode's effect. Occurrence quantifies the frequency of occurrence of a potential failure mode. Detection describes the assessed ability of current controls to detect failures or causes that could lead to a failure. Each component of the RPN uses a rating scale to aid prioritization of failure modes. Rating scales should contain 3 things: a range of ratings, a description, and criteria for each rating. It's important that you associate each rating value with a clear description and criteria so that all team members have a common understanding of the meaning of the ratings. Descriptive criteria for ratings are crucial to the validity of the risk assessment. Severity ratings do change from industry to industry. For example, the military may choose to base its severity ratings from 1 to 5 on potential hazards to personnel and operations. A bank might use a similar 5-point scale, but criteria would describe the severity of failures in financial terms. Occurrence ratings can also differ from industry to industry. For instance, the Automotive Industry Action Group has a rating scale where a 1 is defined as having a probability of occurrence of less than or equal to 0.01 per 1,000 vehicles or items. Contrast this with the military's 5-point failure probability scale. A rating of 1 represents a probability of occurring less than 1/1,000,000th of the time. Detection ratings are impacted by the realities of your process or design. Returning to the automotive industry example, it employs a 10-point scale, with 10 representing absolute uncertainty, meaning that design control can't or won't detect the failure mode, or that there is no design control for the failure mode. At the other end, a rating of 1 is described as almost certain, meaning that design control will almost certainly detect a potential failure. A 5-point rating scale is sufficient for most purposes, once adapted to your needs. Make sure ratings are clearly defined, are understood, and allow for objective prioritization using numeric rating scales. Generic scales are provided in the job aid. You can access the job aid on RPN rating scales after this video to help you determine the correct ratings for severity, occurrence, and detection. The RPN is generally calculated as the product of the 3 ratings of the failure mode: severity, occurrence, and detection. For example, given a severity rating of 3, an occurrence rating of 2, and a detection rating of 5, the RPN is 30. Suppose you were analyzing failure modes to determine which ones should receive priority. A green belt working on the FMEA tells you that the RPN of a failure mode is 325. What does this tell you about the priority of that failure mode? The answer is nothing. RPN values are relative and gain meaning only when they're compared and weighted against RPN values for other failure modes. RPN values are used to compare the risks of the identified failure modes. A high RPN value indicates one or a combination of 3 things, each related to the 3 individual components of the RPN value. The effects of the failure mode can result in an enormous loss to the quality of the product or service, which maps to severity. The cause of the failure mode may have a high likelihood of occurring, which maps to occurrence. The existing controls are insufficient to catch the causes of failure modes, which maps to detection. Generally, the mode with the highest RPN is established as the highest priority for improvement. However, if the difference in RPN values for 2 or more failure modes is not very significant, then the failure mode with the highest severity rating receives the highest priority. There's no fixed rule governing when a difference is considered significant, and it may vary by organization. A difference of 25% or more of the highest RPN can be safely considered significant. Also, you may want to take other factors into consideration when establishing priority. Other organizational priorities may take precedence over failure modes with the highest RPN or those with the highest severity rating. The scope of the improvement project, available resources, and the relative ease of addressing problems are examples of organizational priorities that may impact which failure modes are addressed first. All modes have very similar RPN values, yet failure mode 3 is priority because it has the highest RPN. Failure mode 2 has the highest severity value and is assigned the highest priority based on its higher severity. As you perform the FMEA, you also need to determine what actions will be taken to reduce risk and who will take responsibility for those actions. After corrective actions are taken, you should recalculate the RPNs to assess how things have changed. As mentioned earlier, process and design FMEAs use a similar worksheet. Actually, the major difference is in the type of information you record for each type of FMEA. A review of the 8 columns will help highlight how the purpose and use of these 2 FMEAs differ. Let's explore how each feature is used for both process and design FMEAs. When conducting a design FMEA, the features or functions of the product or service under given operating conditions are noted under the feature or step column. If you are conducting a process FMEA, the process steps being analyzed are identified here. During a design FMEA, the potential failure modes, how the design might fail to meet design intentions under specified operating conditions, are described under the failure mode column. When you are performing a process FMEA, you are instead focused on how the process may potentially fail to conform with requirements or design intent. The process FMEA considers the failure modes under specific operating conditions and assumes that any parts coming into the process are correct. During both a design and a process FMEA, the effect column is used to identify what the consequence of a potential failure is. The cause column is used to identify the potential cause of the failure. In both types of FMEA, the cause is what the eventual improvement solution will focus on. There is one major difference. In a design FMEA, the improvement focuses on eliminating failures due to design weakness, while in a process FMEA, the improvements focus on controllable or correctable aspects of the process. The controls column identifies existing measures for detecting failure modes. In a design FMEA, these will reflect the design activities and tests that are in place to prevent or detect failure modes. Processes are more likely to use process control methods such as statistical process control to prevent or detect failure modes. The ratings column is used to record the team's scale assessment of the severity, occurrence, and detection of each failure mode. For both design and process FMEAs, the RPN column holds the product of the severity, occurrence, and detection ratings for each failure mode. The responses column is used to record the actions that will be taken to improve the design or process. In a design FMEA, they will be actions to improve design and thereby detect, reduce, or lower severity of the failure mode. In a process FMEA, these actions will focus on preventing the failure mode from occurring. However, reducing the severity of process failure modes may require design improvements, process revision, or both. Suppose a team is performing a design FMEA on a satellite receiver. Space is left to record the date that the worksheet is updated with revised RPNs as a result of actions taken. If you are going to perform a design FMEA, you need to start with the engineer's design intent documents. These documents should clearly outline what is and what isn't expected from the design. Let's consider the first three column headers to learn what the team determines from the design FMEA. The team is analyzing how the receiver functions to identify any design weakness that could be improved. The first potential failure mode identified by the team is a dropped signal. Another is weak signal reception. The effect of a dropped signal is a loss of service, which is added to the effect column. The effect of a weak signal is diminished quality of service. Transmitter failure is identified as the potential cause of a dropped signal. Atmospheric interference is identified as the potential cause for weak signal reception. Because atmospheric interference cannot be controlled, none is entered to reflect this. As for transmitter failure, the team indicates the transmitters are randomly inspected. Now the team is ready to rate the severity, occurrence, and detection of each of the failure modes. With the severity, occurrence, and detection ratings established, the team can calculate the RPN for each failure mode. Because weak signal reception has the highest RPN, it's given top priority. Improve resistance is added to the responses column as the action to take to reduce the RPN value of weak signal reception. The team also notes that to reduce the risk of transmitter failure, it could increase inspection efforts. After the response actions are taken, the team again rates the three failure modes. Right away, the team can identify that implementing the responses has reduced the RPNs. Another team is performing a process FMEA for its travel booking service. The team is presently analyzing Step 3 of the booking process, making a reservation, and has just identified two potential failure modes, and the effect, cause, and control for each. The team assesses and adds ratings to the worksheet for the severity of the effect and for the potential for each cause occurring, if it does occur, how likely it will be detected. Now, the team calculates the RPN values to help it prioritize improvement efforts. Because it's typically the failure mode with the highest RPN value that is given priority, the team first notes which failure mode has the highest RPN. But a team member points out that the difference between the two RPNs is not significantly large, and RPN alone shouldn't be the deciding factor. Because reservation not recorded has a higher severity rating, the team decides to give it priority. Now the priority has been established, the team sets to work on identifying how it can improve the process. To prevent human error when making a reservation, the team decides to change the process to include a verification activity. In response to the potential cause of the wrong type of room selected from the drop-down list, the team decides to make a design change. Instead of a drop-down list, a radio button will be used to make the selection. This will help prevent the accidental selection of the wrong room type as the representative inadvertently moves the mouse while the list is still active. FMEA is a non-statistical tool you can use to identify, analyze, prioritize, and act on potential failure modes that introduce risk. Potential failure modes are usually quantitatively prioritized using RPN values, but they can be prioritized based on severity if the difference in RPN values for two or more failure modes is not significant. Two types of FMEA are the most often used, the design FMEA and the process FMEA. A design FMEA focuses on achieving improvement through changes to design, while a process FMEA focuses on improvement through changes to process. This difference is reflected in the nature of the information recorded on the FMEA. Suppose a colleague calls you to say she's lost and needs directions to the convention center. What's the first thing you're likely to ask her? Where are you? You can't give proper directions without knowing this. Process improvement is the same. You need to know where you are and where you want to be before you can make plans to get there. Gap analysis is a non-statistical analysis method that allows you to identify, in measurable and quantifiable terms, the gap between actual performance and desired performance. Defining the gap shows where improvements must be made. Gap analysis helps target your process improvement efforts and provide just cause for your actions. Developing effective strategies and assigning the resources needed to reach organizational goals is easier when you know what you have to do. Gap analysis is applicable to a variety of actual versus desired performance scenarios, and it's one of several analysis approaches you can use to identify key variables, their interrelationships, and their impact on the issues at hand. Gap analysis can have the added benefit of increasing motivation and morale. In Six Sigma, you use gap analysis to identify the gap between the actual and desired performance of an existing process, product, or service. Based on the findings of your gap analysis, you can develop strategies to close the performance gap and achieve the desired performance objectives. While performing other analyses in the analyze phase, you've used certain key metrics to establish a baseline for the process being improved. You use this baseline data during gap analysis to set process improvement goals and develop strategies for improvement. A gap analysis is typically used in Six Sigma to identify requirements for reaching future targets or critical to quality requirements. Examples of requirements that may be used include cycle time targets, benchmarking targets, compliance objectives, market share, and customer satisfaction. An automobile component manufacturer has initiated a Six Sigma DMAIC project to improve one of its part manufacturing processes. The project is now in the analyze phase. The company has performance data for its competitors' critical to quality requirements for car bumpers. The Six Sigma team performs a gap analysis using this data to benchmark the company's performance against that of the market leader. The results will help the team to develop strategies to change the process, close the gap, and meet or exceed the performance of competitors. You can use a gap analysis to compare qualitative or quantitative data. This makes it equally applicable to the analysis of processes where success is measured in terms of things like skills or training requirements, and to manufacturing processes, where requirements are based on precise numerical targets. Whether the data is qualitative or quantitative, a gap analysis has 5 basic steps. First, determine the function or area to analyze and prepare a worksheet. Then, identify the desired performance in the future state column. Next, record actual performance in the present state column. Then, list the requirements for moving from actual to desired performance. And finally, assign responsibility for implementing remedial actions. In Step 1, you determine which function or area to analyze. For instance, the gap analysis may focus on functions like processing time, account reconciliation, or manufacturing a part, or areas like product management, design and development, or quality management. Next, you need to prepare a worksheet to record the information for your gap analysis. A 4-column worksheet is all that's needed. In the worksheet, you can use the present state column to record the process's actual present state performance. Then you can use the requirements column to record the actions or changes required to move the process from its actual to the desired future performance. Next, use the future state column to record desired process performance. And finally, you can use the responsibility column to record who'll be responsible for implementing the remedial actions. These are actions that must be taken to achieve the performance improvement as described in the requirements column. A Six Sigma team at an insurance company is working on a project to improve the company's processes. The team has decided to perform a gap analysis on the annuity creation process. The first thing team members do is prepare a worksheet to record the findings. In Step 2, you identify the desired performance. You may choose to define desired performance using benchmarking data, compliance or regulatory guidelines, or quality standards such as ISO standards. Whatever data you use to define desired performance, make sure the targets are stated as a particular level of performance on a well-defined metric. Certain questions can help you describe desired performance. For example, what are measures of success? Which aspects of performance are already achieving desired performance? And what will business look like when the desired performance is achieved? In Step 3, you record actual performance in the present state column. For your gap analysis to return accurate and useful information, you must compare similar metrics. For instance, if desired employee performance is defined in terms of completing a process in 3 steps, you need to compare that to how many steps it currently takes. Or perhaps desired operational outputs are defined in terms of volume per production run, then you would also need to define the current state as volume per production run. You may not know offhand what data will help establish current performance. The first thing you can do is ask, what activities are we engaged in that led to current business results? From here, you can determine what performance metrics are tracked for these activities. The 4th step, lists the requirements for moving from actual to desired performance, is where you define the gap and identify how improvement will be achieved. Requirements represent the changes necessary to close the performance gap. You should accompany each requirement with a list of the resources needed to accomplish the change. Following a few tips will help you state the gap. When you state the gap, use statements that clearly define the performance gap and only the performance gap. Looking for solutions while defining the gap can introduce bias and undermine improvement. You can use the formula desired performance minus current performance equals performance gap to help you articulate the gap. Employee performance is often the cornerstone of operational results. If requirements impact how employees do their jobs, be sure to detail this when identifying and defining requirements. This will help address gaps in employee performance. There are various questions you can ask to determine how the current operational performance will have to change to meet the desired operational performance. For example, how would operational performance be different than it is presently if desired performance outcomes were achieved? And what activities would your employees need to be engaged in to achieve ideal business results? Backward chaining is another method you can use to identify requirements. Moving backward from the desired state to the present state can help you discover a logical sequence of actions that, if implemented, will bring actual performance in line with desired performance and close the gap. Step 5, assign responsibility for implementing remedial actions, is the final step of the gap analysis. In the last column of the gap analysis worksheet, you can record who's responsible for implementing remedial actions. Recall the example of the Six Sigma team at the insurance company. Because the team is concerned with regulatory compliance, it decides to use the regulatory requirements pertaining to annuities as the targets for desired performance. Let's consider the following example for an explanation of how the gap analysis process was completed, in order, starting with Step 2. Here, the team begins by adding the desired performance targets, aligned with the regulatory requirements, to the future state column. Then, in Step 3, the team reviews the insurance company's current process and records actual performance in the present state column. In Step 4, the performance gap for one aspect of the process, attain customer authorization 100% of the time, is given the highest priority. The team decides that the best way to close the gap is to add a secure authorization step to the process, where the customer is actively involved in the process. This requirement and the resources necessary to implement it are added to the requirements column. Finally, in Step 5, to complete the gap analysis, the insurance company's Six Sigma team has to assign responsibility for the remedial actions. Andy, a team member, is assigned responsibility for modifying the software to enable secure authorization. All the other identified requirements for closing this and the other gaps are assigned to team members as appropriate. Recall the example of the auto component manufacturer that wants to improve the critical to quality requirements of its car bumpers. The Six Sigma team wants to use benchmark data to compare its company's performance to that of the market leader. Consider an additional example, part of Step 1, which is to determine the function or area to analyze and prepare a worksheet, has already been done. The team chose bumper production to be subjected to a gap analysis. So, the team begins by preparing a worksheet to record the gap analysis information. Because the team is benchmarking bumper production against that of the leading competitors, the competitors' performance results are entered in the future state column to identify desired performance targets. The company has been tracking the same performance metrics as identified by the competition. The team enters the current metrics in the present state column of the gap analysis worksheet. The fourth step lists the requirements for moving from actual to desired performance, is where you define the gap and identify how improvement will be achieved. Requirements represent the changes necessary to close the performance gap. You should accompany each requirement with a list of the resources needed to accomplish the change. The team determines the difference between actual and desired performance and begins defining requirements necessary to reach desired organizational performance. For the hole diameter, the team determines the requirement to increase hole diameter by 0.05 inches and enters it into the requirements column. This will require reprogramming of the machining specifications to match the new diameter. This is also added to the requirements column. The team continues in this fashion until all requirements are identified. In the last step, the team assigns responsibility for each requirement and its remedial actions. The hole diameter requirement is assigned to Julie, the machinist responsible for the piece of machinery that cuts the holes. The team continues until all tasks are assigned. Gap analysis does have a few limitations you should be aware of. First, gap analysis isn't a good fit for all problems. Because goals may emerge and evolve during the course of problem solving, what ought to be can be a highly variable target. Also, some problems have many alternative solutions, in which case backward chaining strategies will have little practical use. The usefulness of gap analysis is limited in both these types of situations. Gap analysis is a non-statistical method of analyzing processes. The 5 steps of a gap analysis are to determine the function or area to analyze and prepare a worksheet, identify the desired performance, record actual performance, list the requirements for moving from actual to desired performance, and assign responsibility for implementing remedial actions. A gap analysis helps you to define the problem in a measurable and definable fashion. Then you can develop strategies to eliminate performance. Six Sigma teams often must make decisions about improvement strategies based on future outcomes they can't predict. How can they prepare for an uncertain future? Many organizations use traditional forecasting, incorporating quantitative and often historical data and experience as part of their strategic planning efforts to prepare for the future. But traditional forecasting has a weakness. It often fails to predict significant changes to an organization's external environment, especially if changes happen quickly or unexpectedly. So what if what normally happens doesn't actually happen? Being unprepared for changes, even improbable ones, exposes your organization to risk. Scenario planning is one of several non-statistical analysis approaches that can help you and your Six Sigma team make informed decisions. Specifically, scenario planning can help you cope with the problems of risk, uncertainty, and lack of knowledge about aspects of the future. As such, scenario planning addresses future variables that are difficult or impossible to forecast, such as raw material prices, economic growth, advancements in technology, and regime changes. Scenario planning is a strategic planning process where scenarios or stories are developed to explore how changes in an organization's environment may impact it in the future. You can use scenario planning to discuss possibilities and develop potential responses to the future described in each scenario. Scenario planning is not about predicting the future. It's about making a conscious effort to identify what's possible. The emphasis is on considering possible scenarios other than those being predicted by the widely accepted forecasts. Scenario planning is often used to identify possible future outcomes and trends in markets, suppliers, technology, demographics, and economic variables. Using scenario planning, you generate distinct and plausible futures. The plausible futures that will have the most impact on the organization's business are selected for further analysis. Scenarios are developed to describe what might happen and how the organization's business will be impacted should they occur. Based on these scenarios, you can prepare, plan, and take actions in the present for facing these potential scenarios in the future. The chief goal is to develop a number of potential responses to the perceived risks. Much of the early work in developing scenario planning is attributed to Herman Kahn for use in military planning. By the early 1970s, scenario planning was being adapted for business use by companies such as Royal Dutch Shell. Oil executive Pierre Wack created a scenario planning method to help Shell prepare for the unexpected. And when the oil crisis of 1973 occurred, Shell was able to deal with the challenges the crisis presented and actually improved its competitive position. Being prepared allowed the company to turn the threat into an opportunity. Scenario planning has practical value, even if it isn't intellectually rigorous. This is because scenario planning offers a way to manage what can't be forecasted. It also forces managers to think outside the box and address what might otherwise be blind spots. You may find resistance among die-hard traditional forecasters. To help overcome this, you might use scenario planning to help find a future outcome that forecasting would have missed. Scenario planning has several other benefits. For example, it facilitates early recognition of scenarios should they occur, increases knowledge of the business environment and broader perception of future events, encourages open communication about issues important to the organization, and provides a better understanding of disagreements that occur if managers envision different scenarios. Although scenario planning should be a formal activity, there is no prescribed method for performing scenario planning. Organizations tend to develop a scenario planning method that works best for them. If you decide to use scenario planning, you can get the most out of it by following recommended activities or best practices. Before you can create plausible scenarios, you have to gather the information that will provide the basis for them. Typically, this includes 5 basic activities. The first activity is to assemble a group of people who will contribute a wide range of diverse perspectives. Next, one has to define the present situation that your organization faces, followed by identifying events that are likely to occur, as well as uncertain environmental variables. Then, group related factors, events, and variables. And finally, identify a few of the most critical factors, events, or environmental variables. The first thing you should do is assemble a group of people who will contribute a wide range of perspectives. Diverse perspectives will bring about a more balanced outlook and will encourage the creation of scenarios that consider possibilities outside of the types of futures predicted by traditional forecasting. Managers and executives often have a broader perspective and better understanding of the organization and its external environment. Having them actively participate in the scenario planning process helps ensure that important details aren't overlooked. It also helps with senior management buy-in and ownership. Before you begin developing scenarios, you also need to define the present situation faced by your organization. This is factual information about the organization's external environment, including political, economic, social, and technological realities, and is used as a starting point for scenario development. This is where the story begins for each scenario. With a starting point defined, you can begin to consider what might happen. To do this, you identify events that are likely to occur as well as uncertain environmental variables. Ask participants to share what they believe will happen based on known variables and expected events. Then, ask them to explore what might happen with uncertain but critical environmental variables. It's important to define these because they are driving forces and will act as future indicators that the scenario is unfolding. Next, you organize the information generated by grouping related factors, events, and variables. This will help you understand how these various factors may jointly contribute to possibilities for your organization. After organizing the information, the group can identify a few of the most critical factors, events, or variables. These should be the things that will have the greatest impact on your organization's business if they happen. Fewer is better because these possibilities will be analyzed in detail and scenarios will be developed for them. Now you are ready to analyze the interaction between variables using a matrix. A 2x2 matrix is recommended. Any bigger and the results become hard to interpret. In a two-dimensional matrix, you explore the interaction between the two most important variables. Each cell represents a scenario. Naming the scenarios makes referring to them in subsequent discussions much easier. If you identify more than two critical variables or more than two outcomes for each variable, you can build a larger matrix, but doing so can make the analysis more difficult. The final activities focus on developing the scenarios. Develop detailed stories that begin at present and describe how the organization will be impacted if the future described by the scenario happens. These should be as realistic as possible and may involve the use of computer modeling or game theory. With the stories developed, it's time to design and implement strategies for dealing with the scenarios. Now, if the future unfolds as described by one of the stories, your organization will be prepared to handle it, possibly turning a threat into an opportunity, or at least minimizing the negative effects of risk. Once the strategies are designed, you also need to identify early warning signs for each scenario. Early warning signs are used to signal that a scenario is unfolding. Consider how a leading manufacturer of desktops, notebooks, and server processors uses scenario planning during one of its Six Sigma projects. The project involves developing cost reduction strategies that consider the future outcomes of the cost structures of its Gen 3 processors in the next financial year. The Six Sigma team is reviewing the current structure of fixed and variable costs. This primarily includes the material costs, which account for 40% of the total unit cost, as well as technology costs, including research and development, patenting, and software purchase, which account for 25% of the total unit cost. Material and technology costs in the high-tech products markets are very unpredictable and could increase or decrease depending on larger global factors. These factors include the general economic situation, demand patterns, introduction of disruptive technologies, and prices of some key input materials. The team is conducting scenario planning for the next year and comes up with 4 possible scenarios based on the 2 variables of material and technology costs. The scenarios, which are added to a matrix, are based on what might happen in the next financial year. Stories are developed to describe how these variables could impact business in the future. When scenario planning involves just 2 variables and 2 possible outcomes, some assumptions have been made. One is that in real business situations, organizations would be able to guesstimate with a certain degree of precision the relative increase and decrease of the variables. Of course, determining these levels is specific to the organization's strategic direction and industry. In the previous example, it's assumed for the sake of comparison that the variables increase and decrease in the same proportion. Let's consider the following example. Material costs increase while technology costs decrease. Given the current cost structures, this will result in a moderate increase in the unit cost. Both material and technology costs increase. This would result in a sharp increase in the unit cost. This scenario is the most critical and needs special measures to reduce, absorb, or be ready for a potential price increase. Both material and technology costs decrease, resulting in a substantial decrease in the unit cost. This scenario is most favorable, though less likely than the others. Material costs decrease while technology costs increase. Given the current cost structure, this will result in a moderate decrease in the unit cost. Now that the matrix is complete, the team can move on to further develop each scenario. The team uses computer modeling to help detail how the future will look if each scenario unfolds and how this will impact key business areas. To make sure the organization is prepared to act should these scenarios become reality, the team develops strategies and identifies early warning signs that material or technology costs are changing in the global market. You can use scenario planning, a non-statistical analysis tool, to explore and prepare for an uncertain future. By identifying variables of these possible futures that will have the biggest impact on your organization, you can then prepare ways to deal with these possibilities if they occur. Scenario planning involves possible futures, not predictable futures. By developing scenarios about how changes in your company's external environment could impact it, you can prepare ways to handle the risk change brings, should that change happen. You can access the job aid about scenario planning after this video to help you perform scenario planning. You've undoubtedly heard the term Band-Aid solution. When a problem is resolved, but the underlying system breakdown that caused the problem still remains, that's a Band-Aid solution. You expend time and effort, but don't solve the real problem. In fact, you might even create more problems. During the Six Sigma Analyze phase, you can use a problem-solving approach called root cause analysis to identify the root causes of problems instead of just applying a quick fix to the surface. So what's the best way to solve a problem? Well, you should eliminate its source instead of trying to minimize its effects or symptoms. This principle is the basis of root cause analysis. When you use this approach, your goal is to reduce the chance that a similar problem will occur in the future. Consider this scenario. Imagine that you're the Six Sigma Black Belt at an automotive parts manufacturer and you're trying to solve 2 recurring problems. First, you find that fluid hoses routinely have leaks. The second problem you notice is that several parts are oversized when they come off the production line. You could take the following actions to find out the difference between a symptom fix and a root cause fix. Whenever you encounter a leaky hose, the immediate symptom fix would be to simply plug the hole. You'd still have a hole, but it would be fixed for the time being. An intermediate action you could take for a leaky hose is to patch the hole. This might be a more long-term solution than simply plugging the hole, but it's still not eliminating the cause of the leak. The root cause action you could take for leaking fluid hoses is figuring out what's actually causing the leaks to form. Then you could fix the problem so that it doesn't happen again. In the case of oversized parts, the immediate action would be to implement 100% inspection. In other words, you'd inspect every part that comes off the production line. Can you imagine how time-consuming this would be? An intermediate action for oversized parts might involve installing an oversized kick-out device on the production machine that removes any part that's over the specified size limit. This would ensure oversized parts are removed from the batch, but you'd still be wasting time and resources producing these parts. The root cause action you could take for oversized parts is analyzing the process and taking the steps needed to remove the cause. Maybe the machine that molds the parts has to be realigned, or maybe the problem is the result of user error. Either way, you'd be able to address the root cause. When you're working with your Six Sigma team during the analyze phase, you'll frequently have to determine the root causes of problems. This will enable you to take the appropriate measures to remove the causes during the next phase of DMAIC, improve. Depending on the problem, you might find that this task can range from being relatively quick and simple to time-consuming and complex. It's important to understand that there isn't one fixed method for analyzing root causes. Instead, you should think of it as a tool set that can guide your analysis. However, a general framework for root cause analysis should involve 3 steps. Step 1 is to generate a list of possible causes. Step 2 is to organize and group possible causes. Step 3 is to prioritize the list of vital few root causes. When you're beginning a root cause analysis, the first thing you need to do is gather information relative to the problem. This is the basis of the first step, generating a list of possible causes. You'll probably find that this is one of the most time-consuming steps of the entire process since it involves collecting data. It also includes idea generation activities and tools such as FMEA, cause and effect diagrams, Pareto charts, the 5 Whys analysis tool, and fault tree analysis. These will be covered in other topics. Turn your attention to one of these tools, the cause and effect diagram, also known as a fishbone or Ishikawa diagram. You'll recall from your experience with Six Sigma tools that the cause and effect diagram is used to analyze problems in order to identify and group their causes. It helps you generate ideas and sort them into useful categories. And because the process for creating the diagram is highly interactive, it's especially useful for structuring brainstorming sessions. You can access the content on cause and effect diagrams after this video to review this tool. Now, imagine that you're the black belt at a financial institution. You're working on a project to improve the company's loan processing time, and you're conducting your own root cause analysis. You and your team determine that your problem statement is consumer loan processing delays. Next, you and your team begin brainstorming as many causes as you can come up with. Your session is a success, and you identify several main factors. The first is the loan processing staff's capability. You also note that customers use paper instead of electronic applications. Other main factors include the poor quality of the infrastructure at processing centers and the existence of seasonal trends in loan applications. The final main factor you identify is the amount of the loan customers apply for. You only identify causal factors for one main factor, the capability of the loan processing staff, and you add the following items to the diagram: lack of experience, inadequate education, inadequate training, and lack of motivation and reward. Once you've generated a list of possible causes, you have to organize and group them, the second step in a root cause analysis. Many of the tools you use to generate your list of potential causes, including FMEA, cause and effect diagrams, and fault tree analysis, will also help you organize them. So what's involved with organizing causes? Well, you might determine which causes are related and group them. Or you might determine which causes influence each other, then nest or stratify them. To demonstrate this step, return to the loan processing example. You'll recall that you've already generated a list of causes. Now you have to organize and group them. The cause and effect diagram naturally sorts causes into categories, and you take these groups into the next step. The categories include people, procedures, environment, and application details. You organize the main and causal factors into these groups. Once you've identified and categorized potential causes, you have to prioritize the list of the vital few root causes. You can use several tools to numerically prioritize root causes. For instance, a Pareto chart, a fault tree analysis, or risk priority numbers in a FMEA. While many of the other root cause generating tools, such as FMEA and cause and effect diagrams, can be considered subjective tools, The Pareto chart provides the built-in numerical data to back up your priorities. Another subjective tool is known as the 5 Whys analysis tool. Its purpose is to drill down into causes to find the true root cause that can be acted upon. You'll learn more about this tool in a later topic. Now, return to the earlier example. You're the black belt at a financial institution. As part of the third step, you and your team use a Pareto chart to prioritize your list of the vital few causes. You determine that the 2 most costly causes are the loan processing staff's capability and the fact that customers use paper applications instead of electronic ones. The Pareto chart worked well for you because you had numerical data, but if you hadn't, you might have opted for a more exploratory and subjective method, like the 5 Whys analysis tool. As you're performing your root cause analysis, it's crucial that you back up your conclusions about root causes with data. It's fundamental to Six Sigma analysis and the analyze phase of the DMAIC process that data be solidly grounded. What do you do with the causes you've just identified? The next step is to validate causes by subjecting them to statistical analysis, such as regression and hypothesis testing. Once they're verified, you and your team will work through subsequent DMAIC phases to develop and implement solutions to eliminate or prevent these causes. Root cause analysis is a problem-solving approach used to identify the root causes of problems. It focuses on eliminating a problem's source instead of trying to minimize the problem's effects or symptoms. A general framework for root cause analysis involves performing 3 steps. First, you generate a list of possible causes. Then, you organize and group those causes. Finally, you prioritize the list of vital few root causes. During these steps, you'll use several idea generation activities and tools, including FMEA, cause and effect diagrams, Pareto charts, the 5 Whys technique, and fault tree analysis. Have you been on the receiving end of a child's incessant asking of the question, why? Children often continue asking this question until they reach an acceptable answer. At some point, there is no other why. In Six Sigma analysis, asking why can be a good way to find the root cause of a problem. The 5 Whys analysis tool is one of several available for use during root cause analysis to generate and organize ideas. It can help you resolve problems relating to processes, products, services, or quality. As you might guess from the name, 5 Whys analysis involves asking why up to 5 times. This technique lets you drill down into causes to find the true root cause of a problem. And what's the goal? To eventually reach a cause that's actionable. In other words, a cause you can do something about. The 5 Whys analysis tool is often used in conjunction with a cause and effect diagram during the 3 steps of root cause analysis. It can also be used with a Pareto diagram. You can use 5 Whys analysis to investigate the broad causes that were identified using a Pareto diagram. In fact, 5 Whys analysis can be useful with any of the tools in the root cause analysis toolkit. Your Six Sigma team members must ensure that they reach the goal of the 5 Whys exercise, to drill down to 1 or 2 actionable main causes. Only then can you solve the problem or reduce variation. The 5 Whys analysis tool is an effective method that prompts you to go beyond superficial solutions. You can avoid wasting time and resources on addressing the symptoms and, instead, focus on the true causes of a problem. The first step in 5 Whys analysis is to select a cause. You can identify the cause from a cause and effect diagram or the tall bar on a Pareto chart. This is the first of the 5 Whys because it asks the initial question, why does the problem exist? Ensuring that everyone on the team has a common understanding of the selected cause is vital. What would happen if team members had a different understanding of the first why? This would have obvious implications for the rest of the process. Think about it. If each team member answered the next why in a different way, you'd get further and further away from a common understanding of the root cause. Suppose you're the Six Sigma black belt at a pharmaceutical supply wholesaler. You're leading a Six Sigma project aimed at addressing delays in the receivables cycle in the institutional customers segment. The goal is to reduce the receivable cycle time from the current 6 weeks to 3 weeks by the end of the project. You and your team brainstorm causes for this problem, and select one for 5 whys analysis. In this case, a Pareto chart provides evidence that a key reason for delays is that customers aren't paying their invoices by the due date. The second step in 5 whys analysis is to take the cause you just identified and ask, why does this occur? This is the second why. You and your team identify 3 possible causes for the delays in payment. First, that some customers are losing their invoices. Second, that your company is late in sending out invoices. And third, that customers are paying late. To come up with a cause for the first why, you used a Pareto chart to identify the most influential cause from among several possibilities. As you're brainstorming for this second round of why, you should again brainstorm several possible causes. You'll narrow these down before asking why again in the third step. To narrow down the possibilities, you need to investigate each of the potential causes you just identified to determine if there's data to support eliminating any of them. When you have only a few remaining causes, the team should vote to select one as the key cause that addresses the second why. Then you again ask, why does this occur, which becomes the third why in the process. Consider the following example. The first possible cause you identified is that some customers are losing their invoices. You eliminate this cause, however, because the number of late payments is too large to account for the problem. Could all of those customers really have lost their invoices? The second possible cause you identified is that your company is late in sending out invoices. This cause is retained as a possibility because a new accounts payable clerk has recently been hired. The third possible cause you identified is that some customers are not paying on time. This cause is also eliminated because some of the late payments are coming from customers who have always paid on time in the past. Why should you narrow down the remaining whys to 1 or 2 possible causes? Think about what could happen if you didn't. You'd probably be left with causes that are too far-fetched, are unsupported by data, or are too many in number to investigate further with a fourth why. The 5 whys analysis process would become unnecessarily time-consuming, and further investigating tenuous or unsupported causes wouldn't be effective in helping you to find the root cause of the problem. You discover that invoices aren't being sent out by the automated billing system for a month after the product has been shipped. This is evidence that the late invoices cause is the most likely reason that customers aren't paying their invoices in a timely manner. Now that you've narrowed down the causes to 1, late invoices, you should ask why again. This is the fourth step in the process. What's causing invoices to be late? You determine that there are 3 possible reasons: a problem with the billing system, user error, and issues with your customer database. So what is the most likely reason for the delay in sending invoices? It turns out that the automated billing system wasn't reset properly and is batching invoices to send once a month, rather than immediately upon shipping products, which has always been the procedure. To solve the problem, you have the billing system reset and invoices resume normal batching. At this point, you've reached the final why. At last, you've identified a cause that's actionable. Although the process is called 5 whys analysis, you don't necessarily have to ask why 5 times. In the preceding example, the team reached an actionable cause after only 4 rounds of why. Conversely, you may find it necessary to continue the iterative process of drilling down through additional whys before you reach a root cause you can act upon. The rule of thumb is to stop when you start repeating reasons or causes. Now, imagine that your team had stopped short of the goal. In other words, you didn't ask why enough times to reach an actionable cause. If this had happened, you'd be left with a high-level cause that isn't something you can act upon, and therefore has limited use. It would be difficult, if not impossible, to take a non-actionable cause into the improve stage. For instance, what if you'd stopped at the third why, that customers aren't receiving their invoices in a timely manner? Is this an actionable cause? No, it's not. Without knowing why, you'd have a hard time figuring out what to do about this problem. 5 whys analysis is one of several tools available during root cause analysis for generating and organizing improvement ideas. It involves asking why up to 5 times to drill down into causes to find the true root cause. The goal is to eventually reach a cause that's actionable. The process has 4 steps. Select a cause, ask why does this occur, Select the key reason for the second why and ask, why does that occur? And finally, continue selecting key reasons and asking why iteratively until you find an actionable cause. Imagine that you work at a company that manufactures computer hardware and you're trying to figure out why a particular component isn't working. You want to identify not only the major faults or critical failures associated with the product, but also the causes and potential countermeasures. You'd probably have to use a separate tool for each of these areas, wouldn't you? Actually, you wouldn't. You could use fault tree analysis, or FTA. Fault tree analysis is a tool that helps you consider underlying reasons for a specific failure mode or event. This also helps understand the relationships between them. FTA is commonly used to search for the causes of an observed or potential failure so that problems relating to processes, products, service, or quality can be addressed and eliminated. Although fault tree analysis is very useful in manufacturing, that's not its only application. You can also use this tool in administrative, service, and many other contexts. So what exactly can you do with this tool? For one thing, fault tree analysis allows you to use a backward, systematic approach to identify potential causes or failures. You can also gain an understanding of the relationships between causes and failures, as well as break down the failures into more detailed inputs. When you use FTA in your project, your aim should be to analyze the probability of an event occurring. The tool uses a hierarchical approach and failure logic. This means you can take a complex system and assess the paths and probabilities that contribute to a specific system failure. This analysis can become very complicated, but in real-life situations, you'd most likely use a software package to do this analysis for you. This is especially true when you have a complex system, such as in healthcare or software development. Fault tree analysis is part of the root cause analysis toolkit used during the Six Sigma Analyze phase. The activities involved in FTA span the entire root cause analysis process and help to generate, organize, narrow, prioritize, verify, and quantify, as well as develop solutions for root causes. How do you actually use this tool? Fault tree analysis uses logic gates, which are represented by different symbols, to help determine the overall reliability of a system. There are 5 key steps. Step 1 is to select component for analysis and identify top event, a critical failure or fault related to it. Next, in Step 2, you identify causes for the fault. To represent the relationship between causes and the fault above them, you can use AND gates, which require all the causes to be present for a fault or failure to occur. Or you can use OR gates, which require at least one cause to be present for the fault or failure to occur. In Step 3, the goal is to work toward actionable root causes by creating a tree of contributing causes. If it's possible, in Step 4, you should assign probabilities to each cause and prioritize the causes. Note that the probabilities at AND gates are multiplied, whereas the probabilities at OR gates are added. Finally, in Step 5, you identify countermeasures for each root cause. The first step in the process is to identify a failure and write it down as the top event. For instance, suppose you're the Six Sigma Black Belt at a computer manufacturer and you're trying to figure out why a new model isn't working properly. To start your tree, you draw a box at the top and write down "Computer fails to work." This is your top event. Next, you identify the critical failures, the faults related to the first component. This is where you determine the inputs or causes that contribute to the failure. Remember, the causes can be AND or OR causes. OR causes are independent from each other. AND causes are dependent upon each other. In other words, you must have both to cause the fault or failure. So, to continue creating your tree, you start listing the potential causes for "computer fails to work." Consider the example. With OR causes, you determine that the computer will fail to work properly if the hard drive fails, or the CPU fails, or the keyboard fails, or the monitor fails. Then, with AND causes, the computer will fail to work if the CD-ROM drive D fails and the CD-ROM drive E fails. You continue identifying contributing causes in this manner until you eventually reach a root cause for each critical failure. This is the third step in the process. For example, you determine that the hard drive stops working due to circuit failure. The CPU failure has two causes: incorrect wiring and not being connected to the motherboard. And the monitor fails because the circuit burns out. You should keep in mind that because the goals of a specific FTA will depend on the organization, the prioritization process will differ for each analysis. However, there is one basic way to pinpoint the highest priority root cause. Base it purely on numerical probability and trace it through the FTA this way. To find the probability of a given cause, multiply all causes below it if an AND gate connects them, or add all probabilities below it if an OR gate connects them. So how do you know which cause has the greatest impact on the top event? If you reduce the probabilities of certain causes, you can determine which change has the greatest impact on the top event. Consider the following example. Reducing the probability of CD-ROM drive D to 0.001 reduces the probability of the top event, computer fails to work, to 0.036101. Reducing the probability of keyboard to 0.010 reduces the probability of the top event, which is computer fails to work, to 0.024101. This is the greatest reduction, so you can conclude that this cause has the greater impact. So you've specified a problem and carefully prioritized the causes. What do you do with this information? At this point, you need to identify countermeasures for all the causes. This is the final step in the process. You and your team should brainstorm actions you can take that will counteract the top priority root cause or causes and thus prevent critical failures. Now, return to the scenario involving the computer manufacturer. For the causes incorrect panel wiring and not connected to the motherboard, you determined that the countermeasure should be to routinely test the connections. And for the cause CRT burned out, a countermeasure could be to develop a replacement schedule to avoid this problem. It's important to know how to create a fault tree analysis. But in real life, you'll typically perform your analysis with software because there are often many failure paths to analyze. The tree must be carefully checked for several reasons. For example, to validate the logic of the tree hierarchy, to compare all the possible paths that can lead to the top failure, and to quantitatively rank order the paths for system improvement, and to determine total probability of system failure. Fault tree analysis isn't the only tool you can use to identify and prioritize failures. Failure modes and effects analysis, or FMEA, is also useful for identifying, tracking, and prioritizing failures and risks. You can use a FMEA for many different products and processes, making it a versatile tool. FTA and FMEA have a few key differences. Compared to FTA, a FMEA can lack precision and be tedious to perform. The level of detail is not the same between the two. This is because sometimes a key failure mode requires further investigation, and the Six Sigma team begins a separate FMEA to eliminate this failure mode. Each mode requires that the team determine causes, assign risk priority numbers, and formulate responses. As you can imagine, this can become overwhelming when you have a complex product or service. While a FMEA's treatment of causes is separate, FTA shows you all the interrelations among failures using a hierarchy. This can help you better determine priorities. If you used a FMEA, you wouldn't benefit from the logic included in an FTA, and your team's priorities would be focused by the risk priority number, or RPN, of individual causes in comparison to the top system failure mode. Not only can this approach be expensive, but you might also miss the most important paths to failure. There will be situations where you'll choose one tool over the other. When is FTA the preferred method? When health and safety are involved, you should use FTA because it focuses on the whole picture rather than just a piece, so it's not just about the product but the environment that product will be used in. FTA is also the preferred method when you can identify a few well-differentiated top events, since a top event is the starting point of an FTA. And when there's a high risk of failure due to human or software errors, FTA is the best method. Why? For one thing, the precision and accuracy of the FTA makes it ideal for analysis where high risks are involved. It also enables teams to quantify the probabilities of errors or faults more closely. There are a few more situations where you'd use FTA over FMEA. For instance, when risk evaluation must be quantified. Probabilities give you the numerical data you need in this scenario. Another situation where FTA is best is when the team needs a complete functional profile. FTA focuses on the total system or environment, so it gives you a complete picture. Finally, if a product's functionality is very complex or interdependent, FTA is the best tool. That's because its structure is well suited for analyzing complex systems. Now, what about using FMEA over FTA? Well, for one thing, FMEA is preferred when failure doesn't have significant health or safety consequences. This is because the environment or system on the whole doesn't have an impact. Another use is when top events can't be clearly defined. If they can, you should use FTA. FMEA is the best method to use when there's little human or software intervention in the functionality because the risks involved aren't as high. Here are a few more situations when you'd use FMEA over FTA. When risk evaluation doesn't have to be precisely quantified, you'd use FMEA because it's less precise than FTA. When several successful functional profiles are possible, FMEA is the preferred method because it focuses more flexibly on parts of the system rather than on the whole system functioning in a particular way. Finally, when the process or product functionality is relatively simple, FMEA is the better choice because FTA is more suited to analyzing complex systems. Fault tree analysis and failure modes and effects analysis can both be useful tools to help you find root causes. You just need to be aware of their strengths and use them accordingly. You can access the job aid about the fault tree analysis, FTA, after this video to review these tools. Fault tree analysis, or FTA, is a tool that's used to define a specific unwanted event and determine all the possible reasons it could occur. FTA uses a hierarchical approach and failure logic to take a complex system and assess the paths and probabilities that contribute to a specific system failure. The FTA process has 5 steps. First, you select a component for analysis and identify the top event. Next, you identify causes for the fault using AND or gates. The third step involves working toward root causes by creating a tree of contributing causes. You then assign probabilities to each cause and prioritize the causes. Finally, you identify countermeasures for each root cause. Failure modes and effects analysis, or FMEA, is another tool you can use for identifying, tracking, and prioritizing failures. The concept of the value stream should be very familiar to you. It's the sequence of activities required to design, produce, and provide goods or services. Information, materials, and the product or service's worth all flow along the value stream. The different activities performed during a process either create value in the end product or they don't. Value is a rating of how well a product or service meets customer requirements. It's defined by the customer. So activities can either be value-add or non-value-add. Value-add activities are the actions and tasks that make a product more complete. These activities increase the value of the product in the customer's eyes. The end result of value-add activities? Receipt of payment from the customer. Non-value-add activities don't add any extra value to the end product or service. These activities include any non-essential actions the customer doesn't want or isn't willing to pay for. As you know, the value stream is an important concept in Six Sigma. Non-value-add activities are classified as muda, or the waste that exists in a process. Waste analysis is a non-statistical analysis method used in Six Sigma. Its goal? To reduce the number of non-value-add activities at each step in the process. Typically, in Six Sigma, 7 categories are used to classify non-value-add activities. These are known as the 7 wastes, and you should already be familiar with the nature of these categories. They include overproduction, inventory, rejects or defect correction, processing or overprocessing, waiting, unnecessary motion, and transport. You can access the content on 7 categories of waste after this video to review the 7 wastes. If you follow the traditional way of thinking, some of these categories aren't considered waste at all. But the Lean Six Sigma thought process asks very different questions. The goal is always to improve the system instead of maintain the status quo. Traditional thinking often involves addressing the symptoms or consequences of a problem, as if assuming these are always present, instead of trying to eliminate the root causes of the problem. You can access the job aid about the 7 wastes after this video to follow along with the upcoming instruction and as a reference to the causes, consequences, and ways of eliminating the 7 wastes. Now, turn your attention to the first category, overproduction. It typically occurs when you produce more than is needed, earlier than is needed, or faster than is needed. Long setup times, unbalanced processes, and adopting a just-in-case philosophy, keeping extra parts on hand for an unreliable machine, for instance, can also cause overproduction. What are the consequences of overproduction? For one thing, your inventory and storage costs increase, and you run the risk of increased damage. You may also have to deal with extra queues and lead times. The traditional way of thinking about overproduction differs from the Lean Six Sigma way. The traditional thought process doesn't perceive batches of extra material as waste. In fact, they're thought to be necessary, so employees always have something to work on. A supervisor might ask, how can I get employees to put in extra hours this weekend to work through all this material that's built up? The Lean Six Sigma way of thinking is very different. It seeks to reduce overproduction in the system rather than find ways to deal with it once it's happened. In this way of thinking, a supervisor might ask, how can we change our system to eliminate the waste of overproduction? If you take the proper actions, overproduction can be eliminated. For instance, you can assess work in progress for reduction or elimination opportunities, balance the workload using takt time, use smaller batch sizes or no batches at all, and keep batch sizes to the level demanded by sales. The second of the 7 wastes is inventory. It's typically caused by minimum order quantities and bulk buying, and too much work in progress, or semi-finished goods. It can also occur when you let inventory levels rise during positive economic forecasts. And what are the consequences of excess inventory? These include costs for environmental control, record keeping, storage, and retrieval. Another consequence is that other problems that should be fixed are concealed. For instance, you might have an unbalanced workload or long setup times that need to be addressed. The extra inventory could also be at risk of possible obsolescence and damage. The traditional way of thinking about inventory entails figuring out ways to control and accommodate the excess stock. A manager might ask, how can I accurately control and track all this inventory? The Lean Six Sigma way of thinking, on the other hand, entails dealing with inventory before it becomes a problem. Using this thought process, a manager might ask, how can we work with suppliers to change their processes and allow smaller shipments? You can eliminate this waste by taking several actions. You can synchronize production with demand, use Kanban and pull systems, and work with suppliers to eliminate minimum order quantity requirements. The next common category of waste is rejects or defect correction. Rejects and defect correction are typically caused by unsatisfactory equipment maintenance, lack of training, poor instructions or design, and weak quality management. This waste can have very significant and often incalculable consequences that can affect the entire value stream. For example, rework, scrap, redesign, paperwork, or operators spending time repairing equipment. The traditional way of thinking about rejects and defect correction emphasizes inspection to make sure defective products don't reach the customer. In a Lean Six Sigma environment, the emphasis is on creating an atmosphere that emphasizes using Six Sigma tools to minimize defects. Rejects and defect correction can often be eliminated using Lean, Six Sigma, or other vigorous continuous improvement efforts. Another category of waste is processing, or more specifically, overprocessing. This can have several causes. For instance, taking unnecessary steps or processing to a higher level than the customer expects or requires. You might find this to be a gray area, especially where inspection and testing are concerned. Sometimes inspection will be a value-add activity, and other times it might seem to be a non-value-add. Like the other wastes, processing can have certain consequences, the most significant of which are wasted expense and wasted time. In the traditional way of thinking about processing, a manager might ask, how can we combine steps to speed up processing? The Lean Six Sigma thought process instead emphasizes reducing the amount of processing that occurs. So the manager might ask, how can we identify and eliminate unnecessary steps to speed up processing? So how can you eliminate the waste involved in processing? Well, this will vary depending on the situation. Here's an example. Suppose you file hard copies of purchase orders after you've entered them into a database. The hard copies are rarely, if ever, referenced. Eliminating the step of filing saves you time performing an unnecessary step. Now turn your attention to the next waste, waiting. Several factors can cause waiting: delayed shipments, long setups, absent people, or the lack of a point-of-use mindset. Waiting not only applies to people but to idle machines as well. Too much waiting can have consequences such as wasted resources, diminished morale among employees, and resources that sit idle. In a traditional process, waiting isn't usually considered worrisome. Why would it be? An operator standing in front of a machine probably means parts are being produced. You might try to find a way to keep the operator busy during machine downtime. But the Lean Six Sigma way of thinking is very different. In this case, the focus might be on balancing employee schedules in relation to machine cycle times so that no one is standing idle. So how can you eliminate waiting? Well, you could reduce setup times and engage in total productive maintenance. You could also cross-train personnel to take over in other areas, as well as improve scheduling. The next category of waste is unnecessary motion. Unnecessary motion is usually caused by poor workplace layout. For instance, poor layout and positioning of a workstation can lead to unnecessary reaching or bending. Unnecessary motion, like the other wasters, can have certain consequences, such as ergonomic problems and wasted time searching for or moving items. It can also be demoralizing for employees who can't find things when they're needed. The traditional way of thinking about unnecessary motion emphasizes centralized facility design. A manager might ask, how can we streamline tool and part retrieval by creating centralized locations for items? In a Lean Six Sigma environment, the emphasis is on creating an atmosphere that works for the employee to reduce wasted effort. A manager might ask, how can we change the layout of the workplace to fit the employee? You can take several steps to eliminate unnecessary motion. For example, you could redesign jobs to eliminate excess movements, or fit the workplace to the employee. Another good tactic is to employ Kaizen events to improve the work area. The cross-functional improvement team should include employees with experience in the positions involved, as well as people with the authority to make decisions. This method can lead to significant changes. The final category of waste is transport. Typically caused by poor layout design, it can have significant consequences. There is an increased likelihood of damage as you move items from one location to another. All transport is non-value add, and the costs of conveyor belts, forklifts, and other machinery can be significant. The traditional way of thinking about transport entails figuring out ways to control and manage transportation requirements. A manager might question whether it's more cost-effective to buy or lease a new forklift, or ask how transportation can become faster. The Lean Six Sigma way of thinking, on the other hand, aims to reduce or eliminate the need to move product. A manager might question how to change the layout of a process to create better physical flow. How can you eliminate transport waste? You could carefully map workflows, or assemble all the equipment used for one product or service and train personnel accordingly, even to use all the pieces if necessary. In addition to the 7 wastes, another form of waste exists but isn't included in the other categories. It's very common and counterproductive, yet is often ignored by companies and Six Sigma teams. It's called underutilization. Underutilization can refer to material, machine, and human resources. Sometimes employees' creative ideas for improving processes are suppressed by the organizational structure. In a Lean Six Sigma environment, though, employees' input is welcome and rewarded. For example, an employee in a call center has an idea about how to reduce the amount of time customers are placed on hold. In a traditional setting, the employee's idea might be noted, then forgotten. But in a Lean Six Sigma organization, a team might be created to figure out how to implement the employee's idea. So you've learned how the Lean Six Sigma way of thinking about waste differs from the traditional way. Now, how do you translate this into the real world? An example should tie it all together. Imagine that you're the black belt on a Six Sigma implementation project at a mid-sized integrated printing press. Prior to taking on a large-scale DMAIC project, you're applying lean tools to identify and eliminate wastes from your company's operations. There are 7 wastes you might use to eliminate at the printing press company, for example. You and your team determine that you can eliminate overproduction by printing smaller batches at a time. Eliminating inventory waste ties in with overproduction. When you're not printing more materials than you need, your storage requirements are reduced as well. By printing in small batches, you reduce this waste. You work with the quality assurance team to implement defect correction for materials to reduce rejects. Quality is improved through the use of standard work, more frequent training, and continuous improvement tools. You eliminate processing or overprocessing by first determining what it is that the customer is seeking, then communicating this to staff who operate the printing press. In some cases, materials were printed without the customer's final approval, which led to rework. When staff members are clear about the standards, inappropriate processing can be eliminated. You and your team find that the printing operators are often left waiting for marketing to sign off on materials before they can be printed. By improving the process of information flow, you eliminate this waiting period. Because employees in the finance department have been complaining about the layout of their workstations, you and your team find a way to eliminate unnecessary motion. You redesign their stations so everything they need is within easy reach. You and your team work with the warehouse staff to redesign the warehouse layout using mapping product flows and process relationship charts. This eliminates unnecessary transport of product, which saves time and staff costs. The different activities performed during a process either create value in the end product or they don't. Non-value-add activities are the waste that exists in a process. Waste analysis is a non-statistical analysis method used in Six Sigma to reduce the number of non-value-add activities at each step in the process. 7 categories are used to classify non-value-add activities. Known as the 7 wastes, they are overproduction, inventory, rejects or defect correction, processing or overprocessing, waiting, unnecessary motion, and transport. The traditional way of thinking might not consider these categories as waste, but the Lean Six Sigma thought process endeavors to improve the system instead of maintain the status quo. The improve stage is focused on pinpointing input variables that influence key output variables and determining how to set those key inputs in a way that will improve your outputs and your process. Experimentation is the key to accomplishing this Six Sigma goal by developing solutions, testing them, and then putting them into practice. The classical approach to experimentation is the one factor at a time approach, or 1FAT. The 1FAT approach measures the effect of changing just one factor at a time while holding all other factors constant. A good illustration of a 1FAT experiment is a drilling process where you want to know if drilling speed and certain other factors significantly affect drilling precision. The drill has 3 different speeds: 100 RPM, 120 RPM, and 150 RPM. So you decide the best way to test is by conducting 4 runs at each speed. You can then display the 12 tests in a chart in the expected running order, which is then completely randomized. The classic 1FAT approach tests a few factors while trying to keep all other factors constant. This leads to a number of limitations. First, the 1FAT method requires too many experiments to study all of the factors. Experimenters may never be able to discover the best combination of variables and therefore the best solution to improve the process. Second, the classical 1FAT experiment may not indicate how each factor interacts with each of the other factors, and the wide variety of combinations may not be determined. The conclusions drawn from a 1FAT experiment can be misleading as well. This is because the results don't account for all the possible combinations. And finally, a one-fat experiment can be a wasted effort, taking up time and money studying factors that aren't important. The best way to overcome these limitations and truly determine how factors will behave in all combinations is to systematically change the factors the one-fat approach attempts to keep constant. By changing the conditions under which the factors are influenced, you can better determine how the process can be improved. You must carefully plan these changes to ensure accurate results. The design of experiments, or DOE method, is an alternative to the one-fat approach. DOE helps you to carefully plan how you will carry out your test by controlling the inputs and then studying how the outputs are affected. DOE experimentation, like one-fat, has a number of identified purposes. And typically, experiments are conducted for only one of these purposes. First, it helps you choose between alternatives. This enables you to make an informed decision based on criteria such as quality or cost. It also allows you to identify key factors affecting an output. This can help prevent you from wasting time and energy. It enables you to achieve a target output or response as well. It allows you to improve robustness so that, while conditions vary, the strength of the process will remain intact. And finally, it enables you to optimize results even when you have a number of critical to quality or CTQ characteristics that need to be balanced. Consider again the drilling precision scenario. You may use DOE when choosing between two drill bit vendors based on quality and cost. Or you may be carrying out DOE in order to determine what other key factors besides drill speed and ground type affect drilling precision. You could also use DOE to help attain a target precision in drilling. DOE could improve the robustness of your drilling process to reduce drilling precision error and number of defects under a range of drilling conditions. Or, to reduce variability, the DOE method could help you distinguish which inputs you need to modify so drilling precision is the same every time. Finally, you can use DOE to optimize process results so you can determine how to drill the most precise hole for the least cost and wear and tear to the equipment. When choosing to use the DOE method, you should also take into account the advantages. First, limited expertise is required. Within DOE, you don't need to be a statistical expert to carry out the work. The method allows for experimenters who have base experience to still be able to succeed. In most cases, you'll notice right away if an important factor has been overlooked, and you can use standard statistical software. Also, DOE allows you to evaluate a number of factors at the same time, so fewer experiments are required, resulting in minimum interruption to business. By using DOE, you can concentrate your efforts on fewer tests, focusing on the main factors so results can be improved with minimal cost. Noise control is another advantage. In DOE experiments, input factors can be controlled in such a way that will decrease the effect of noise factors on your experimental results. And the final advantage is confidence in results. Because DOE tests are balanced, you'll be able to make confident decisions based on solid conclusions. Design of experiments, or DOE, helps make systematic and intentional changes to input variables to measure their impact on output, dependent, or response variables. In other words, the goal of DOE is to approximate a mathematical model of the effects of inputs on outputs and the ideal settings for optimizing your outputs. DOE is a very useful tool in Six Sigma. During the earlier stages of a Six Sigma project, typically a number of input variables are identified that could potentially impact process outputs. By using DOE, you can reduce the number of input variables and determine which ones really have the most impact on a process output, and then, using the reduced set of variables, optimize a process. You can also determine what the key settings should be to get the desired process output. It is important to have a basic understanding of the key DOE terms that can be used to do this. Consider an example of a drilling process in which you want to know if drilling speed and certain other factors significantly affect drilling precision. How would the goal of DOE apply to this example? By setting it up as a mathematical model, the process can be illustrated to have multiple inputs, X and an output, Y. An experiment would then be designed to answer a number of questions, such as which factors affect drilling precision, how do you set the factors to obtain the Y you desire, and how do you make Y stable? A well-designed DOE will provide the mathematical model you can use to answer these questions. Essentially, you use DOE to control the inputs in order to study how different levels of inputs affect key outputs. You want to find the levels of input variables that optimize the output variables. You're controlling outputs by carefully controlling the inputs that your DOE reveals to have significant effects on your outputs. You'll ultimately want to discover and maintain those input variables at the optimum levels to improve your process. Consider a scenario where a Six Sigma team at an auto parts manufacturer wants to analyze the effect of input-independent variables on the response in the casting process for front and rear bumpers as part of a designed experiment. As part of the process, a liquid material is poured into a mold which contains a hollow cavity of the desired shape and then allowed to solidify. The experiment is run and the results are placed in a table with the column headers runs, machine pressure, liquid material density, liquid material temperature, and breaking strength, response. There are 16 rows. Under the runs column, these are numbered 1 to 16. Runs 9 to 16 are replicates. Now, let's consider key DOE terms in the context of the auto parts manufacturer. The first term is runs. An experimental run, or simply run, is the observation or trial carried out during our experiment. It is a combination of all factor levels, low-high, low-medium-high, for which the resulting response is recorded. In the auto parts manufacturer scenario, all 16 rows in the table represent runs. An experimental run occurs when we set levels for all factors, run the experiment, and then collect the response data so it can be analyzed. In this example, a total of 16 runs are conducted, including 8 replicates. The next key term is treatments. A treatment, in the broader sense, is any experimental condition applied to the experimental units for making a comparison among them. In the auto parts manufacturer scenario, the experimental conditions, or treatments, are changed for each factor in each run, and each response is recorded and analyzed. This is the information recorded in the machine pressure, liquid density, and liquid material temperature columns. Responses is another key term. It refers to the output variable that is affected by the inputs in an experiment. It is sometimes known as a dependent or output variable. The goal in performing a DOE is to adjust input variables to optimize the response or output variable. A response can be a single variable or there can be several responses. In the auto parts manufacturer scenario, there is one response, the breaking strength of the bumper material. In the machine drilling process example, the response variable, or output, is the drilling precision of the holes. One of the key elements of planning is selecting the right factors, also known as independent or input variables. Another DOE key term, factor, refers to an input variable that you can set at different levels in order to examine its effects on the output variable of interest. Factors can be categorized as either continuous or discrete, also called attribute. In the drilling example, circumference or drill speed would be a continuous variable, whereas the type of hole and rock gradient would be considered discrete. Factors can also be quantitative or qualitative. From the drilling example, variables like drill bit size and moisture content would be quantitative, whereas a variable such as the drill operator's upper body strength would be considered qualitative. Factors can be controllable or uncontrollable as well. Controllable factors can be manipulated, fixed to retain a constant within the experiment, or changed to cause a reaction. Uncontrollable factors, also known as noise factors, incite variation in an experiment. Using methods such as blocking or randomization can prevent noise factors from skewing the experiment. In the auto parts manufacturer scenario, there are 3 factors: machine pressure, liquid material density, and liquid material temperature. Now consider another example, loan processing at a retail bank. Your response variable, Y, in this case, is the loan processing speed. Currently, loan processing at your bank is taking twice as long as your nearest competitors, and you're trying to improve this situation. With DOE, you might be able to control your output variable to a certain extent by changing the different levels of your input variables, your factors. It's important to note some of these factors cannot be controlled by the experimenter, and they might have an effect on the responses. However, all factors suspected of having some effect on response should be measured and used in the data analysis. The next term, factor levels, refer to how the properties of factors are measured. The levels of each factor are altered in an experiment to create different treatment combinations. In the auto parts manufacturer scenario, there are two levels for each factor, low and high, which are depicted as plus or minus. Let's take a look at the loan processing example to review the factor levels. For loan processing, you can take your different factors, which are your experience of loan processing staff, mode of application, amount of loan, and number of applicants, and you can set this up as two factor levels. And within each of these factors, you set your two factors appropriately. And then your symbol for these would be your low setting and your high setting. As you set up your levels, you need to make sure that these different values for each level are far enough apart so that the effect on your response variable, your Y variable, can be appropriately measured. And so you're not going to include every possible value, but you're going to set this up based on high and low levels. Now, it's important to note that with two factor levels, because you're only looking at a low value and a high value, you're assuming a linear relationship between these two values. When you look at a DOE that has three factor levels, you can take into account a middle value. So you would have your low, a middle, and also a high value or a high setting. In the auto parts manufacturer scenario, you have three different factors of input material, time, and temperature. You have three levels for each of those variables. So you can have material A, B, and C. You could have a time of 30, 45, or 60 seconds, and a temperature of 100 degrees centigrade, 125 degrees centigrade, or 150 degrees centigrade. Now, it's important to note here that, again, you've got several continuous variables, including your time or temperature, and then your input material is categorical. So it is possible to have a mix between those two different types of variables. One challenge in the DOE is the occurrence of experimental errors. Experimental error, the next key term, can be defined as either variations observed during identical test scenarios, systematic error, or variations that are not attributed to experimental factors, random error. Systematic error occurs when the same error is evident every time an experiment is run. This means the design of the experiment has an inherent error. One type of systematic error is known as bias. When you encounter bias in your experiments, one of the key aspects of bias is that it's equal to the difference between your known value, such as a calibrated standard or expected outcome, and what you're actually observing or yielding as a result. An example of a systematic error is an experiment where the calipers being used to take all measurements is calibrated incorrectly. Every measurement taken would be off by the same amount. Recalibrating the calipers could correct this error. Now let's discuss random errors in more detail. An example of random error is an experiment where you have to record the weight of a machine part. Each time you measure the part, the scale provides you with a slightly different amount, 1.346 grams, 1.347 grams, and 1.345 grams. This type of error can be decreased by calculating an average of the measurements. While this may seem like human error, it's actually not. The limitations of the finite measurements of the scale are a part of the experimentation process. Because no measurement can be perfectly precise, random or unpredictable error occurs in almost every experiment. It's also important to note that human errors can interfere with an experiment, but these aren't considered experimental errors. The above-mentioned experiment contains an example of bias. There is a measuring instrument that's used to measure a part. Over time, the weight of the part increases to 1.446 grams, but according to the true standard, it's supposed to be 1.346. That's a bias of 0.1 grams. The final key term is nested designs. A nested DOE occurs if you have at least two factors, and a factor in the first category occurs within only one category of the other factor. In the auto parts manufacturer scenario, for example, you can have two teams measuring one each of the two factors, temperature and time, in two categories. In this example, the design is nested if the same observation is made within a category of factor 2, which observes time, as is in a category of factor 1, which observes temperature. A nested design can be useful to test whether there is significant variation among groups, or teams, or among subgroups within teams. The ultimate goal of Six Sigma is to improve your process, and in order to do that, you must design solutions, test them, and then put the best ones into practice. The design of experiments, or DOE method, is an alternative to the classical one-FAT approach. DOE helps you carefully plan how you will carry out your test by controlling the inputs and then studying how the outputs are affected. The purposes of DOE include choosing between alternatives, identifying key factors, achieving a target, reducing variability, improving robustness, and optimizing results. The key DOE terms that you need to be familiar with are factors, factor levels, responses, runs, errors, treatments, and nesting. To account for experimental errors and hopefully reduce their effects, you should follow some basic principles for good experimental design: balanced design, randomization, blocking, replication, and repetition. Balanced design is the first principle to be considered in effective experimental design. For a design to be considered balanced, all treatment combinations in the design should have the same number of observations. You must first define the factors and levels of an experiment and then calculate the runs required. Putting all of these elements of your experiment into your design plan helps address the challenges of bias, error, and uncontrollable factors right in the design phase. For example, in an experiment with two factors, A and B, and two levels for each factor, high and low, you do 4 runs. Each run must test at either the high or low level for each of the two factors. So if you set up your experiment at the low level for both factors in the first run, A low and B high in the second run, A high and B low in the third run, and both A and B high in the final run, your experiment is considered balanced. Runs need to be evenly distributed so that all levels are tested for all factors in different combinations. In the same experimental design, if you set up your experiment with both factors at the low level in the first run, both at the high level in the second run, both low in the third run, and then both high again in the final run, your experiment would be considered unbalanced. The settings of each factor don't occur the same number of times with each other setting. In fact, you'd be essentially running the same experiment twice, with the highs and lows matched together. The next principles you consider in good experimental design are randomization and blocking, two methods that are highly effective in decreasing the impact of error and uncontrollable factors. In statistical analysis, you assume that any observations are independent, but this goal is actually reached through randomization. Randomization balances the effect of noise variables. It also ensures each person or item in a population is equally likely to be selected for inclusion in a run, and therefore equally likely to be subject to any noise factors present in that run. The process of randomizing the run order is recommended. So, by implementing randomization, you are minimizing the possibility of bias in your results. The goal of randomization in DOE is to organize the experiment to have treatment combinations done in a random manner, improving statistical validity. By randomizing your experiment, if the outcome indicates a clear result, you'll be more secure in your conclusion that one process or product is better than the other. In other words, randomization places systematic sources of variability into the error term. This is a good thing because it prevents you from unknowingly introducing a causal pattern and allows you to make valid inferences. The main disadvantage of randomization is that it creates the potential for a large error term. Blocking is one way around this. Blocking is a technique that takes into account additional non-experimental factors that you suspect could be sources of variation in the design. When such a factor is identified, you can use blocking to create sets or blocks based on this factor. Treatment runs are then randomly assigned to the blocks. In this way, experimenters reduce unwanted variation in the experiment and reduce the total error term. For example, a block in an experiment may be a portion of the population under study that's expected to be more uniform than the population as a whole. If you're conducting an experiment on the amount of individual TV viewing in a neighborhood, each household might be considered a block, as opposed to all the households in the neighborhood or all the individual people. You can achieve greater precision by comparing the units within a block, since the main differences between the blocks are assessed separately. Population variation can be expressed as either within-group or between-group variability. You can eliminate between-group variability by assigning treatments within blocks. Blocking allows between-block variation to be independently assessed and subtracted from the experiment, so results can be analyzed without additional distractions. This process removes the unnecessary variation between blocks and, in turn, provides more precise results. Blocking achieves greater precision because it confines comparisons to within blocks. In other words, you eliminate the difference between blocks and examine the correlation within blocks. To measure the effectiveness of blocking, you can run an analysis of variance, or Anova, to ensure the within-block variability is less than the between-block variability. The goal is to ensure the in-block variation is as minimal as possible, so the between-block variation provides valid and essential information. Consider this example of within-group and between-group variability. You're conducting a study of the variation in the wear and tear of tires. If you study all car models as one large group and only measure the wear and tear on the left front tire, the results will be skewed. If you select different car models as the blocked variable and randomize the position of the tire being tested, you can increase the similarities among the blocks. This will create more homogeneous blocks, which leads to more precise results because the variation within blocks has been minimized. You can also block in time or space instead of by similarities in factors or population. For example, in an experiment conducted over a number of days, the runs made on the same day are most likely to be more similar to each other. Or, in an experiment where a staining process is being tested on wood, areas that are closer together would be expected to be more similar than areas that are farther apart. The principles of randomization and blocking can be used together effectively, since they're both tools for dealing with unavoidable sources of variability. By assigning treatments within blocks randomly, you'll eliminate any systematic effects between blocks while also decreasing within-group variability. In an experiment, the units you choose for a sample, the order in which samples are tested, and the order of runs are all experimental elements that would be appropriate for randomizing. And non-experimental elements that could be potential sources of variation in the experiment, such as car models when you are testing tire brands for wear, would be appropriate for blocking. The last two basic principles for good experimental design are repetition and replication. While these two principles may seem the same at first, in this context, they're two very different methods for overcoming error and bias. Replication is the process of repeating the entire experiment, including the setups, 2 or more times. Replication provides you with additional readings for the entire set of treatments and helps increase the precision of the estimates of the effects in an experiment. Replication improves the chance of detecting any statistically significant effect of natural process variation, or noise, and allows you to measure inherent variation in an experiment. This leads to increased precision when estimating the effects of factors, since the average of a number of observations is likely to be closer to the true value than a single observation. When using replication, you need to take into account a number of considerations. For instance, you should be aware that multiple replications may add increased precision to your prediction model. You should note that with more data, you may be able to pinpoint less evident effects and have greater ability to detect effects of a given size. However, when designing an experiment to examine a large group of factors, you usually don't conduct multiple replications. The number of replications you decide to run may be dependent on other issues, such as cost or time. Unlike replication, repetition doesn't require you to set up and run the entire experiment again. Repetition involves repeating the same treatment 2 or more times before moving on to the next treatment within an experiment. When you take 2 or more measurements for the same treatment without changing the setup, you're able to pick up any measurement variability, which is an indicator of measurement error. In an experiment with 2 factors and 2 levels, you test all the combinations of factor levels and then reset the experiment so all elements are the same and conduct the test again. That's replication. In an experiment with 2 factors and 2 levels, you repeat the same treatment twice before moving on to the next. This is repetition. There could be more than 2 factors and levels in an experiment, and you could have repeated each treatment more than twice. In experimental design, there are a number of challenges to overcome in dealing with error and noise. But utilizing some basic principles for good experimental design can help to reduce these challenges. Balanced design ensures that the factor level combinations are balanced and that every level is tested for every factor. Randomization is a method that helps balance the effect of noise variables. It ensures that each item in a population is equally likely to be selected for inclusion in runs and that runs are done in random order. The main disadvantage of randomization is that it creates the potential for large error terms. To combat this, blocking takes into account any extraneous factors and groups these factors into blocks. You can then randomly assign treatments to the units within the blocks. Replication is the process of setting up identical conditions for an experiment or run and running it again a second time from scratch. Repetition involves taking measurements of each experimental unit twice or measuring 2 units in each sample. Once you get to the end of the DOE process, you'll want to measure more than just the impact of factors on the experiment's output. Determining and analyzing the main effect and interaction effects is the next step in the analysis of a factorial design experiment. From your training so far, you know the effect of a factor on the dependent variable is the main effect. The effect evident in the output due to interaction of 2 or more factors is the interaction effect. This occurs when the effect of one factor on the output depends on the level of 1 or more other factors. Being able to interpret main effects plot graphs is a valuable skill you can use to determine which input has the greatest effect on the response variable. When you plot an input factor, the slope of the angle defines the main effect. The steeper the slope, the greater the main effect. Consider this example. You're conducting an experiment to select the best wood stain based on absorption percentage. There are 3 factors: the quality of the wood, the temperature, and the solvent level in the stain. Each factor has 2 levels. Wood quality can be classified as either Class 1 or Class 2. The temperature of the shop is tested at 70 degrees and 80 degrees. Finally, the solvent level in the stain can be categorized as high or low. You determine that you need to do 8 runs, and to ensure the test is precise and to pick up any measurement variability, 5 repetitions are needed for each run. So you run the experiment and record the results in a data table. You must then calculate the average of the 5 repetitions for each of the runs. Then you can proceed to calculating the main effect. The first step in calculating the main effect is to find the average of the results for each level of each factor. So, for example, wood quality of Class 1, W1, occurs in runs 1, 2, 3, and 4 and has an average of 5.5. Likewise, you can calculate the average for W2, T70, T80, S-, and S+. The second step is to plot the effects for interpretation. You get 3 results. The average response for W1 was 5.5, and the average response for W2 was 5.5. When plotted, this presents as a straight line. This indicates no effect between the levels of the factor wood quality. In terms of temperature, the average response for T70 was 6.75, while the average response for T80 was 4.25. When plotted, this indicates a small effect with a slight slope downward between the two levels of temperature. Finally, the average response for S- was 7.25, and for S+, it was 3.75. When plotted, this presents the largest effect, with a fairly steep slope. The best stain is determined by the lowest main effect calculations. In other words, the combination that results in the lowest value for the response variable because you want to minimize absorption. You want to choose the level for each factor that calculates to the lowest average result, so you choose a temperature of 80 degrees and a stain with high solvent content. Since the values for W1 and W2 are the same, you must consider other issues when choosing which to recommend. Since the wood of Class 2 is less expensive, you would recommend it as a cost-saving measure. Often, the main effect is referred to as the high-level result minus the low-level result. In that case, the factor that has the largest difference between its levels, regardless of positive or negative sign, would be the main factor, or the factor with the greatest impact on the characteristic being studied. In the wood stain example, when you calculate the differences of the levels of each factor, you discover that the greatest difference in responses is between S+ and S-, with a calculated effect of negative 3.50. This indicates that the solvent level in wood stain is the factor with the greatest main effect. There's always a possibility that the differences you find may not be statistically significant. This can happen if the experimental error is large, indicating that the highs and lows could be equally due to chance as to real change. To verify that your results are, in fact, statistically significant, you'd typically use Anova. Along with the main effects, you'll also want to analyze the interaction effects in your experiment. As you know, when the effect of one input factor on the output is dependent on another input factor, this is known as the interaction effect. When determining the interaction effects, it's helpful to arrange your design table so each high-level setting is represented with a plus sign and each low level is represented with a minus sign. Then you add 4 new columns for the interaction effects. The 4 columns are factor 1 multiplied by factor 2, factor 1 multiplied by factor 3, factor 2 multiplied by factor 3, and factor 1 multiplied by factor 2 multiplied by factor 3. You can then begin to characterize each interaction as positive or negative by filling in the table. Keep in mind the rule that if the signs are the same, the interaction is positive, and if they're different, the result is negative. A positive sign means the levels of both factors are high for that trial, or they are both low for that trial. A negative sign means that one factor level is high while another is low. For the 1 by 2 by 3 column, you must multiply 1 by 2 first and then multiply that result by 3. With the response values in the last column, you can calculate the interaction effects between wood quality, W, and temperature, T. Find the average of the runs with a plus sign, runs 1, 2, 7, and 8. Likewise, calculate the average for W by T runs with a minus sign. Then you find the difference between W by T plus and W by T minus, or the interaction effect of wood quality and temperature. You always subtract the negative factor combination from the positive. If the interactions exist, in other words, they aren't zero, it means the main effects are not additive. An additive effect is an effect in which 2 actions used in combination produce a total effect the same as the sum of the individual effects. In the wood stain example, an interaction effect of wood quality and temperature results in a difference of 0.50, which indicates that the main effects are not additive. Alternatively, T by S is 0, so the main effects of temperature and solvent level are additive. After finding the interaction effects values, you plot the interactions as 2 lines on a graph and analyze the results. The plot doesn't tell you if the interaction is statistically significant, it simply shows the impact of changing one factor on another. Interaction effects, when plotted, can present in one of 3 ways. When you plot the interaction of 2 factors and the lines are parallel, you know the lines will never intersect and therefore there's no interaction. But if you plot the interaction of two factors and the lines aren't parallel, you know that eventually the lines will intersect and that there's an interaction, but it's only moderate. However, like main effects, whether or not an apparent interaction is statistically significant is tested by a hypothesis test. When you plot the interaction and the lines are sloping toward each other, you know they will intersect and there's a strong interaction between the two factors. Access the job aid main effect and interaction effect plots after the video to review examples of plots of main effects and interactions. Within experimental design, you must take into consideration power as well as effects. The power of a test is the ability to conclude that the null hypothesis, that there is no effect, is false when it actually is, and to correctly reject the null hypothesis. It's highly desirable to have a test with the appropriate amount of power. Power that's too low can lead to failing to detect a main or interaction effect and, in turn, deciding that there are no effects for that factor. Having a test with power that's too high can lead you to determine that very small effects are significant when they're not. A number of things have an increasing effect on power. First, a larger effect size. You can increase the size of an effect by making the difference between factor levels larger. Higher alpha also has an effect on power. By increasing alpha, you decrease beta, and since power is 1 minus beta, increasing alpha also increases power. Third, less variability has an effect on power as well. When there's less variability and a smaller standard deviation, there's a better chance of detecting smaller differences. If you have more test replications, then you have more samples and increased confidence in your results, since your test will be more sensitive. And finally, if you add center points, you increase power as the standard deviation estimation is more precise. A number of other design considerations can affect the power of a test, such as the number of factors, number of blocks, number of terms omitted from the model, and use of full versus fractional designs. However, these considerations should be driven primarily by your research objectives rather than by power considerations. Power is also related to sample size. Increasing the sample size increases power. So the most practical way to increase power is to increase the number of replicates and, in turn, the size of your sample. But keep in mind, having a sample that's too large just to achieve more power can result in extra expense and an experiment that's unmanageable. You can manually calculate the sample size for a given power level by using a formula, or you can calculate it with statistical software. Think about this example. You work for a cookie company and are conducting an experiment on the moistness of a new cookie. If you run the experiment with 3 replications, your design has a power of 0.80, or an 80% chance of detecting the main effects and interactions. If you increase the replications to 4, you increase the power of your experiment to 92%, and in turn increase the precision of your test. The power of a test can be assessed in 2 ways. First, power of a test can be assessed prospectively. When it's assessed prospectively, it's done before the data is collected. You do this to take into account the requirement of the test's sensitivity for detecting effects in the experiment. It helps if you know the correct amount of power you need in order to detect the effects present in your experiment. Second, retrospectively assessing the power of a test occurs after data has been collected. This type of assessment is primarily used to determine if the power of the test was adequate. If you find the level of power was too low, you can change the design to increase the power. If you find it was too high, you can discount an effect that seemed meaningful and in fact wasn't. For example, in a prospective assessment of power, you can take such actions as increasing sample size to reach the level of power most appropriate for the test. On the other hand, retrospectively, you can examine an experimental design of a test, and if there were no statistically significant results, you can discount an effect to detect the minimum effect. Determining and analyzing the main effects and interaction effects is vital in the analysis of a factorial design experiment. The effect of a factor on the response variable is the main effect, while the effect evident in the output due to a combined interaction of 2 or more factors is the interaction effect. Interpreting main effects plots as either no effect, small effect, or large effect can help determine which input has the greatest effect on the response variable. Interaction effects, when plotted, can present in one of three ways: no interaction, moderate interaction, or strong interaction. The presence of an interaction effect indicates that the main effects are not additive in combination. The power of a test is the ability to conclude that the null hypothesis is false when it actually is, and to correctly reject the null hypothesis. Experimenters should consider how various design elements influence the power of the experiment. In experimental design, you want to make sure your experiment detects all the effects you are interested in while keeping downtime and costs in check. Some experimental designs blur the effects of some factors, making it impossible to detect them, but this is the trade-off when you want more streamlined experiments with fewer runs. In certain experimental designs, any effects that can't be estimated separately, in other words, the effect of one factor is combined with another, are called confounded effects. You may also find that one effect is confounded with another if they have the identical level values in their column. Notice that the interaction of A and B, the product of the A and B columns, is the same as column C in the table. Interaction and main effects that are confounded are often referred to as aliased with each other. The confounding pattern occurring in a design is described by alias structure. In design of experiments, or DOE, fractional factorial experiments have interactions and main effects confounded or aliased. However, DOE allows you to plan which factor effects will be confounded so you can design your test around the effects that are most likely to be significant. For example, the yield of a gas production facility was tested with 4 factor inputs, A, B, C, and D. You want to ensure the experiment is cost-effective, and you can't shut down the facility for any length of time to make the runs. You suspect there will be an interaction effect for factors B and C, and that factor A will have a significant main effect. You choose to conduct a fractional factorial experiment, knowing that some of the factor effects will be confounded. If factor A is confounded with the interaction BC, then the main effect estimate for A will be indistinguishable from the interaction effect of BC. Because of confounding, you can't estimate which proportion of the effect is due to the main effect of A and which proportion is due to the interaction effect of BC. Given what you suspect about the main and interaction effects of your factors, you'll want to avoid confounding A with BC. The two most common types of design are the full factorial and fractional factorial experiment. The full factorial experiment in this example has 4 factors and 16 runs. A full factorial experiment is conducted on all levels of all factors and has no confounding. Responses are measured for every combination, so when there are more than 2 or 3 factors, a large number of runs are required. For example, if you have 6 factors and 2 levels for each factor, you'll need to conduct 64 runs in a full factorial experiment. The fractional factorial experiment in this example has 4 factors and 8 runs. A fractional factorial experiment excludes some of the factor-level combinations. Due to this, some degree of confounding always appears in a fractional design. This type of experiment is used primarily to reduce cost and time, and if other constraints are placed on the experiment. An experiment with a larger number of factors is often carried out as a fractional factorial to reduce the number of runs. For example, if you have 6 factors and 2 levels for each factor, you'll only need to conduct 32 runs for a 1/2 fractional factorial experiment. When designing a fractional factorial experiment, you need to know which effects are confounded so your conclusions aren't compromised. You should note that full and fractional factorial designs will be explored in detail later in this course, as well as in the next course. In dealing with a fractional factorial design and effects that are confounded, you'll need to be able to measure the extent of confounding, which is called the resolution. Resolution defines the order of confounded main effects and interactions, and the classifications are expressed in Roman numerals. You can calculate resolution by adding the number of factors in interaction or main effects in a confounded pair. For example, in a resolution 5 or Roman numeral 5 design, one-factor main effects like A are confounded with four-factor interactions like BCDE, and two-factor interactions like AB are confounded with three-factor interactions like CDE. When you're designing an experiment, you determine what resolution is necessary to detect the effects that you want to leave unconfounded. Normally, you'll want to design a fractional factorial experiment in which the main effects and lower-level interactions, like two-factor or three-factor interactions, are unconfounded. This way, you can estimate the results individually for these important interactions. If confounding must occur in your design, you'll want it to be between main effects and higher-level interactions, such as four-factor or higher interactions. Interactions of three or more factors are rarely significant, so you can assume that those interactions will be of negligible importance. There are 6 resolution levels: Roman numeral 1, Roman numeral 2, Roman numeral 3, Roman numeral 4, Roman numeral 5, and Roman numeral 6, though Roman numeral 3, Roman numeral 4, and Roman numeral 5 are most common. Other higher-level resolutions can also be achieved depending on your experiment's requirement. A resolution level 1 experiment is essentially a one-fat experiment where each factor is adjusted one at a time. This is highly undesirable. Next, a resolution level 2 experiment occurs when some of the main effects are confounded with each other. This is highly undesirable because the team will want to estimate these effects separately. A resolution level 3 experiment happens when no main effects are confounded with each other, but main effects and two-factor interaction effects are confounded. It's the least desirable for fractional factorial designs. The next resolution level experiment, level 4, has main effects confounded with three-factor interactions or two-factor interactions confounded with each other. It's more desirable than a level 1, level 2, or level 3, but not as ideal as a level 5. A resolution level 5 experiment has confounding between main effects and four-factor interactions, and between two-factor and three-factor interactions. Since these effects are likely to be negligible anyway, resolution level 5 is the most desirable for fractional factorial designs. And finally, a 6-factor design performed in 32 runs will be a resolution level 6 experiment. An experiment with the same number of runs will also be a full factorial experiment with no confounding if there are 5 factors in the experiment. To remain within the scope of this course, you can presume all examples are experiments of 5 factors or less. Think back to the gas production facility example. The experiment tested 4-factor inputs, A, B, C, and D. You know that there may be an important interaction between factors B, C, and D, and you suspect that A has a significant main effect as well. What resolution would be best here? You know a resolution Roman numeral 3 would save time and money with fewer runs, but it would obscure some effects through confounding. You also don't want to confound one-way with three-way effects, and a resolution of Roman numeral 4 would confound them. So your design must contain enough runs to reach a resolution of Roman numeral 5. This way, your experiment with 4 factors and as a full factorial needs to aim for resolution Roman numeral 5 to detect all the effects and interactions that you're interested in. In keeping with the sparsity of effects principle, which states that the simplest model is usually the most plausible, a resolution level Roman numeral 5 experiment is the closest to a full factorial design and so is the most desirable. If you can design the experiment so the higher level interactions are indeed of lesser importance, you can essentially ignore those elements that are confounded. This means your results will be similar to those from a full factorial experiment. In a designed experiment, any effects that can't be estimated separately are considered confounded or aliased. A fractional factorial experiment offers a clear advantage over the full factorial when it comes to reducing downtime or costs. However, you have to ensure that any important effects are either unconfounded or confounded with effects that are negligible. Resolution levels indicate the extent of confounding. There are 6 resolution levels: resolution Roman numeral 1, resolution Roman numeral 2, resolution Roman numeral 3, resolution Roman numeral 4, resolution Roman numeral 5, and resolution Roman numeral 6. Resolution levels between resolution Roman numeral 3 and resolution Roman numeral 5 are the most common, and of these, resolution Roman numeral 3 is the least desirable, and resolution Roman numeral 5 is the most desirable. Having an experimental design process with steps to follow can make the difference between a poorly planned experiment that fails miserably and a well-designed one that improves your process immeasurably. Within the Design of Experiments (DOE) process, there are 6 steps to designing and planning a well-rounded experiment. First, you define the DOE problem and experimental goals. Then, you select the responses, factors, and measurement method. Next, you choose the appropriate design. You then conduct the experiment and collect samples, after which you analyze the data and find results. And finally, you verify the predicted results. The first step, when you define the problem and the experimental goals, is vital. You're essentially designing an experiment that will truly answer the question your problem is posing. The second step involves selecting the responses, factors, and measurement method for your experiment. You first need to determine the output or response variable of your process, keeping in mind these 2 considerations. One is that the response variable should generally be something that's quantitative, agreed to by all parties, and related to the experimental objectives. Another consideration is that you should try to determine a response variable that's not combined with 2 or more process measurements. That way, right from the start, the results are not confused with any other elements. Another key task in Step 2 is determining appropriate input variables, or factors, to experiment with. Once you meet with everyone involved in the planning group, you'll usually be able to pinpoint most of the important input factors and those factors that are less important. At this point, you'll also determine the levels of each of your factors. It's important to set the factor levels at reasonable measurements of high and low. If they are set too closely together, you won't be able to grasp the actual effect of each factor level. Once the factors and levels are selected, you can move on to choosing the appropriate measurement method. In the third step, you choose an appropriate design based on the information you've gathered so far. Try to find a balance between the results you're trying to reach and the cost of the experiment. If you choose a design to specifically come in under budget, you'll have room to add a few corrective runs if needed. Other considerations when choosing your design are the resources available and the amount of control you have over the experiment. Once design and planning are completed, you can move on to Step 4 to conduct the experiment and collect samples. At this point in the process, you'll take the design into the experimental setting and physically run the tests that you have planned. The design will dictate how you'll proceed, but when conducting runs, it's vital to randomize them to ensure precise results. It's also important to consider replication and exactly how the experimental results will be recorded. These decisions are typically made in the planning stages and are all carried out in Step 4. For the next step, Step 5, you analyze the data and find results. Using statistical software, you can run an analysis to identify the main and interaction effects of factors on the response variable. From this data, you can make your conclusions and suggest process improvements based on both practical and statistical significance. And finally, during Step 6, you verify the predicted results. After making suggestions on how to improve the process, you should follow up with trials to validate the findings. This is simply good scientific practice and may help detect any problems before they surface. The first step of the DOE process is considered the beginning of the planning stage, and it involves defining the DOE problem and any experimental goals. Although the ultimate goal of DOE is to discover how to achieve an optimal response, there are 3 main categories of DOE applications that contribute to this goal. These applications, screening, optimization, and robustness testing, all have individual objectives that, when accomplished, benefit the next application in line. You wouldn't necessarily conduct an optimization experiment without having done a screening experiment first. Likewise, a test for robustness is conducted after you run an optimization experiment for identifying and validating the optimum factor settings. Access the content 3 applications of DOE after the video to review the 3 types. Screening is applied at the beginning of DOE to help you explore all of the factors. This helps you to identify the most significant ones and to determine appropriate factor levels. Optimization is applied after screening has narrowed down the factors to the few most important and their levels. The goals of optimization are to help you estimate the responses of all possible factor combinations and identify the factor settings at which the values for all responses are optimized. Robustness testing is the final application of DOE implemented before product release or final process change. The goal of robustness testing is to help you find out if the new method is impervious to factor level fluctuations and to understand how factor levels can be changed or refined to increase robustness. Consider this example to illustrate the objective of each application of DOE. You work for a call center and are applying DOE to help improve the customer service complaint process. The input variables have been identified as employee experience, complaint delivery, phone or email, number of stations with new computers, time of year, and type of complaint. The response variable is customer satisfaction, measured in terms of customer satisfaction score. You conduct a screening test to determine that out of the 5 factors, employee experience and complaint delivery are the 2 factors that have the greatest effect on customer satisfaction score at specific factor levels. You then conduct an optimization test on the 2 factors to find that the optimal level of employee experience is 5 years and complaint delivery is by phone. These conditions produce the highest customer satisfaction score of 7.5. Finally, you conduct a robustness test to determine if the customer satisfaction score of 7.5 can be maintained over time at the optimal factor settings even with their natural variation. Consider another example, this time in a manufacturing context. You're working with a bolt manufacturer studying the influence of 4 factors on the precision of the bolt's size. The 4 factors are metal alloy content, press calibration, press PSI, and finish sanding. The response variable is defect rate, and the desired response is to minimize the defect rate. Each factor is assigned a high and low level, alloy content high or low, calibration weekly or monthly, press PSI high and low, and finish sanding high grade or low grade. You conduct an 8-run screening test to determine that 2 of the factors, alloy content and press PSI, have an effect on the response variable. Your test also reveals that alloy content at the high level and PSI at the low level produce desired results. You then move on to conduct an optimization experiment on those 2 factors, alloy content and press PSI, with varying combinations of levels. Your tests reveal that alloy content at 11.45% and PSI at 17.5 produce bolts with the least amount of defects, 1.5% in this case. Conducting robustness testing to validate the findings before you make changes to the process is your next step. You want to test that minor fluctuations in PSI settings over the run of a production day don't skew your defect count. You also want to understand how much of a range plus or minus the ideal PSI setting your production line can take before producing defective bolts. Screening tests give you yes or no answers and narrow down the many factors you've identified at specific levels to those that are most important. Optimization tests examine all possible factor combinations and their resulting responses to determine the point at which the response variable is optimized. You move from general yes and no answers when screening to specific factor and response values in optimization. The final application of DOE is robustness testing, which is carried out to determine how stable the optimal factor level settings are in your process. Also, robustness testing helps you determine a range within which the levels can change but remain robust. Access the Job Aid DOE planning considerations and recommendations after the video to review a summary of the planning stage of DOE. Within the design of experiments DOE process, 6 steps aid in designing and planning a well-rounded experiment. Define the DOE problem and experiment goals. Select the response, factors, and measurement method. Choose the appropriate design. Conduct the experiment and collect samples. Analyze the data. And verify the predicted results. The 3 applications of DOE, screening, optimization, and robustness testing, all have individual objectives that help to further define the experimental goals. Screening helps you to explore all factors, identify the most influential ones, and determine their appropriate factor levels. Optimization helps you to estimate the responses of all possible factor combinations and to identify the settings at which the value for the response is optimized. Robustness testing is used to test the sensitivity of the response to small changes in the factor settings and to redefine factor levels if needed, so that small changes don't cause the response to change significantly. The general goal of design of experiments, or DOE, is to approximate a mathematical model of the effects of factors on the response. It also aims to determine the ideal factor settings for optimizing the response. Essentially, DOE is used to control and adjust the factors in order to study how the response is affected by different factor levels. Step 2 in the DOE process, select responses, factors, and the measurement method, is a key step in designing your experiment to ensure you meet these goals. You'll typically begin by selecting the response variable. Whether you're selecting one response variable or several, there are a few recommendations to keep in mind. First, when you meet with your team to brainstorm about possible responses, you should use a process map to identify key responses. This way, you can examine every angle of the process. Another recommendation is to avoid binary variables, so you must avoid responses that are of pass-fail type. An experiment with binary response variables would require large samples to measure the effect of each factor. You should also identify responses that are functional requirements or design parameters. All members of the team should have a chance to provide expert input and agree that an identified response is, in fact, a key response. As a final recommendation, identify responses that are easily and accurately measured. Within DOE, it's suggested that responses always be quantitative or measurable by a numerical value to ensure accuracy of results. The team's measurement system must be able to measure the responses. It's recommended that you avoid binary response variables in DOE, since choosing a binary response means you'll need a large sample size. This is neither practical nor cost-effective. If you choose a binary variable, you must then create a scale in order to convert it to a quantitative variable. You must carefully define the scale to ensure a good DOE with consistent results that are stable and accurate. Setting a measurable response of key interest is an important step in designing a meaningful experiment. Selecting factors and their levels is the second element of Step 2 in DOE. Within experimentation, factors and levels are changed in order to systematically observe which have the greatest impact on the response variable. With this information, factor levels can be adjusted specifically to achieve optimization. The general goal of factor selection is to identify the best combination of settings for the factors that have the greatest potential for response optimization. Selecting factors is carried out with the aim of selecting appropriate factors from among all the identified factors. So the more factors that are identified, the more opportunities you have for optimizing the output and enhancing the robustness of the process in the presence of noise variables. This concept will be explored further in a later course. There are a number of recommendations to consider when selecting factors. First, use the transfer function to identify factors that impact the response. Then consider all factors judged important by operators and engineers. And finally, choose factors that can easily be varied and controlled. To determine which factors to implicate in optimizing a single requirement or response, you use the transfer function. The transfer function allows you to follow a factor down through progressive levels of subprocesses to better understand its effects. It's first identified using process mapping, and further details are added using derivation, modeling, and experimentation. You should also put together a team of people close to the process in order to brainstorm factors. Process operators and engineers will have the specific knowledge to be able to judge which factors are important and their impact on the response. This type of discussion will also reveal factors that exist but are less important. By including people close to the process, you have expert opinions helping determine key factors and the most appropriate levels to test. It's also recommended that you choose factors that can easily be varied and controlled. The factors that you identify as important to the process will almost always be factors that you can control and may therefore be selected for the experiment. An experiment assumes that you'll be able to change the settings of the factors so that you get a desired response. Factors that are not controllable cannot be considered part of an experiment. When selecting factors, you should avoid factors that are impractical to vary. You should also avoid factors that cannot be used in combination with other factors in the experiment. Once you determine the factors of the experiment, you next need to think about the associated levels. In relation to choosing factor levels in Step 2 of DOE, there are a few recommendations to consider. First, choose fewer levels when cost efficiency is critical. If you're willing to trade some detail for the sake of simplicity and cost efficiency, choose fewer levels for your experiment. Most screening experiments are conducted using only 2 levels for each factor. Second, choose more levels when detail is important. If you're not willing to trade detail for simplicity and cost efficiency, choose more levels. Of course, choosing more levels will subsequently increase the cost and complexity of your experiment. And finally, avoid too large or too small of a range. Within DOE, it's suggested that the 2 levels for each factor are reasonably high and low settings within the possible range of values for the factor. In a DOE experiment, you'll alternate the levels of your factors to observe how different factor level combinations affect the response. Having 2 levels provides a value on either end of the spectrum, which allows you to study the effect without having to compromise cost or resources. So while the data is fairly limited, you have the advantage of a simple and straightforward experiment. When you get into more than 2 levels, you need more data, it costs more, uses more resources, and creates a more unwieldy experiment. It's generally not recommended to have more than 2 levels. If you're beginning an experiment and considering more than 2 levels, you can ask yourself the question, why does the experiment need more than 2 levels? Usually when you analyze this further, the reason for having more than 2 levels is found to be weak, or it may even disappear. In some cases, factors can be discrete instead of continuous. This means the values you'd use to express the high and low levels of factors need to be expressed as discrete or attribute values. For example, with color of ink used in printing, the levels would be red and black. There is an important rationale for setting each factor at reasonably high and low settings of the possible range. Setting the levels too close together won't provide you with an accurate enough understanding of the factor's effect. On the other hand, setting them too far apart and into extreme highs and lows may cause the experiment to fall outside normal operational settings. It is possible to set the factor levels too far apart, which causes the factors to have nonlinear effects. This, in turn, causes the model to produce incorrect results, and this error increases as the levels are set further apart. A way to combat this challenge is to add a center point. Center points provide a standard reference around which you can perform further experimental runs. So if the response value at the center point is close to the response value during all other runs, you can assume the linear model is adequate. You can follow the rule that any factor's settings should fall within the middle 80% of the average working range. Most commonly, in manufacturing or operational processes, the low level is set at the current operating setting and the high level at a proposed improvement setting. For example, if a chocolate factory is running an experiment and the working range for chocolate melting is between 70 and 140 degrees Celsius, the factor settings can be expressed as 80 degrees Celsius for the low temperature level and 120 degrees Celsius as the high temperature level. The final element in Step 2 is determining the measurement method. Measurement system analysis is a vital process to be performed prior to conducting a DOE. By completing this analysis, you can be assured that your experimental conclusions are a sound basis for improvement decisions. You should consider a number of concepts in relation to measurement methods when planning DOE. Your first consideration is the capability of the measurement system. It must be capable of accurately measuring the factor and response variables chosen for the design. You should also consider the impact on results. All elements of measurement system correlation, including repeatability, reproducibility, bias, linearity, and stability, can impact the accuracy of DOE results. Next, consider replications and error. The number of replications used in an experiment has a relationship to the experimental error, making the number of replications an important consideration to be weighed against the practical considerations of cost and time. Correlation analysis and confidence intervals is your final consideration. Teams should analyze measurement correlation in light of a chosen confidence interval by sampling the outputs from the measurement system and estimating a range of values. When conducting DOE for optimization purposes, having a solid measurement strategy is key. You must ensure that your measurement method is easily adaptable and sensitive to changes in input variables related to the response you are examining. This sensitivity will aid in the accurate measurement of the factors and responses chosen in your design. You should note that measurement error can have a big impact on the results of your experiment, so it's vital to reduce error and account for any you can't eliminate. If the method or equipment you're using to measure the factor level's effect on the response variable fails to measure adequately, you'll be left with imprecise DOE results that are unreliable for drawing conclusions. For example, imagine you're conducting a study on a new machine being added to the packaging line at a cookie manufacturer. You're testing to determine if the new machine improves the production line process and packages the correct weight of cookies per box. Conducting a measurement system analysis before beginning an experiment will decrease error and pinpoint where your measurement methods should be improved. A comprehensive measurement system analysis will examine various elements of measurement correlation, including repeatability and reproducibility, bias, linearity, and stability. You should be able to analyze measurement correlation in light of chosen confidence intervals. The confidence interval for a measurement of an experimental variable gives an estimated range of values, which is likely to include the actual value for the variable. This interval is estimated by sampling the outputs from your measurement system. By defining the data based on the boundaries of confidence intervals, you can present clearer conclusions and make more precise statements about the response data. Replication and repetition allow an experiment to stay within defined limitations and still provide additional data without increasing sample size considerably. This goes hand in hand with practical considerations of keeping cost, time, and effort in check. You can determine the number of replications needed for an experiment to bring error down to an acceptable level. Along with the selection of appropriate responses, factors, and levels, the validation of a suitable measurement method completes the second step in the DOE process. Access the job aid DOE planning considerations and recommendations after the video to review a summary of the planning stage of DOE. Step 2 in the DOE process, select responses, factors, and a measurement method, is a key step in designing your experiment. When selecting responses, you should use a process map, avoid binary variables, identify responses that are functional requirements or design parameters, and identify measurable, quantitative responses. When selecting factors, it's recommended that you use the transfer function. Consider all factors judged to be important by those close to the process, and choose factors that can be varied or controlled. Once the factors are determined, you choose factor levels, considering whether to trade detail for cost efficiency or vice versa, and ensuring that you avoid selecting a range that is too large or too small. When determining the measurement method, you need to consider measurement system capability, impact on results, replications required, and correlation analysis. The first 3 steps of the DOE process constitute the planning stage. It's vital to complete Step 1 and Step 2 in order to lay the foundation for Step 3, choose the appropriate experimental design. With your goals outlined and response variable, factors, levels, and measurement method decided, you can then use this information to choose the most appropriate experimental design. When designing your experiment, choose the most fitting experimental elements as well as the design that will maximize both your research and process improvement. You should also choose a design based on the desired statistical goals and experimental costs. It's important for all parties involved to have input in this decision. You need to take into account the resources available and how much control you, as experimenter, will have over the experiment. Your design choice should leave room for unexpected additional runs, which are used to fix any correctable errors. You'll recall that the two most common experimental design types are full and fractional factorial designs. Full factorial designs are generally used when you have a small number of factors and levels, resulting in a small number of runs, or when there are more factors and cost and time are not an issue. Fractional factorial designs are typically used when the number of runs is large due to a larger number of factors and levels. You're still able to extract valuable information, but with fewer runs. When using the full factorial design, you examine every combination of every level of every factor, while with the fractional factorial design, you conduct a fraction of the runs of a full factorial. There are other experimental designs, but this course will focus on the differences between these two basic categories. In choosing the best experimental design, you must determine the number of runs required for the type of design. Generally, experiments can be represented as L raised to the power of k, where L is the number of levels and k is the number of factors. When you want to determine the number of runs in an experiment, you raise the number of levels, L, to the number of factors, k. For example, in an experiment with 2 levels and 2 factors, you calculate 2 raised to the power of 2, or 4 runs. If you have 2 levels and 3 factors, you calculate 2 raised to the power of 3, or 8 runs. For a full factorial design where every combination will be tested, the more factors you have, the more runs you must complete. In some cases, it's important to consider the number of runs in your experiment and how that will affect your budget and time constraints. When using a fractional factorial design, you focus on the main effects and some of the interactions of interest and select a subset of combinations to test instead of every combination. The fractional factorial design reduces the number of runs needed for an experiment to a fraction. You exclude one or more combinations by calculating L to the power of k minus p, where p represents the number of fractional reductions. For p equals 1, the design reduces to 1 fraction, which is known as a half-fractional design. For p equals 2, the design reduces to 2 fractions, which is known as a quarter fractional design, and so on. Consider these examples of how the number of runs are calculated. In a full factorial design with 2 levels, L equals 2, and 5 factors, k equals 5, you calculate a full factorial by 2 raised to the power of 5, which equals 32 runs. In an example with 2 levels, L equals 2, and 4 factors, k equals 4, if you want to determine the number of runs for a half-fractional, then p equals 1. You calculate 2 raised to the power of 4 minus 1, or 2 raised to the power of 3, which equals 8 runs, half of the full factorial 16 runs. You can generally follow the rule that when there are 4 or more factors, you should use a fractional instead of a full factorial. And finally, in an example with 2 levels and 6 factors, if you want to determine the number of runs for a quarter fractional, then p equals 2. You calculate 2 raised to the power of 6 minus 2, or 2 raised to the power of 4, which equals 16 runs, a quarter of the full factorial 64 runs. Fractional factorial designs, as they involve fewer runs, make a trade-off in terms of confounding some higher-order effects. As you may be aware, 3-factor and higher interactions are often considered unimportant relative to main effects and 2-factor interactions. When higher interactions are negligible and can be ignored, it's generally safe to sacrifice them to confounding. The experiment would require a smaller number of runs and can use the fractional factorial design. You can seek the advice of experts on the team to determine which interactions are negligible. Each type of experimental design has drawbacks and advantages that you should think about when choosing whether full factorial or fractional factorial is right for your experiment. Full factorial designs are comprehensive but cumbersome. While they require more runs and provide more data, they're also more costly and can require additional time and effort that you may not be able to afford. In contrast, fractional factorial designs can result in confounded factors, but are more economical and easier to conduct. They're effective for large numbers of levels and factors, as they can provide good estimates of main effects and interactions to compensate for less data. Fractional factorial designs are commonly used for screening since they reduce the number of runs to a manageable size. Consider this example. You're conducting a study on a drill speed's effect on precision. You've identified 5 factors, set each at 2 levels, high and low, and determined your measurement method. You calculate the required runs for a full factorial 2K experiment, or 2 raised to the power of 5, which equals 32 runs. Due to time and cost constraints, you decide to conduct a fractional factorial instead of a full factorial experiment. The number of factors remains at 5 with 2 levels each, and the measurement methods will not change. You calculate the required runs by reducing the fraction by 1, L to the power of k minus 1, giving 2 levels raised to the power of 5 factors minus 1, or 2 raised to the power of 4, which is 16 runs. This is a half-fractional factorial design. Within Six Sigma, and specifically DOE, the ability to choose either a full factorial or a fractional factorial design means you can always find the best experimental design for a particular situation. Knowing when to choose full over fractional, or vice versa, is a skill in itself. Your main goal as experimenter is to evaluate the consequences of each type of design and choose the one that provides the results you require within the limitations. An important tip is to build your experiments sequentially. This way, information you gain from one experiment can be used in future experiments. Typically, you carry out a screening experiment through a fractional factorial design to identify those factors that are most important. Then, you use either a full or fractional factorial to create your mathematical model of the process. Finally, you perform a validation experiment to confirm the results. Another important point is that if you use only a portion of your budget, for example 25% in the first DOE, you'll have room to make changes and fix mistakes in the next series. When it's vital to your results to test every combination of all input factors, then you must choose a full factorial design. But when it's not necessary to test every combination, and time, cost, and effort are limited, then fractional factorial design is best. A key consideration when choosing the experimental design is resolution level. As you know, 3-factor and higher interactions are deemed unimportant and can be ignored. If you identify a number of your interactions as 3-factor or higher, you won't need as many runs to assess the factors. Then you can go with a fractional factorial design and a highly desired resolution level of Roman numeral 5, in which the only confoundings that occur are between the main effect and 4-factor and 2-factor and 3-factor interactions. So when you ask the question, which design should you use, full or fractional, you must think about these considerations. A full factorial design is generally chosen when you require a very high resolution, Roman numeral 6, with no confounding, and can absorb the time and other resources to conduct many trials. A fractional factorial design is generally chosen when certain interaction effects are inconsequential enough to be ignored, when resources, time, or budget is in limited supply, when screening, or when taking advantage of the sparsity of effects principle, which states that the simplest model is the best. Consider an experiment to test frame strength in a new SUV with 7 factors, each with 2 levels. You decide you need to test all combinations as you expect there could be significant higher-order interactions, so it's required that you have a resolution level of Roman numeral 6 with no confounding. You recognize that expensive vehicles have to be damaged in the test, but also that you have unlimited resources of time and team members, so you choose a full factorial design with 128 runs. Then consider how things would change if you have the same experiment, 7 factors and 2 levels each, and you're conducting a screening test with a strict budget and the experiment will affect downtime. You also know that you don't need to test all combinations since you're reasonably confident that any higher interactions are negligible. Taking all of this into account, a resolution level Roman numeral 4 is desired. The best experimental design in this scenario is a fractional factorial design with 32 runs. The following example of choosing an experimental design illustrates the first 3 steps of the DOE process, the planning steps. You're working on a Six Sigma project at a plastic injection manufacturing company that manufactures syringes to be supplied to large hospitals. In step 1, you define the business problem and experimental goals. You want to optimize the injection molding process to minimize mold cracking in subsequent treatments and while in use in hospitals. Moving on to step 2, the response of interest is identified as the tensile strength of the mold, measured in PSI, since molds with higher tensile strength provide weight-optimized design and are less prone to cracking. You also identify 3 factors and the associated levels at this step: the temperature at which the plastic polymer is melted, the quantity of the polymer material injected into the molds, and the hardening time allowed between the chilling of the material and its ejection from the mold. 2 levels are determined for each factor, a low level and a high level, selected from each end of the middle 80% of normal operating range. Finally, you survey the information available to this point and choose the most appropriate experimental design. With 3 factors and 2 levels each, you know a full factorial will require 8 runs. You have a large budget and have already conducted a screening experiment to narrow down these 3 factors from 7. You want to be able to assess all interaction effects with no confounding and choose a full factorial design for this experiment. Access the job aid DOE planning considerations and recommendations after the video to review a summary of the planning stage of DOE. When using a full factorial design, you examine every combination of every level of every factor. With a fractional factorial design, you conduct a fraction of the runs of a full factorial. In choosing the most appropriate experimental design for a particular situation, you must consider the number of factors and levels, the resources available, and the resolution desired. Of the 2 types of design, full factorial experiments offer the highest resolution with no confounding, but will cost you more in time and resources. Fractional factorial designs are more cost-efficient, but require that you accept some confounding between effects. How can a Six Sigma team determine key factors, their effects, and their ideal settings in order to achieve a desired response? Properly planned, designed, and conducted experiments help black belts to understand the factors that affect output and to determine their ideal settings. The design of experiments, or DOE approach to collecting information, provides more reliable information than traditional one-factor-at-a-time experimentation, and the results of DOE are more easily analyzed and interpreted. Experiments are conducted to learn about the relationship between input factors and the output response. The goal is to optimize the response by determining the optimum levels of each of the factors impacting the output. Factors can then be set at those optimum levels so the desired response can be achieved. Experiments can study one factor at a time. These are sometimes referred to as one-fat experiments. Or you could study many factors simultaneously in designed experiments. You may use one-fat experiments when your process isn't complicated, but it usually is. One-fat designs don't reveal the interactions between factors or their combined impact on the response. So if you have more than one factor of interest or you're concerned about interaction effects, one-fat will omit valuable information about significant factors and their interactions. Applied to more complex situations, one-fat is a cumbersome, inefficient, and inadequate approach to experimentation. Factorial experiments are a type of designed experiment. These experiments are carefully planned to evaluate factors simultaneously in a way that allows you to identify their individual and combined effects on the output. Effective factorial design ensures the fewest number of runs are conducted, while generating the most information about how input factors affect output. Factorial experiments are commonly used in Six Sigma. DOE is a systematic method for planning, designing, and analyzing a factorial experiment. In factorial designs, you choose 2 or more factors to study at 2 or more levels each. Responses, the output variables, are measured for different factor and level combinations. Each complete trial or replication of the experiment tests all the possible combinations of the varying levels of these factors. This design helps you determine which factors have the biggest impact on the response and identify any interactions that exist between the factors. Factors, or input variables, can be discrete or continuous, and responses, or output variables, are usually continuous. There are various benefits of using factorial and DOE experiments over one-fat experiments. For instance, they allow you to undertake the simultaneous study of many factors, which is more economical and less disruptive. And they nullify uncontrollable or noise factors that have a big impact on the output by controlling other input factors. These experiments also give you insightful information without in-depth statistical knowledge. However, you can run statistical analysis on the results using computer programs. Other advantages are that factorial and DOE experiments allow you to study a process with relatively few experiments and distinguish important factors from the not-so-important ones so that you can concentrate your efforts on the important ones. You can also have confidence in the conclusions drawn due to their balanced designs. Factors can usually be set at the optimal levels for verification. Finally, you can determine when important factors have been overlooked. Experiments expressed using the notation L raised to the power of k, replacing L and k with the level and factor values respectively, you can determine the number of runs required for experiments. L denotes the number of levels each factor will be tested at, and k denotes the number of factors. For example, if each factor will be tested at 2 levels, replace L with 2. If 3 factors are being tested, replace k with 3. Expressed as a 2 raised to the power of 3 experiment, each of the 3 factors will be tested at 2 levels, resulting in 8 runs. 2 times 2 times 2 equals 8. Experiments with only 2 levels of each factor are common and will be the focus of this course. In some cases, 3 levels of each factor may be tested, making the experiment a 3 raised to the power of k design. Now, let's look at each type of experimental design to learn how many runs are associated with it. 2-level experiments with 2 to 8 factors will have between 4 and 256 runs, and 3-level experiments with 2 to 8 factors will have between 9 and 6,561 runs. In full factorial designs, an experiment is run for every factor-level combination. Doing this allows you to detect all interaction effects. That is, it reveals how the interactions between factors affect the output. Testing every factor-level combination and detecting all interactions means full factorial designs are tested at the highest possible resolution. And at this resolution, no effects are confounded. Also, for each run of the experiment, you can estimate an effect, which can be used to estimate uncertainty. Fractional factorial designs use fewer runs. Because of this, they save time, resources, and money, and still provide a good estimate of the significant factors and their combined effects. Also, it's important to note that fractional factorials don't consider high-level resolutions that aren't very significant. Considering the high cost of added experimental runs and the remote chance of learning anything of value, this is a desirable trade-off. Now, let's look at how fractional factorial designs differ from full factorial designs on 2 points. First, fractional factorial designs have fewer runs. While the full factorial experiment for this 2-level 3-factor design has 8 runs, the fractional factorial design may only have 4. A full factorial design will always have the full number of runs, calculated by raising the number of levels, L, to the power of the number of factors, K. Fractional factorial designs will have fewer number of runs than this. And second, because each factor level combination is tested in the full factorial design, there is no confounding. But notice how in a fractional factorial design, the product of factor A and B is the same as that for factor C. This is an example of confounding. You can't be sure which term is having the effect. The more effects that are confounded in an experimental design, the lower the resolution. You can conceptualize experimental runs in a two-level, two-factor, or three-factor experiment by plotting them as a square or cube, respectively. Each corner of the square represents a run in a two-level, two-factor design, and each corner of a cube represents a run in a two-level, three-factor design. Let's look at each corner of the square and cube to learn which factor level combination it represents. The A minus B minus corner of the square indicates that factor A is at its low level and factor B is also at its low level, while the A plus B plus corner of the square indicates that both factor A and factor B are at their high levels. The A minus B minus C plus corner of the cube represents the run where A is low, B is low, and C is high. And the A plus B plus C plus corner represents the run where A is high, B is high, and C is high. Now, consider how the runs would be plotted for a full factorial example of a potter trying to find the right combination to produce the desired effect in her finished pottery. It's a two-level, three-factor design, so it can be plotted using a cube with one factor on each axis: temperature, time, and glaze. The combination of a kiln set at 1,200 degrees Celsius fired for 8 hours using glaze type 1 is plotted at the back top right corner of the cube. A full factorial design is a good choice when a high resolution is desirable, mainly when you expect that significant higher order interaction effects are present. It's also a good choice when experiments require only a small number of runs and are therefore manageable. What's considered manageable will depend on the circumstances of the test. Generally, 8 or 16 runs are accepted as reasonable. The table of designs and resolutions for two-level designs indicates that the full factorial designs achieve the highest resolution possible. As such, there is no confounding in these designs because they're of the highest resolution. The table also shows the degrees of resolution for different fractional factorial designs. Consider this example. You're working with a team to improve the useful life of hydraulic fluid used in heavy equipment. Anova results indicate that maintenance and use have the greatest impact on the fluid's useful life. The team knows that these two factors are significant, as are their interaction effects on the hydraulic fluid. The team determines that each factor should be set at 2 levels for the experiment. Maintenance will be tested according to recommended maintenance, generically defined as high, and no maintenance, defined as low. Use will be tested at 24-hour operation, defined as the high level, and 8-hour day, defined as the low level. Knowing that interaction effects will be high between these factors, the team decides to use a 2 raised to the power of 2 full factorial design to learn about the combined effects. A systematic approach to experimentation, such as DOE, is typically preferred over one-fat experiments. This is partially attributed to the fact that DOE experiments are generally more reliable, easily analyzed, and easily interpreted. 2 types of DOE commonly used are full and fractional factorial designs. The main difference between the two is that full factorial designs test every factor-level combination, and fractional factorial designs don't. Because they test all factor-level combinations, full factorial designs detect all interaction effects. This means the highest resolution is achieved where no effects are confounded. Full factorial designs are a good choice when a high resolution is desirable and when experiments involve only a few factors and levels. Full factorial experiments are conducted using 6 steps and are a type of designed experiment. The steps in the design of experiments, or DOE process, are to define the DOE problem and experiment objectives, select responses, factors, levels, and measurement method, choose and create an appropriate design, conduct the experiment and collect samples, analyze data and find results, and verify predicted results. Step 1 of the DOE process is to define the DOE problem and experiment objectives. Typically, when conducting an experiment, you're looking to define a model, the equation that describes the response variable y. In this model, for a two-level, two-factor experiment, the betas represent the constant values in the model. While conducting the experiment, you learn about the impact each factor and each factor-level combination has on the output. Based on the impact demonstrated during the experiment, you'll take one of two actions: quantify the effect or remove it from the model. Let's have a look at what each action means for the model. If A, B, or their combined impact on the response is significant, you populate the model with numbers that quantify these effects. This allows you to make predictions about the impact on the response according to various input conditions. If any of the main effects or interactions are insignificant, you remove them from the model and analyze the reduced model again with fewer terms. If none of the main effects or interactions are significant, or you're left with very few significant terms, you'll select other potentially significant factors to test and run the experiments again. In DOE, considerable knowledge about significant main effects or interactions is often gained through failed experiments. Consider how this might be applied. A glass manufacturer makes glass sheets for residential and commercial building applications. Recent quality inspections have uncovered a number of defects. The manufacturer decides to bring its best technicians together to analyze the problem. They find that inconsistencies are increasing breakage during installation. The Six Sigma team is charged with conducting experiments to determine the optimum settings for the key inputs to ensure the defects are eliminated or reduced to acceptable levels. The team identifies that the key variable determining breakage is the glass's tensile strength, breaking strength. The tensile strength, measured in terms of stress and deflection behavior of glass sheets, is the most important feature and the key to price premium and customer satisfaction. The team also determines that two input variables affecting tensile strength the most are density and molten temperature. The team then plans to conduct a designed experiment to determine the effects of the input factors and interactions, if there are any. The goal is to build a model of the relationship between significant factors and interactions and the response variable. The team uses software to determine the factor settings that will optimize the response, tensile strength of the glass sheets. Step 2 of the DOE process is to select responses, factors, levels, and measurement method. In this step, you will choose measurable responses of interest and then determine all the relevant factors and levels that may have an impact on the response. Next, decide on the measurement method to use. Note that specific recommendations for how to select factors, responses, and measurement methods are covered elsewhere in the Black Belt curriculum. Recall the example where the team is working to improve tensile strength of glass sheets. Currently, the team is working to design the experiment. The experimental design matrix identifies the runs, factors, levels, replicates, and the response. The team understands that the two key factors affecting the tensile strength of the glass sheets are material density and molten temperature. Material density is measured as pounds per centimeter cubed. Molten temperature, measured in degrees Celsius, describes the temperature for melting the raw materials used in the manufacture of the glass. Now, let's look at how the team works through each component in Step 2. In this experiment, the response variable Y is tensile strength. It's measured in megapascals, 145.04 pounds force per square inch. The two factors to be studied for their impact on the response are factor A, material density, and factor B, molten temperature. The team chooses to test both factors at two levels. Material density is tested in pounds per cubic centimeter at a low level, 30, and a high level, 40. Molten temperature is tested at two levels, 2,100 and 2,600 degrees Celsius. Step 3 is where you plan and create the experimental design. When deciding whether to use a full factorial design, cost, and efficiency are the most important considerations. If higher-level interactions are suspected, resolution will be considered, but only after cost and efficiency. Full factorial design is a good choice when the experiment will require few runs. Generally, 8 to 16 runs are manageable. In the experiment to learn how to improve glass by improving tensile strength, team members determined that all interactions between factors were significant, so they designed a full factorial experiment. Taking into account replicates, the total number of runs is 16, a manageable amount. Let's look at two additional elements that complete the experimental design. First, runs. The notation L raised to the power of k, where L denotes the number of levels and k denotes the number of factors, is used to determine how many runs are required. In the 2 raised to the power of 2 full factorial design to improve the tensile strength of glass, 4 runs are necessary to test each factor and factor-level combination. Second, replicates. Because these are desirable, it's calculated that, with 4 replicates, the total number of runs will be 16. You'll learn more about replicates in later videos. The 3 R's are repetition, replication, and randomization. These considerations affect the total number of runs in an experiment and their experimental order. Repetition involves repeating single factor-level combinations, not the entire experiment, more than once in order to measure a response variable under similar conditions. Repetition provides measurements that you can use to estimate the inherent variability in the measurement system. Replication is the practice of resetting the factors and reconducting the experiment. In a replicate, the entire experiment must be redone, not just part of it. Replication helps to quantify experimental error by measuring the variation in your experiment. Because replicates provide a measure of experimental variability, Anova can be used to determine significance. The number of runs in a replicated experiment will be a multiple of the original number of runs. For example, 2 replicates in a 2 raised to the power of 3 experiment would give a total of 16 runs. This is calculated as the original 8 runs of the first replicate plus the 8 of the second replicate. Several considerations influence how many replicates will be chosen for an experimental design, including the cost, manageability, amount of variation expected in the experiment, and degree of precision expected from the experiment. If you're using software, it will recommend how many replicates to include. There are a few other guidelines you should be aware of when making your decision. First, if an experiment presents many opportunities for variation, and the precision of the experimental results is important, then more replicates will be desirable. However, many experimenters believe that experiments should have a minimum of 2 replications and shouldn't exceed 16 runs, or a maximum of 32 runs in total. Any more than 32 runs and the experiment could be unmanageable. Experimenters who plan to conduct expensive, destructive tests, like automobile crash tests, will want to minimize the number of runs while still providing for at least 2 replications. In these cases, a total of 8 or 16 runs may be more feasible. The final R is randomization. To explore it, consider an experiment conducted in a manufacturing plant. The experiment has been split across day and night shifts. A nuisance variable, humidity, is impacting the response for each run. Humidity present during the day and the lack of humidity at night is reflected in the responses. The responses align with the humidity levels present when the runs were conducted, but humidity is not one of the factors being tested. This leaves the question, how can randomization improve the experimental design? You can randomize the order of test runs to spread out the variation caused by nuisance variables. Essentially, randomization prevents experimenters from unwittingly introducing causal patterns through bias or timing, and gives each item a fair and equal chance of being subjected to a given treatment. This helps to produce treatment groups that only include variation that's of primary interest to experimenters, not variation caused by nuisance variables. A good rule of thumb is to randomize as much as possible. This is especially important if the experiment will be conducted over time. And if the measurement process is done separately from the experiment, test results should also be measured in a random order. Consider how the 3 R's are used in the experiment to improve the tensile strength of glass. To help quantify experimental error, replicates are added as successive and exact runs of the original 4 that make up the designed experiment. Repetition is used to estimate the standard deviation of the process by testing the strength of 4 panes of glass under the factor level combination represented by run 3. Finally, the runs are randomized. This will help minimize the effect of variation from noise factors. Now, return to the previous example. As the team defines the runs, they're put in standard order. Later, the runs are randomized, typically using software or a random number generator. Let's look at each order type to learn how they differ. In this matrix, the standard order and the run order are the same. Factor A, material density, is listed at both its low and high level, and factor B, molten temperature, is held constant at its low level. Then the low and high levels of factor A are listed, and factor B is held at its high level. Each replicate maintains this order and creates a repeating pattern. Before the experiment begins, the order in which the runs will be executed needs to be randomized to minimize any variations caused by the noise factors. The standard order column remains sequential. The randomized order, which will be followed during the experiment, is identified in the run order column. Typically, only the run order column is referenced during the experiment. Both columns are shown here to illustrate how the standard order is randomized to get the run order. In this case, for the first run, the factors will be set as per the original standard order number 14. The second run to be tested will be as per run 3 in the standard order, and so on. For simplicity, most software outputs will then rearrange the table so that the run order is sequential from top to bottom, and the standard order numbers appear scrambled. Recall the team working to control the nuisance variable humidity in its manufacturing plant. The team randomized the experiment to spread the variation due to humidity randomly through the experiment. The responses no longer align with the humidity levels present when the runs were conducted. The team can now obtain a better estimate of the effects of the factors being tested. The fourth step in the DOE process is to conduct the experiment and collect samples. You conduct the experiment by applying each run in a lab or at a test facility. As you measure and record the response for each run, you'll notice that the responses for replicates differ slightly, despite having the same factor level settings. Replicates are used to estimate the variance in response caused by the slightest difference in experimental conditions. In step 4, the team working to improve the tensile strength of glass completed the experiment based on the full factorial design it created. The experiment was conducted by setting the density and temperature levels at high or low for each run, and measuring the force applied to break each glass sheet. As each run was applied, the force required to break each sheet was measured and recorded in the final column of the matrix, tensile strength. Analyze data and find results, and verify predicted results are the final steps of the DOE process. These steps will be discussed in later videos. Full factorial experiments follow the DOE process to design, conduct, and analyze experiments. These experiments test the impact of each factor level combination on output at all factor level combinations. The goal is to find the optimal factor level combinations that will achieve the desired output. Randomization helps to overcome the impact of nuisance variables on the responses. Replication helps to quantify experimental error by resetting the experiment and doing it again. And repetition helps estimate the inherent variability in the measurements. How does DOE help you with the improvement process? It helps you to analyze key factors through experimentation, which helps you to learn about their impacts and determine their optimum settings. Then, if possible, you can adjust the input factors to optimum levels that will achieve the desired output. A glass manufacturer wants to improve the tensile strength of the glass sheets it produces. The Six Sigma team has already completed the first 4 steps of the DOE process. In step 1, the team defines the DOE problem and experiment objectives. The glass manufacturer makes glass sheets with polyvinyl butyrol PVB interlayer for residential and commercial building applications, including skylights, atriums, partitions, curtain walls, doors, and roofs. The Six Sigma team decided to conduct experiments to determine optimum settings for the key inputs of the process for making the glass to ensure the desired quality is achieved. The team determined that the key variables for assessing the quality of glass sheets are its tensile strength, breaking strength, density, and heat-bearing capacity. Out of these, the tensile strength, measured in terms of stress and deflection behavior of glass sheets, is the most important feature and the key to price premium and customer satisfaction. Next, the team agreed that the two key inputs affecting the tensile strength of the glass sheets are molten glass density and molten temperature. Molten glass density is measured as pounds per centimeter cubed. Molten temperature, measured in degrees Celsius, describes the temperature for melting the raw materials used in the manufacture of the glass. In Step 2, the team selects responses, factors, levels, and the measurement method. As they worked to design the experiment, they first selected tensile strength, measured in megapascals, 145.04 pounds force per square inch, as the response variable to improve. The two factors studied for their impact on the response were material density and molten temperature. Both factors were tested at two levels. Material density was tested at its low level, 30 pounds per cubic centimeter, and its high level, 40 pounds per cubic centimeter. Molten temperature was tested at 2,100 degrees Celsius and 2,600 degrees Celsius, representing two levels, low and high, for the factor. The team used the notation L raised to the power of k, where L denotes the number of levels and k denotes the number of factors, to determine how many runs were required. For a 2 raised to the power of 2 full factorial design, the team concluded that 4 runs would be necessary to test each factor and factor-level combination. The third step is to choose and create an appropriate design. Because the team believed that higher-level interactions were significant, they designed a full factorial experiment. The total number of runs, taking into account replicates, is 16. The number of factors and levels tested in the experiment are very few, and even with the desired replicates, the total runs are within manageable limits. Considering the cost, manageability, and high-resolution requirements of the experiment, the team decided to go for a full factorial design with 4 replicates. Step 4 is to conduct the experiment and collect samples. The team completed the runs in the experiment, and as each run was applied, the response was measured and recorded. Based on the full factorial design, the team conducted the experiment by setting the density and temperature levels at high or low for each run, and measured the force applied to break each glass sheet in the experiment. This force was recorded as the breaking strength for each sheet and the data from each run stored in a table. Now, the team is ready to analyze the results of the experiment and complete steps 5 and 6 of the DOE process. During the first 4 steps of the experiment, the team used a matrix to help design the experiment and record the results of each run. Analysis and interpretation of the results involves several actions, which are typically performed by statistical software. This is the 5th step of the DOE process: analyze data and find results. The first thing to do in Step 5 is calculate estimates for main effects, either manually or using statistical software. Main effects, estimates of the effect of a factor independent of any other factors, are calculated one factor at a time. In a full factorial experiment, the relevant statistical effects are determined per factor. You compare the results from all the runs with the high level of a factor to the results of all the runs with the low level for that same factor. This is evident in the experimental design matrix to improve tensile strength of glass. Let's consider an example. To manually calculate the main effect for temperature in an experiment to improve a race car's speed, the team adds all the responses where temperature was set to its high level. Then it subtracts the sum of the responses where temperature is set at its low level. Now, the team divides by the number of responses at each level, in this case 4. The resulting value of -3.75 indicates that when temperature is at its high level rather than its low level, there's a loss in the response variable speed. Calculating main effects doesn't lead to an absolute result. You calculate main effects to compare them and gain information about trends. More specifically, calculating main effects tells you two things. First, which main effect has the biggest impact on the response variable? The higher the main effect's calculated value, the bigger its impact, regardless of whether the value is positive or negative. And second, whether the relationship between the factor-level combination and the response is positive or negative. The glass manufacturer's team manually calculates the main effects for the factors in the experiment to optimize the tensile strength of the glass. Let's look at each factor for an explanation of how estimates are calculated. To determine the effect of material density, you add together the 8 responses when material density is high and add together the 8 responses when material density is low. Then, you subtract the sum of the low responses from the sum of the high responses. When you divide by the number of responses at each level, you get a value of 12.1. So, when the material density is set at high rather than low, the yield is a gain in tensile strength. To determine the effect of molten temperature, you add together the 8 responses when molten temperature is high and add together the 8 responses when molten temperature is low. Then, you subtract the sum of the low responses from the sum of the high responses. When you divide by the number of responses at each level, you get a value of negative 12.6. This means that when molten temperature is set at its high level instead of its low level, tensile strength weakens. In this experiment, the team finds that numerically, disregarding the negative sign, the molten temperature effect is greater than the material density effect. Interactions, or interaction effects, between factors can hide the true impact a factor has on a response. If a factor's level changes and this changes the effect of other factors, interactions are present. In the 2 raised to the power of 2 experiment being conducted to test the impact of material density and molten temperature on the tensile strength of glass, there are 2 main effects and 1 two-way interaction. After calculating the main effects for each factor, the team is interested in the interactions between factors. To determine the interaction effect of combined factors, team members need to know the factor's combined level, which they find by multiplying levels. For instance, they multiply the material density level, which is high, by the molten temperature level, which is low. This results in a low level for run 1. For run 7, they multiply material density, which is low, by molten temperature, which is also low, and finds the combined level is high. Now, the team can estimate the effects of interactions. In this case, only one two-way interaction exists. Using the same calculation method for estimating main effects, the team finds the interaction between material density and molten temperature is equal to negative 1.85, which results in a decrease in tensile strength. While effects plots can be created manually using the same values calculated for main effects, software is typically used. Let's look at each plot type to review the main and interaction effects plots for the glass manufacturer's experiment. The plot of the main effects represents the effects as sloping lines. The numerical effect corresponds to the rise of the slope. The upward sloping line for material density signifies a positive effect, and the downward sloping line for molten temperature signifies a negative effect. As noted earlier, the effect for molten temperature is slightly larger at negative 12.6 than the effect for material density at 12.1. A greater difference between effects would result in a more noticeable difference in the slopes. The plot of interaction effects confirms that the interaction between the 2 factors doesn't have a significant effect on tensile strength. You can tell this because the plotted lines are nearly parallel. Once the main and interaction effects are calculated, the team can begin to analyze the relationship between the factors and the response, using the calculated values for each effect and its charts. If effects are calculated manually, although not typical, it's not possible to know which effects are statistically significant. When you use software to analyze your results, the software will typically calculate and graph the main and interaction effects. It will then determine statistical significance, create a model equation, and identify the settings of factor levels that will optimize the output. You can use software to test the statistical significance of main and interaction effects and determine a model equation representing their relationship with the response. This is a key objective of Step 5, analyzing the data and finding the results of the experiment. DOE software typically provides several outputs that you can use to analyze the significance and meaning of effects observed in your experiment. First, you can use a table of estimated effects and coefficients, which reports the statistical significance of each effect as a p-value and also gives coefficients for the model. You can also use a Pareto chart, which provides a visual summary of the relative significance of each main and interaction effect. Finally, an Anova table, which summarizes the significance of main and interaction effects. The table of estimated effects and coefficients provides an estimate of main and interaction effects similar to those that would be obtained through a manual calculation, as demonstrated earlier. In the example given, only the relevant columns are included, without the coefficient column. It also provides a p-value for each of the calculated effects. Some of the main or interaction effects may not be statistically significant, and if so, they should be removed from the model. Significance is determined by examining the p-values returned in the software outputs. You can visually assess which factors are most significant by examining a Pareto chart. It indicates what proportion of variance each factor accounts for. Any bar that extends beyond a certain significance level indicates a significant effect. The Pareto chart for the experiment to improve tensile strength of glass sheets shows that the main effects of material density and molten temperature are significant, as both bars extend beyond the 5% significance level of 2.179. Again, the interaction effect of the two factors is shown to be insignificant. The effects table reveals which effects are significant enough for inclusion in the model. In the glass manufacturer's experiment, the interaction effect material density multiplied by molten temperature has a p-value greater than 0.05 and therefore isn't significant. However, the main effects are significant as they have a p-value less than 0.05. Another way to verify the significance of effects is through analysis of variance, or Anova. Anova results for the experiment also reveal that the interaction effect isn't significant, while the main effects are. The model equation for the experiment is derived from the estimated coefficients returned by the software. The coefficient values in the partial estimated effects and coefficient table are used for determining the model equation for the experiment to improve tensile strength. The team adds the coefficients for the constant, material density, and molten temperature to the model. Because the interaction effect of material density and molten temperature isn't significant, it isn't included. The model will help you optimize the output, the response variable, by suggesting the optimum levels to set the factors at to achieve the desired response. Software often provides the values that represent optimum levels. For any experiment, it's advisable that you check the assumptions that must hold true for the model to be valid. You do this using residuals analysis. By checking that residuals are independent, that error is normally distributed, and that variance is constant. It's possible, even probable, that none of the effects will be significant, and they'll all be removed from the model. If this happens, you'll choose new factors or new levels of the same factors to test. Because DOE is iterative, you'll likely run several screening experiments before you're able to identify the significant factors affecting the response. As you do, add them to the model, further refining it in pursuit of the ideal settings to achieve the desired response. Optimization will only be achieved after several iterations of DOE. The team working to improve tensile strength has completed one experiment. This round of DOE identified two factors with a significant effect on the response. Knowing that more are likely, the team continues to design and run additional experiments to screen for other factors such as input materials used, annihilation time, and thickness of the glass sheets. As it does, the team moves closer to a model including all significant factors, which will allow it to determine the levels to set the factors at to achieve the optimum response. Step 6, Verify predicted results, is the final step of the DOE process. Verification is a lengthy process of checking that the improvements implemented as a result of DOE conclusions are still holding or having the desired effect. This is done in the field and on the floor, as the day-to-day activities of the process are performed. Verification can continue over weeks or even months and will depend on the nature of the process being improved. After you conduct your experiment, you perform steps 5 and 6 of the DOE process. The key objective of step 5, analyze data and find results, is to test the statistical significance of effects and determine a model equation to show their relationship with the response. You can use tables of estimated effects and coefficients, Pareto charts, and Anova tables to analyze the significance and meaning of effects. This allows you to refine and optimize the model equation. In step 6, verify predicted results, you check that the actions you took to improve the process are having the desired effect. You do this by observing the working process. Based on what you learn, you may perform more experiments in pursuit of continuous. When you're trying to learn about something, it's difficult and often unrealistic to study each member of a population. But by carefully selecting a subset of the population, reliable estimates of the whole can be obtained while saving time, money, and resources. Design of experiments, commonly referred to as DOE, offers a design for this, the fractional factorial design. Recall that full factorial designs study the effect of each factor and every interaction between them. An example is the 2 raised to the power of 5 full factorial design. In a fractional factorial design, runs are selected from the full factorial design in such a way that the effects of all factors and some interaction effects can still be estimated. Generally, the higher-order interactions, 3-way and higher, are assumed to have a negligible effect, rendering them insignificant and unnecessary to estimate. Now, let's look at the characteristics of full factorial designs to learn how fractional factorial designs differ from them. First, full factorial designs include at least one run for every factor-level combination. In fractional factorial designs, fewer runs are used, but if the design is balanced, results can be extrapolated for the removed runs. For any experiment to remain manageable, it's recommended that you limit the number of runs to 16 or 32 maximum. For a 2 raised to the power of k design, this means you can only test 5 factors, resulting in 32 runs. Because fractional factorial designs don't test every factor-level combination, it's possible to test more factors and have the experiment be manageable. For instance, a half-fractional design testing 5 factors at 2 levels only requires 16 runs. Lastly, a full factorial design tests all factors and interactions, whereas a fractional factorial design allows higher-order interactions to be confounded because they are presumed negligible. This allows you to conduct fewer runs and focus only on main effects and lower-order interactions, which are likely to be most significant. You can conceptualize a balanced design using a cube, where each corner of the cube represents a run in the experiment. Typically, software is used to select the runs to remove and still maintain a balanced fractional factorial design. Take, for example, a 2 raised to the power of 3 design. If you remove 4 out of 8 runs in a balanced fashion, you get a half-fractional factorial design. The results obtained from a fractional factorial experiment will be similar to the results from a full factorial experiment if the fractional experiment contains the appropriate number of runs and is suitably balanced. Consider this example. A federal health agency wants to improve the effectiveness of its advertising message. Let's look at each design and table to review the results of the experiment run as a full and as a fractional factorial design. The full factorial design has 16 randomized runs in total. The fractional factorial design, or fractional factorial, has 8 randomized runs in total. The full and fractional results tables return similar values for the main and interaction effects. And the p-values for both experiments run using full and fractional factorial Anova tables are quite similar. Circumstances suitable for using a fractional factorial design are threefold. When all three of these circumstances are present, a fractional design is appropriate. First, when an accurate study of the significant main effects and interactions can be achieved without testing all factor-level combinations. Next, a fraction design is also suitable when there's a large number of input factors and levels, making a full factorial design overly cumbersome. And you would use a fractional design when constraints of resources, time, and effort make a full factorial design infeasible. The first circumstance to establish is whether an accurate test of the main effects and interactions can be achieved without testing all factor-level combinations. Fractional factorial designs focus on detecting main effects and lower-order interaction effects. It's here that you'll find the effects with the greatest impact on the response variable. Higher-order three-way interactions or greater are usually insignificant, so a fraction of the full design can be run, sacrificing the study of higher-order interactions. Because of this, some degree of confounding is always present in fractional designs. One desirable advantage of fractional designs is they involve fewer runs and place less strain on resources. In other words, testing L raised to the power of k runs, for example, can cost twice as much as testing L raised to the power of k minus 1 runs. Consider an example of how a full factorial design may not be necessary. Let's look at each aspect, required runs, and estimated effects to learn about what's involved in a 2 raised to the power of 5 full factorial design. A full factorial design for 5 factors requires 32 runs. Of the 32 runs, 31 terms are estimated. 1 run is the intercept. Of these terms, 16 are higher-order effects. So, in the case of the 2 raised to the power of 5 design, conducting so many runs to investigate all interaction effects isn't worth it, because most of the effects will be negligible or insignificant. If a large number of factors and levels would make a full factorial design overly cumbersome, you may want to use a carefully planned fractional factorial design instead. Generally, if the number of input factors is 5 or greater, a fractional design is a better choice. Access the job aid Runs Needed per Factor after this video to review the required number of runs. Finally, if the constraints of resources, time, and effort make a full factorial design infeasible, even if the number of runs isn't excessive, you may want to use a fractional factorial design instead. Experimentation is iterative, so efficiently using your limited resources, time, and effort will allow for more experiments and conceivably greater improvement. The notation 2 subscript r superscript k minus p is used to describe 2-level fractional factorial designs. Let's look at each component of the fractional factorial notation to learn what it represents. The letter k identifies the number of factors to be tested, while p represents the number of generators. R indicates the resolution of the design. This is usually written as a Roman numeral. 2 raised to the power of k minus p communicates the number of runs required and defines the base factorial design. The component 2 raised to the power of negative p indicates the fraction of the design that is being conducted. For instance, 2 raised to the power of negative 1 indicates that half as many runs are being completed as are required for a full factorial design. When p is equal to 1, then 2 raised to the power of negative 1 is the reciprocal of 2, giving 1 over 2, or a half fractional design. Similarly, when p is equal to 2, then 2 raised to the power of negative 2 is 1 over 4, yielding a quarter fractional design. A table containing design and resolution information can help you understand what various full factorial 2 raised to the power of k designs and fractional factorial 2 raised to the power of k minus p designs involve. Specifically, the table indicates how many runs are required and what resolution level should replace the subscript r. A design with 16 runs can be a 2 raised to the power of k design where k is 4, or it can be a 2 raised to the power of k minus p design where k is 5, 6, 7, or 8, and p is 1, 2, 3, or 4, respectively. As the number of factors being tested increases for a given number of runs, the resolution of the design decreases. Each fractional factorial design provides a specific resolution. So, when you choose a design, you need to consider whether the resolution will provide the information about interaction effects that you need. Resolution is a measure that defines the extent to which interactions are confounded with other interactions or main effects. 3 resolution levels are most important in 2 raised to the power of k and 2 raised to the power of k minus p design: Resolution 3, Resolution 4, and Resolution 5. Adding interactions and main effects is a quick and reliable way to determine whether they confound at a particular resolution. If the sum of the factors in the main effects and interactions equals the resolution number, they confound. If the sum is less or more than the resolution, the effects aren't confounded. For example, say you're considering a Resolution 3 design. A main effect involves 1 factor, and 2-way interactions involve 2 factors, giving a total of 3 factors. So these effects are confounded in a Resolution 3 design. Now, what about Resolution 4 designs? The number of factors in the main effects and 3-way interactions add up to 4. This tells you that main effects and 3-way interactions are confounded, as are 2-way interactions, because 2 plus 2 equals 4. What about main effects and 2-way interactions? 1 plus 2 equals 3, so main effects and 2-way interactions aren't confounded with each other. Now let's look at each resolution to learn which interactions and effects are confounded when it's used. A Resolution 3 design confounds main effects and 2-way interactions. Because 2-way interactions are usually significant, this isn't typically a good choice. With 2-way interactions confounded with main effects, you won't know what is actually generating the effect. Resolution 3 designs can be used to screen significant main effects from a large number of factors in a small number of runs. Subsequent experiments can further investigate the main effects of those significant factors and any interaction effects between them. In a Resolution 4 design, 2-way interactions are confounded with other 2-way interactions, and main effects are confounded with 3-way interactions. Resolution 5 designs confound 2-way interactions with 3-way interactions, and 4-way interactions are confounded with main effects. Typically, neither of these confounds are worrisome because higher-order interactions are unlikely to be significant. Resolution 5 and higher designs are the most desirable because they don't confound the interactions that are most likely to be significant: main effects with other main effects, or main effects with 2-way interactions. As the number of factors increases and the number of runs remains constant, you sacrifice more interactions to confounding. For instance, in quarter, 8th, and 16th fractional designs assessing 5, 6, or 7 factors in 8 runs, there's a greater trade-off for the convenience of 8 runs. As the resolution declines, all the additional factors are confounded with 2-way and lower-order interactions. If you choose these designs, you must be confident that these interactions are negligible. Like the full factorial design, you can conduct a fractional factorial experiment using the steps of the DOE process. Consider a national nonprofit organization that wants to increase donations by improving the effectiveness of its advertisements. The organization has just received 2 advertisements from its agency and needs to determine how these advertisements might be improved to help generate more donations. A team sets to work exploring and analyzing the advertisements using the DOE process. Let's look at how the team progresses through the first 2 steps of the DOE process. In Step 1, define the DOE problem and experiment objectives. The team defines the problem as insufficient funds to run all the programs the organization is committed to. The objective of the experiment is to determine which combination of factors is most effective at getting people to donate money. Step 2 is to select responses, factors, levels, and the measurement method. So the team sets advertisement effectiveness, measured as donations in millions, as the response variable, then carefully considers the factors that may have the desired effect of increasing donations. Factors to be studied are the type of advertisement, duration, definition, background music, and brand display. All factors will be tested at 2 levels, with each level set to high or low. The team has 5 factors and a limited budget, So as they begin step 3, they decide to create and conduct a half-fractional factorial design instead of a full factorial design. Planning 16 runs will help make the best use of limited resources and will allow for a replicate. A Resolution 5 design can study 5 factors in 16 runs in a 2 raised to the power of 5 minus 1 design, which allows the team to study the relationship between main effects and two-way interactions and how they impact the advertisement's effectiveness. Because these are likely to be the significant effects, the team will still be able to gain a good estimate of the effects. You can access the job aid Designs and Resolutions for 2-level experiments after the video to review the designs of full and fractional factorial experiments. Replicates are planned to help quantify experimental error, and when the experiment is conducted, it will be randomized to nullify the effects of noise variables. After it conducts the experiment, the team plans to check for repetition in the outputs to help estimate standard deviation. A 2 raised to the power of 5 minus 1 half-fractional design tests 5 factors in 16 runs instead of the 32 runs required for a 2 raised to the power of 5 design. In a Resolution 5 design, one main effect is replaced with a confounded term of that factor and the 4-way interaction of the other 4 factors. By choosing a half-fractional design, the team that wants to increase donations is essentially replacing interaction ABCD with a test factor E, brand display. The team will do this by confounding factor E with the 4-way interaction. Let's look at each task to learn more about factor E and the design matrix. Because 3-way and higher-order interactions are generally assumed to be negligible, combining 4-way interactions with factor E still allows the team to determine the significance of factor E. If these terms turn out to be significant, the team can be fairly confident it's factor E that's causing the response. The team can also determine confounding. Factor E is confounded with the 4-way interaction ABCD. And the team can review the design matrix for the experiment to test advertisement effectiveness. Here it shows the factor levels for all 16 runs. Now the team is ready to complete Step 4, conduct the experiment and collect samples. The team takes the design to the lab and conducts the experiment. As the runs are completed, the results are recorded in the Advertisement Effectiveness Measured as Donations in Millions column. Fractional factorial designs help you learn how to achieve improvement in fewer runs than a full design. However, because confounding is present in all fractional designs, you must choose a design that will minimize the impact of confounding in your experiments. The resolution of a fractional design tells you which effects will be confounded. Resolution 3 designs are least desirable because they confound the effects that are likely to be significant, main effects, and two-way interactions. Resolution 5 and higher designs are most desirable because, while confounding is present, their impact is typically agreed to be negligible. Fractional designs are generally a good choice when 3 circumstances are present: when accurate estimates of the main effects and their interactions can be achieved without testing all factor-level combinations, when a large number of input factors and levels would make a full factorial design overly cumbersome, and when the constraints of resources, time, and effort make a full factorial design infeasible. Consider this scenario. A Six Sigma team at a national nonprofit organization is working to improve advertisement effectiveness, measured as increases in donations. The team has received 2 advertisements from its agency and needs to determine how they might be improved to help generate more donations. The team sets to work exploring and analyzing the advertisements using the DOE process. Let's examine the steps that the team has already taken. In Step 1, the team defines the DOE problem as insufficient funds to run all the programs it's committed to, and defines the objective of the experiment as determining which advertisement is most effective at getting people to donate money. In Step 2, the team selects responses, factors, levels, and the measurement method. Advertisement effectiveness, measured as donations in millions, is set as the response variable. Then, team members carefully consider the factors that will tell them the most about the desired output of increasing charitable donations. Factors to be studied in the experiment are the type, duration, definition, background music, and brand display. All factors will be tested at 2 levels, with each level being assigned either the high or low designation. As the team begins Step 3, choosing and creating an appropriate design, it decides to create and conduct a half-fractional factorial design instead of a full factorial design. The experiment will be a Resolution 5 design, testing 5 factors in 16 runs with 1 replicate. This will help make the best use of limited resources and will allow for a replicate. By choosing a Resolution 5 design, the team can study the relationship between main effects and two-way interactions, and how they impact the advertisement's effectiveness. Because these are likely to be the significant effects, the team will still be able to gain a good estimate of the effects. Next, in Step 4, conduct the experiment and collect samples. The experiment is randomized to nullify the effects of any noise variables that may be present. The team takes the designed experiment to the lab and conducts the experiment. As the runs are completed, the results are recorded in the Advertisement Effectiveness column. As the team conducted the experiment, in Step 4, response values for each run were added to the matrix. Specifically, they were added to the Advertisement Effectiveness measured as donations in millions column. Recall that this matrix was used to design and conduct the experiment. The team will use this information to perform Step 5. Analyzing fractional factorial experiments follows the same procedure as analyzing full factorial experiments. You complete 2 tasks in Step 5. Calculate main and interaction effects, and construct a model. And in Step 6, you verify that the improvements are still having the desired effect on the response variable. Let's look at each task in more detail. You can calculate main and interaction effects manually or using software. Effects are calculated by adding all the responses for the factor at its high level and subtracting the sum of the responses for the same factor at its low level. Then, to determine the effect, the result is divided by the number of response values at each level. With the effects calculated, you can construct the model equation. Coefficients supplied by your statistical software are entered into the model, describing the relationship between the factors and the response. If you calculate effects manually, you won't yet know which effects are statistically significant, and therefore the model will contain all the effects. Like full factorial designs, calculating effects for fractional factorial designs helps you estimate the model. But in fractional designs, many of the interaction effects are confounded, and confounded effects can't be estimated. Hence, confounded effects aren't included in the model. Because confounding is always present in fractional designs, you need to proceed cautiously. Carefully consider the impact confounding may be having on your results. Now, let's look at some tips on how to reach appropriate conclusions when confounding is present. First, consider the coefficient combinations. When assessing a coefficient for 2 or more confounded effects, consider how the coefficients of individual effects might combine to present misleading information. For instance, several small, insignificant values may add up to a large combined value that appears significant. Or 2 large significant values may cancel each other out if they have opposite signs, like -4 and 5, giving a result that appears insignificant. In each case, if taken at face value, you may reach the wrong conclusion about the results of your experiment. It's also helpful to accept best guesses. Because results aren't always what they seem, accepting best guesses based on the data is common. For instance, say you're considering the confounded effect of an interaction between 2 significant factors and an interaction between 2 insignificant factors. A proper assumption is that the interaction effect of the 2 significant factors is the dominant interaction and accounts for the greater share of the confounded effect. If your assumptions are wrong, model checking will reveal relatively large values or unexpected structured variation. Finally, don't underestimate interaction effects. While main effects tend to be most significant, and 2-factor interactions tend to be more significant than 3-way interactions and so on, don't underestimate interaction effects. Higher-order interactions aren't always insignificant and shouldn't be dismissed without consideration. Like main effects, interaction effects might or might not be significant. But because higher-order interactions are typically negligible, more attention is given to main and lower-order interaction effects during analysis. Generally, p-values are used to determine whether interaction effects are statistically significant. Interaction effects with a p-value less than 0.05 are considered significant. Any coefficients with a p-value greater than 0.05 are removed from the model. Just like full factorial experiments, p-values for determining statistical significance are typically provided by the software you are using in your fractional factorial experiment. Other common sources for determining statistical significance are the Anova table and Pareto chart. Let's look at each source to learn how p-values are provided. Anova tables report the p-values for main effects and interactions. If a term's bar extends beyond the 5% significance line in a Pareto chart, its effect is significant. The significance of calculated effects must be validated and verified using Anova, regression analysis, or another statistical test. Experiments are usually iterative, especially if the initial experiment was a screening experiment. Subsequent experiments further elucidate the effects of factors. Fractional factorial designs are well suited to the iterative approach because they minimize the number of runs and therefore minimize the resources required. But still, their conclusions point you in the right direction for further experimentation. Based on what you learn from the p-values, you can reduce the model. And once you check any assumptions made using residual plots, you can use the model to gain a better understanding of the effects and determine which factor settings will optimize the response. An interaction effect between two factors exists when the effect of one factor on the response depends upon the presence of another factor. Interaction effects add complexity to your model, so it's important to understand interaction effects when analyzing any experiment where interactions are present, either full or fractional factorial. For that reason, it's worth spending some time exploring what interaction plots reveal. Interaction plots graphically display the effects of interactions. The y-axis shows the response, the x-axis shows the levels of one factor, and plotted lines represent the levels of the other factor. Say you have two factors at 2 levels each. Plot factor A on the x-axis and factor B using 2 lines. First, you plot both of factor A's levels when factor B is constant at one level, say high. Next, you plot both of factor A's levels when factor B is constant at its other level, low. When all points are plotted, you can assess the interaction between the factors. Consider the example of the team looking to improve advertisement effectiveness. The interaction plot describes the interaction between brand display and advertisement type. Advertisement effectiveness, measured as donations, is shown on the vertical axis. Let's look at how the team interprets the interaction plot. Because the two lines are significantly non-parallel, the team knows there's an interaction between the factors. When using theme B, the advertisement's effectiveness is similar at the low and high brand displays. With theme A, advertisement effectiveness is lower when brand display is at its low level, but it's still higher than B's responses at both brand display levels. However, the combination of theme A and a display time of 5 seconds shows a dramatic improvement in advertisement effectiveness. This indicates a substantial interaction effect. Let's consider another example. A Six Sigma team working to improve the precision of a machining process has plotted two factors, metal type and speed, on an interaction plot. Metal type 1 results in higher precision than metal type 2 at the high speed. In comparison, metal 2 works much better than metal 1 at the low speed. The team concludes that there's a significant interaction between these factors because the response for the levels of metal type depends on the level settings of speed. This is demonstrated by the crossing of the lines. Metal 2 at the low speed yields the highest precision measure, so this combination will be recommended. Consider this example. An experiment to improve road test scores has been completed, and the results for two factors have been plotted on an interaction plot. The team can tell from the plot that when the level of both factors is low, road test scores are worse than when both factors are high. Because the lines are parallel, the team knows that there's no interaction between the two factors. The biggest improvement is achieved when both factors are set to their high levels. So, 60 hours of instructor training yields the biggest improvement to road test scores. In the advertisement effectiveness experiment, a brand display of 5 seconds using theme A yields the best response. At this factor-level combination, advertisement effectiveness almost reaches $10 million. Step 6, Verify Predicted Results, is the last step of the DOE process. Verification can be a lengthy process. Now that the improvements have been implemented, you must check to make sure they're having the desired effect. Verification is done by observing the actual process as it normally happens on the floor in the day-to-day activities of the process. This step can span weeks or months, depending on the nature of the process. You analyze the results of fractional factorial experiments using the same process and methods used to analyze full factorial experiments. However, because confounding is always present in fractional factorial designs, you must carefully consider its impact. Follow these tips when studying the impact of confounding. Consider coefficient combinations, accept best guesses, and don't underestimate interaction effects. You can use an interaction plot to graphically assess the effects of interactions. This will also help you understand the relationship between the factors involved in the interaction. A train manufacturer is designing a train that will use up to 50% less energy. A Six Sigma team assigned to the project is working to make sure the design reduces carbon dioxide emissions. In the train manufacturer example, it's easy to imagine that many input factors will need to be studied to achieve the desired reduction in carbon dioxide emissions. But for the team assigned responsibility for making sure the final design delivers on reduced carbon dioxide emissions, the propulsion system's impact on carbon dioxide levels is the only concern. Sometimes you may only be interested in one factor and will elect to use a one-factor design. One-factor designs study one factor only while attempting to hold all other factors constant to reduce or eliminate their effects. One-factor designs differ quite a bit from the factorial designs, full factorial and fractional factorial. Let's look at each type of design for a brief comparison of the differences between factorial and one-factor designs. Full factorial designs study 2 or more factors and include a run for every factor-level combination, or treatment, present. No factor-level combinations are left out of the experimental design. Because of this, full factorial designs can be extensive and difficult to manage. Fractional factorial designs study 2 or more factors and include a balanced subset of the runs required for a full factorial design. Fractional designs can provide a comparable estimate of effects with fewer runs than a full factorial design. And one-factor designs study one factor only. This is the primary difference between one-factor designs and the factorial designs. Like full factorial designs, one run is included for every factor-level combination and its replicates. One-factor experiments are typically used when there's reason to expect that one factor is primarily responsible for the response or the improvement desired in the process. For instance, an auto manufacturer that wants to improve dent resistance may only be interested in the material used to enhance dent resistance. Or a food packaging plant may be interested in how moisture content in foods affects freezing time. While many factors may be involved, only one is of interest. In addition to factors of interest, all experiments have noise factors that may impact measured responses and introduce bias and variation into the experiment. This can lead to incorrect assumptions or conclusions. Noise factors are often, but not always, beyond the experimenter's control. Common noise factors may impact experiment results. Examples of noise factors include the day or time of day the experiment is conducted, the batch of materials used in the experiment, and the operator using the equipment or performing the process. Other examples include the test equipment itself and environmental phenomena, such as air temperature during the experiment. In one-factor experiments, all factors other than the one primary factor of interest are considered noise factors. Consider this example. A paint manufacturer wants to improve the texture of its paint. Spin time, the time to mix dry ingredients before combining them with liquid ingredients, can be 30, 45, or 60 seconds. A team of experimenters wants to know how this one factor, spin time, is impacting paint texture. The team suspects that paint texture may be impacted by a noise factor, the mixer that's used. 4 mixers are used during the paint manufacturing process, so the team concludes that 12 runs are required to study each treatment combination once, each of the 3 mix speeds with each of the 4 mixers. The team could use one of several designs to conduct this experiment. Let's look at each design variation for an explanation. First, running each batch in successive levels of the factor. The team may decide to divide the 12 runs into 3 batches, one for each speed as indicated by the row header. Each batch would run 4 successive tests for each spin speed, running each batch in successive levels of the factor. Testing in batches is often very practical, simple, and the least expensive option. But testing batches may introduce unintended patterns whereby effects are influenced by noise factors. It also neglects to consider the variation that the noise factor could be causing. Let's look at another design option. The team could design the experiment as a completely randomized one-factor experiment. In this case, all 12 factor-level combinations are implemented in a randomized manner. This method is ideal in a strict statistical sense, but is often impractical. And while this design makes use of randomization, it fails to explore the potential variation caused by the noise factor, the mixer. Finally, the team could elect to design what is known as a randomized block design. To minimize the unwanted variation due to the mixer, the team will group the runs homogeneously into 4 separate batches, or blocks in this case, 1 per mixer. The experiment is designed to test each of the 3 speeds with each of the 4 mixers, randomizing the order of the speed tested per mixer. In order to qualify as a randomized block design, every block must study every level of the factor of interest. Randomized block designs offer ways to help you overcome the disadvantages of running a successive or a completely randomized design. This type of design enables you to control noise factors. The objective of a randomized block design is to reduce the variability due to noise, which can interfere with your conclusions about the effect of the primary factor on the response. In the simplest designs, only one noise or blocking factor is used, but it's possible to block more than one noise factor. Some noise factors can be controlled or kept constant, while others can be blocked. Still others might be left alone because either they're least known or their effects on the experiment are expected to be negligible. In randomized block designs, blocking is used to reduce or eliminate the variation contributed by a known significant noise factor. This is achieved by dividing the total number of runs into relatively homogeneous subgroups called blocks, whereby the noise factor, at each of its levels, is the block. Then the order of the runs is randomized within each block. Randomization helps to further reduce the variation by lessening the effect of remaining noise factors. Within these blocks, the variation attributed by the noise factor is less than it would be if the experiment weren't blocked. To qualify as a randomized block design, each block must contain one measurement of each treatment, and a blocking factor is the noise factor being blocked. Let's consider a few examples of when a randomized block design might be used and when it might be inappropriate. For instance, a manufacturer of steel beams wants to improve seams to reduce stress fractures. The yield strength of the compound used to weld these seams is the factor of interest. 3 different compounds can be used, giving 3 levels of the factor of interest. However, the team running the experiment suspects that a noise factor, the welder welding each seam, may impact results if not controlled. The team decides to use a randomized block design to block by welder and control this noise factor. Another example is a Six Sigma team that has been assigned to reduce variation in the response, which is variation in color luminance. The team is designing a one-factor randomized block experiment. The factor of interest is drying temperature, which can be done at 3 levels: low, medium, and high. The team suspects that a noise factor, the 3 automated color mixers, A, B, C, are partially to blame for the variation. The team also believes this is because the mixers aren't measuring the correct amounts of color. The team decides to block by color mixer to control for the potential impact it's having on color luminance. Finally, consider a team working to improve agricultural practices. They are trying to find a way to improve germination of oats. The team wants to know if the soil mixture is impacting germination. The team believes that inconsistent outdoor temperature at different times of the day might be impacting germination. To control this noise variable, the team decides to move the experiment indoors and blocks by temperature in each block. Based on what you've learned about randomized block design, it should be clear that the experiment that fails to block properly is the final example. Here, the team has not blocked the noise factor, it has removed it. Moving the experiment indoors brings temperature within their control and eliminates the need to block for temperature. Typically, more than one noise factor may be present in an experiment. For instance, in the example where the team wants to improve paint texture, other noise factors such as temperature in the factory or the varying humidity level at different times in the day may also be impacting the texture of the paint. Before creating your block design, you need to decide which noise factors are important enough to be, and possibly can be, blocked. Typically, the decision whether to block or not will depend on several facts. 1. If the noise factor is unknown, meaning no information exists on it or its potential impact, it can't be blocked. 2. Based on your best estimates, if the noise factor is significant, it should be blocked. And 3. If the noise factor is beyond your control, it should be blocked. You can also adjust your experiment to avoid noise factors. For example, you know that during the summer, the temperature at the experiment site increases in the afternoon to a level that could possibly affect the moisture quantity response in your experiment. You could stipulate that all tests be conducted before 12 o'clock p.m. By doing this, you can avoid the noise factor and its potential impact on the response. When a potentially significant noise factor can't be avoided, blocking is the only choice. Recall the example of the team working to improve germination. Bringing the experiment inside was not a practical or realistic choice. Instead, the team could have blocked the experiment into 6 two-hour increments. All the tests in each batch would then be subjected to the same temperature. This would minimize the effect of temperature on germination within each block and the whole experiment. If you expect some biasing differences among days in an experimental design that takes several days to complete, you can block by day in the design. This will mean that each treatment is tested each day to reduce the variation introduced by day. Let's look at this example. A Six Sigma team working for a metal manufacturer wants to improve the surface finish of a particular metal. If exact temperature control isn't maintained during manufacture, surface defects can occur as the metal recrystallizes. The team wants to know how temperature is impacting the surface finish of the metal. However, the team also suspects that noise factors may be impacting surface finish. The noise factors are furnace run and thermal stress. The team doesn't have any data about the potential impact of thermal stress, and therefore it can't be blocked as a noise factor and can't be studied. Furnace run, on the other hand, can't be designed out of the experiment. The team has plenty of information about furnace runs from its quality control reports, so it will be included in the design as a noise factor. Once you have determined which noise factor must be blocked, you divide the experiment into homogeneous blocks. Block designs rely on homogeneous groups to further reduce variation or error contributed by noise factors. The objective is to create blocks in which noise factors are held constant while the factor of interest is allowed to vary. This way, it's possible to assess the effect of the various levels of the factor of interest without having to account for variations due to changes in the blocked factor. In other words, you minimize within-block variation relative to the variation across the entire sample, thus yielding a more precise estimate of the true error for the primary factor. Homogeneity within the block is an important concept. Let's discuss this concept further. When grouping or blocking homogeneously, the variability within each block is less than the variability in the entire sample. Therefore, more efficient estimates are obtained. This means each estimate of the factor-level treatments within a block is more efficient than estimates across the entire sample. And, when aggregated, the estimates across the blocks provide an overall truer estimate of error than could be achieved without blocking. Grouping homogeneously helps to further reduce noise, even for variables that aren't blocked. This is simply because groups that are more alike than different are likely to exhibit less variance among other noise factors too. This reduces overall variance. You can reach better conclusions when using homogeneous blocks. Because the important noise factor is blocked and the groups are homogeneous, the variation you observe is more closely aligned with the factor of interest. Because there is only one factor of interest and one blocking factor, the randomized block experiment can be represented in a two-dimensional matrix. The levels of the blocking factor are the rows, and the levels of the treatment factor are the columns. Now that you have knowledge of the fundamentals behind the randomized block design, consider the importance of randomization. Recall that in a randomized block design, each block contains exactly one measurement of every treatment. This ensures that every level of the factor of interest is tested at each level of the noise factor. Listing the blocking factor at all its levels by row and the noise factor at all its levels horizontally by column, the design ensures that each of the original tests is implemented. It also ensures that every level of the primary factor is tested within each block. It's the intersection of the row and column that defines the test or treatment. So even without the letters and Roman numerals, you know that the third cell in block C, which is also the third cell of noise factor 3, represents the test for the blocking factor at level C and the noise factor at level 3. These identifiers are used here for illustrative purposes only. When the design is blocked and randomized, these identifiers aren't used. The numbers that appear in the cells simply convey the run order within each block. One general rule guides the use of the randomized block design. Block what you can and randomize what you cannot. First, you create homogeneous blocks to remove the effects of one or a few of the most important noise factors. Then you randomize the runs within each block to reduce the effects of any remaining noise factors within these blocks. It may be useful to think of a randomized block experiment as a collection of completely randomized experiments, with each block comprising one experiment. Note, the blocks themselves aren't randomized, the order of the runs within them is. Recall the team working to improve the texture of paint. Let's examine how the team blocked and randomized the experiment. The blocking factor was the mixer, and the factor of interest was the spin time. The team decided to produce 4 batches of paint, one using each mixer, at each of the 3 spin times. The runs must be blocked so the factor of interest is measured in each block. Notice how each treatment, indicated by the intersection of the blocking factor and the factor of interest, matches one of the original 12 tests defined for the experiment. Remember, the numbers 1, 2, and 3 only represent the run order. Now that the treatments have been divided among the blocks, the team can randomize the order in which each spin time is studied within each block. When team members complete all the experiments, they replace the run numbers with the actual response values. They measured paint texture as viscosity by Pascal second, and the measured responses ranged between 11.64 and 16.59 Pascal seconds. Recall the team working to improve surface quality of a particular metal. Team members decide to create a randomized block design to block the furnace run noise factor. They create 4 blocks, one for each furnace run. Within every block, each of the 3 temperature levels, 700, 800, and 900 degrees Fahrenheit, will be tested. The 12 required treatments are homogeneously blocked to each noise factor level. Then runs are randomized within each block. A model can be used to express a randomized block experiment with one noise factor. Let's discuss each component of the model further. Y subscript ij is any observation for which x1 equals I and x2 equals j. where x1 is the primary factor and x2 is the blocking factor. Mu is the overall mean response. T subscript I is the effect for being in treatment of I, of factor x1, where x1 is the primary factor. And B subscript J is the effect for being in block J, of factor x2, where x2 is the noise factor. Like full and fractional experiments, the calculated results of a randomized block design need to be verified and validated using Anova or some other statistical test in order to analyze the significance of factors and confirm the model. Any conclusions will be implemented and further validated during the improve phase in an effort to optimize the process. You can access the job aid Randomized Block Designs after this video to use as a guide when creating randomized block designs. You use randomized block designs to control noise factors in one-factor experiments. After you decide which noise factor is important enough to block, you divide the experiment into homogeneous blocks, grouped by levels of the blocking factor. Every level of the primary factor is tested within each block. This ensures that the entire experiment is implemented within each block. The order of the runs within the block are randomized, which helps to further reduce the effects of all noise factors that may impact the results of the. Like randomized block experiments, Latin square designs are also one-factor designs, but they are typically used when two or more noise factors need to be blocked. The Latin square design was originally applied to agriculture. The two noise factors were the two directions on the field, and the square was a plot of ground. Like randomized block designs, Latin square designs are used to measure the effects of a single factor on a response variable while attempting to block or average the effects of noise factors by balancing out their contributions. In Latin square designs, the factor of interest is considered the third variable. The two noise factors being studied are the first two variables. The factor of interest, also commonly referred to as the primary factor or the experimental treatment, is applied to the noise factors in a balanced fashion. A Latin square is always a perfect square, with the same number of columns as rows. This means that the number of levels for each variable, the noise factor and the factor of interest, need to be equal. As a result, the design restricts randomization of run order within the experiment. In a Latin square design, the two noise factors are divided into a matrix, and the factor of interest at all levels is divided amongst the cells. The principle governing the design is that each row and each column must receive each treatment exactly once. Also, a key assumption of this design is that the noise factors don't interact with one another or the factor of interest. This must be true in order for this design to be used. Let's discuss each component of the matrix in detail. The levels of noise factor 1 are listed vertically. There will be as many rows as there are levels for this noise factor. The levels of noise factor 2 are listed horizontally. There will be as many columns as there are levels for this noise factor. Finally, each cell within the matrix corresponds to a specific level of the factor of interest and the two noise factors. Before the experiments are implemented, the combination of levels of the noise factors and the factor of interest in each cell defines the treatment to be applied. And after the experiments are conducted, each response value is a combination of all three variables. The two noise factors nullify one another's impact, so the measured responses indicate the factor of interest's impact on the response. Consider this example of a Latin square. A food manufacturer wants to reduce the time it takes to freeze produce. A Six Sigma team has been assigned the task of improving freeze time. One factor is of primary interest. The team wants to know how the moisture content of the food impacts the freeze time. Because team members want to study the impact of two noise factors, they choose a Latin square design. The produce being frozen, the first noise factor, has been chosen because the team suspects that the moisture content of the different produce may be significantly impacting freeze time. And there's evidence that the freezers being used, the second noise factor, may not be freezing uniformly. This is a 4x4 Latin square design because the noise and primary factors are all being studied at 4 levels. You can use two similar designs to study one factor of interest. Both are an extension of the Latin square design. The first is the Greco-Latin square design, which is used to block 3 noise factors. The second design is the Hyper-Greco-Latin square design, and it's used to block 4 or more noise factors. The Six Sigma team working to improve freeze time designed a Latin square to explore the factor of interest and 2 blocking or noise factors. But suppose the team wanted to include additional blocking factors. Let's examine each type of design for a brief example of how the team could include additional noise factors in its experiment. First, the Greco-Latin design. The team decides it wants to know how another noise factor, time of harvest, impacts freeze time. This factor is added to the treatments in a balanced fashion, meaning each treatment is tested within each experimental block. If the team wanted to study another noise factor, say humidity levels in the freezer, it could easily do so using a Hyper-Greco-Latin design. Again, the new noise factor must be added in a balanced fashion. The number of runs in a Latin square design is equal to the number of levels of the factors, k squared. So, for example, a 4x4 design, 4 being the number of levels of the factors, has 16 runs. When you create designs for Latin squares with 3, 4, and 5 level factors, it's important to randomize the treatments and run order as much as is allowed by the design. Recall that the Latin square designs place restrictions on randomization. Now, let's look at each design, starting with 3 level factors, to learn what the treatment combinations should be for each run. The first design has 3 factors, 2 noise factors and 1 factor of interest. Each factor has 3 levels. So the number of runs in this design is 9, or k squared. The runs are randomized by randomizing the run order in which the factor of interest is tested per block. Next, 4 level factors. This design also has 3 factors, 2 noise factors and 1 factor of interest. But in this instance, each factor has 4 levels. So the number of runs, k squared, is 16. Again, randomization is achieved by reordering the run order of the factor of interest at each of its levels per block. Finally, 5 level factors have the same 3 factors as the previous 2 designs. But this time, there are 5 levels of each factor, resulting in the need for 25 runs. This time, all 5 levels of the factor of interest are randomized per block. There are a couple of important points that should be noted about all 3 of these designs. Consider the 5-level factor design, for example. Each row and column will contain each level of the factor of interest. This helps highlight the restriction on randomization. For this to be a valid Latin square design, the number of levels per factor must be equal and must be balanced in the design. Consider a Six Sigma team working to improve the surface finish of a particular metal. It ran a randomized block design to study how temperature impacts the recrystallization of metal. At that time, only one noise factor, furnace run, was of concern. But now, the team is interested in another known noise factor, humidity in the factory at the time of the experiment. The team decides to use a Latin square design to include the second noise factor in the experiment. Here's a brief explanation of the details of this Latin square design to help you understand it better. 3 factors are being studied: the primary factor, temperature, and 2 noise factors, furnace run and humidity. Furnace run is represented by the rows, humidity is represented by the columns, and the primary factor of interest is represented by the letters in the cells. Combined, each cell makes up the treatment of each run in the experiment. Each factor has 4 levels, as evidenced by the 4x4 matrix design. The number of runs in the experiment is equal to the number of cells in the matrix, 16. The center cell of this 3-level factor Latin square design is the treatment combination of furnace run at level 2 and humidity at level 2. 2 characteristics of Latin square designs make them advantageous. First, they're efficient relative to other designs. Because they require fewer runs than many designs, Latin square designs can be quicker and less expensive to conduct. Second, they can control variation in two directions. This characteristic of the Latin square design allows variation attributed to two noise factors to be kept separate by design or because they can't be combined. Latin square designs also have some characteristics that are considered disadvantages. Let's have a look. Because the number of rows, columns, and treatments must be the same, the scenario must fit the design. If you want to study one noise factor at 3 levels and another at 4 levels, you can't with a Latin square design. In addition, you can't measure interaction effects between row and column factors, between rows and treatments, or between columns and treatments. This makes the Latin square design inappropriate for use when interaction effects are expected. Another drawback is that only a few degrees of freedom for error exist in small squares. Using repeated squares in a given experiment can help alleviate this problem by increasing the error degrees of freedom. Finally, experimental error is likely to increase with larger squares. Error is given by r-1 times r-2, where r is the number of rows or number of columns, as both of these are equal. Typically, a 2x2, 3x3, 4x4, or 5x5 design will have 0, 2, 6, and 12 errors respectively. Like the randomized block designs, as the tests are completed, the letters in the matrix are replaced with measurements. The observed impact on the response is recorded in the cell for the treatment that brought about the particular response. Noise factors aren't always insignificant. The Latin square design provides a way to measure the effects of noise factors, but now you need a way to analyze them. As with other experimental designs, statistical software will typically be used with Latin square designs to provide graphs and tables summarizing main effects. Anova is the primary tool for analyzing Latin square designs. If the factor of interest or a noise factor at various levels has a significant effect on the response, the factor will have a p-value that is less than or equal to alpha in the Anova report. Alpha is typically set at 0.05. This significance would show up as a p-value lower than alpha, implying that the factor at the given levels affects the response. Anova for Latin square designs involves totaling the rows, the columns, and the treatments, all the A's, all the B's, and so on. Next, you determine the mean sum of squares for the treatment and the mean sum of squares for the error. Finally, you compare the ratio of the mean sum of squares for the treatment and the mean sum of squares for the error, the F statistic, to a critical value to assess significance. You should be familiar with this Anova procedure from your other Six Sigma work. Anova is typically done using software. Let's look at the basic components of a Latin square model. Y subscript ijk denotes any observation of the response variable for which x1 equals I, x2 equals j, and x3 equals k, where x1 and x2 are blocking factors and x3 is the primary factor. Mu is the overall mean response. R subscript I denotes the effect for block factor I. C subscript j denotes the effect for block factor j. T subscript k denotes the effect for treatment factor k. Random error denotes the random error of the experimental design. Various estimates can be obtained for the Latin square design. Let's take a look. The estimate for mu is the average of all the data, while the estimate for R subscript I is the average of all y for which x1 equals I minus the average of all the data. And the estimate for C subscript j is the average of all y for which x2 equals j minus the average of all the data. Finally, the estimate for T subscript k is the average of all y for which x3 equals k minus the average of all the data. The model describes the response variable y. The model's purpose is to define the factor and level settings that will yield the best response. Through experimentation, you learn about the impact the factors have on the response variable. And based on the impact demonstrated during the experiment, factors will either be quantified if shown to be significant, or removed from the model if shown to be insignificant. Recall the Six Sigma team working to improve the surface finish of a particular metal. The team has designed a Latin square that will allow it to control the variability of the blocking factors, furnace run and humidity, while testing the primary factor, temperature. You can access the job aid Latin square designs after this video to guide your application of the designs. The software returns an Anova readout, which the team reviews for significant factors. The factor of interest is identified in the title and is listed with the other two factors, the noise factors. The team finds that temperature, with a p-value of 0.012, is significant. And humidity is also significant, with a p-value of 0.000. However, furnace run isn't significant. Latin square designs are similar to one-factor randomized block designs. The main difference is that Latin square designs offer a way to study one factor of interest while controlling the effects of two or more noise factors. You must follow a couple of rules when using a Latin square design. You can only include one primary factor, and there must be an equal number of rows, columns, and treatments. This ensures the design is balanced. Also important to note is that Latin square designs can't measure interaction effects, making them an inappropriate choice if you want to understand the interactions between factors. Latin squares can be analyzed manually, but usually software is used. Anova readouts are the primary tool used to analyze the results of a Latin square design. In Japanese, the word muda means waste, and any activity that doesn't add value is considered muda. The reduction and elimination of muda, or waste, is an important part of Lean Six Sigma. People, materials, and machines all create waste through activities that are non-productive, interrupt the process flow, or consume more value than is produced. Although it sounds straightforward, removing waste can be a significant challenge for organizations. In the traditional business world, problems are usually solved by addition, extra staff, more resources, or additional steps in a process. To accept Six Sigma, team members must learn to solve problems by subtraction, eliminating non-value-added activities. You should be familiar with the concept of waste from your Greenbelt training. The Lean methodology recognizes 7 categories of waste, namely overproduction, unnecessary inventory, transport waste, process waste, rejects, waiting, and unnecessary motion. You can access the resource, The 7 Categories of Waste, after the video to refresh your knowledge of the main types of waste. Every defect has an impact on the overall production cost of a product or service. As a Six Sigma Black Belt, you'll be expected to deploy Lean tools to detect and repair errors. The main Lean waste elimination tools are 5S, just-in-time, Kanban, value stream mapping, Kaizen, Poka-yoke, Jidoka, Takt time, visual controls, and total preventive maintenance, TPM. You should be familiar with these tools from your Greenbelt training. You can access the content of Lean tools after the video to refresh your knowledge of Lean tools. This video focuses on the 4 main waste elimination tools in the Lean methodology: 5S, Poka-yoke, standard work, and Kanban pull. Each has a different but important method of waste elimination. Quality improvement can't be implemented in a workplace that is disorganized, cluttered, and neglected. 5S is a simple and practical method for eliminating waste in the workplace. 5S originally involved 5 Japanese words beginning with S that were later given English terms: sort, straighten, scrub, standardize, and sustain. Each of these 5 terms involves particular activities and practices that can work as steps toward overall waste prevention and elimination. Let's discuss each 5S step in more detail to learn about the activities and practices it encompasses. Sort involves separating needed from unneeded items, inspecting and listing items that need repair, and clearing out the clutter. Straighten entails arranging and organizing the tools, equipment, inventory, and supplies remaining after the sort stage. It means finding a place for everything and everything in its place. Scrub means cleaning the work area, doing root cause analysis on sources of dirt and grime, and making corrections, removing trash, and defining the standards of cleanliness to adhere to. It also includes repairing any broken machinery. Let's cover the final two steps of 5S now. Standardize is the step where the previous 3 S's are standardized. It involves recording 5S activities and best practices and incorporating them into the normal work routine. It also involves maintaining a clean environment by setting a regular maintenance schedule. Sustain involves monitoring adherence to each of the 5S steps. In this stage, you maintain the improvements made in the first 4 steps and establish 5S as the normal way of doing business. Many organizations have adopted 5S to prevent and eliminate wastes and also to improve productivity and performance. Hewlett-Packard used 5S to reduce training time for employees and to improve information sharing. Boeing used the methodology to improve productivity, product quality, and safety levels. You can access the job aid 5S practices after the video for more details on the practices within each step of the 5S approach to waste elimination and quality improvement. Mistake proofing is a fundamental part of the lean philosophy. The second main waste elimination tool is known as pokayoke, or mistake proofing. This tool focuses on preventing mistakes before they happen by eliminating the opportunity for error and detecting the potential for error in existing processes. Everyday life abounds in pokayoke devices, such as the automatic shutoff on a kettle or the spell check on your computer. In business, pokayoke could include a part designed so it can't be used incorrectly, or a fail-safe cutoff mechanism in a risky procedure. For example, a filing cabinet could be designed so that opening one drawer locks all the rest, reducing the chance of tipping. Pokayoke uses simple devices to counteract or detect defects, or to prevent defects from occurring in the first place. There are 4 basic types of pokayoke devices, namely checklists, screening, signaling, and control methods. You can access the job aid Pokayoke Mistake Proofing after the video to reference countermeasures in Pokayoke Mistake Proofing. Let's examine each Pokayoke device in more detail. First up are checklists, which are the simplest of the Pokayoke measures. A checklist is a list of action items, steps, or materials needed for a task. Each item is checked off as it is completed or accounted for. A checklist ensures that all steps in a process are covered, or that all required parts and materials have been used. Checklists are useful when there are a fixed number of operations in a process, or when a product has a fixed number of parts. Next is screening. Screening devices are design features that prevent processes, equipment, or tools from being used incorrectly. These devices screen out the wrong ways of completing a task by ensuring that the only conditions under which a task can be executed is the right way. Screening devices remove the need to correct mistakes, since the user can't make a mistake in the first place. Software engineers often use a simple screening device that disables the accept box until the user accepts the terms of agreement. Then is signaling, which is a device for noting when something is out of order or not conforming. Signaling does not stop the product line or process. An example would be warning lights that alert a machine operator to a problem, or beeps that signal a step is due to be performed. And finally, control methods are devices that shut down a process when a defect occurs. These are more powerful than signaling devices because the process cannot be completed until the error or defect is corrected. An example would be a production line that stops when a machine starts producing a defective part. A manufacturing example of a screening pokayoke involves a jacket that requires 10 buttons to be attached. Rather than relying on the worker to always use the correct number, a packet of 10 buttons is part of the standard materials. If any buttons remain upon completion of the sewing, the operator can tell that an error has occurred. Standard work is the third main waste elimination tool. It's an agreed-upon set of work procedures and best practices that document the interaction of people, materials, and machines. The purpose of standard work is to maximize performance and minimize waste at each workstation while facilitating planned talk time, the maximum time allowed to produce a product in order to meet demand. Standard work involves careful documentation of work processes, action sequences, quality and safety checks, and other important work details. Establishing standard work relies on recording and distributing data in a few basic forms. There are a number of documents in a standard work package. including standard worksheets, combination sheets, capacity charts, task and training manuals, and standard operating sheets. Standard worksheets are the base document of standard work. Their purpose is to describe the normal conditions of work. A standard worksheet is kept at each workstation. It documents and visually represents each work sequence. If the actual conditions are different from what is documented, it indicates there's a problem to resolve. In a larger organization, many workstations may use the same standard operating procedures and the same standard worksheets. Although a worksheet can contain many fields, the three most important are the cycle time, work sequence, and standard inventory for a workstation. Let's examine these three fields in a bit more detail. Cycle time is the time needed to carry out the sequence of steps that produce the desired result. The work sequence outlines the steps in a process and the order in which those steps are carried out. The work sequence is often included as a diagram. Standard inventory is the minimum inventory needed for operations to proceed. Standard inventory is clearly marked on the standard worksheet so you can see discrepancies between that amount and the actual inventory on hand. Where standard worksheets express workflow in the dimension of space, standard work combination sheets express the flow in the dimension of time. These documents are used to record manual, walking, automatic, and waiting times in a single, graphical, easy-to-understand chart. The standard worksheet and standard work combination sheet go together to give a complete picture of a work process. A standard work package also contains capacity charts. These documents chart the capacity of the machines involved in a process. Each chart represents the interaction between a part and a machine. Put simply, they outline what a machine is capable of. Capacity charts are particularly useful for identifying bottlenecks. Standard work is nearly impossible unless workers have a reference that describes the standards for doing that work. Task and training manuals are instructions to the process operator for implementing the process. They include detailed policies and procedures, equipment layouts, safety standards, cycle times, and quality checks. Standard operating sheets, sometimes called standard operators sheets, deal with the interaction of a worker with equipment and tools. These documents communicate standard timings and procedures and relay accurate, up-to-date information about cycle times and operations capacity. Operating sheets also provide equipment layout diagrams, order of operations, and safety and quality checks. Standard operating sheets are regularly revised as equipment and operations change. The operator's detailed instruction sheet, or ODIS number, is used to facilitate revision control tracking. In the Lean methodology, Kanban is a control system that uses just the right amount of work and materials to meet production needs. Originally the Japanese name for a card or ticket used to signal the need for inventory, Kanban has become a term describing the pull method of consumption-driven replenishment. Kanban pull describes the connection through the value stream from supplier to consumer and back to supplier in a continuous loop. When a downstream process consumes a component from an upstream process, upstream begins production of a replacement. Kanban pull uses a signal or other communication to indicate when and in what quantities materials need to be replenished. A signal can take different forms, but it is always generated by actual consumption, the pull of the downstream customer. For example, in a manufacturing situation, a workstation might communicate with a predecessor workstation, signaling the need for new materials or components as soon as work has been completed. In this way, Kanban pull facilitates continuous flow. In factories that use Kanban pull, the order to produce new parts and materials is dependent on receiving a piece of instruction called a Kanban card. Cards are placed and retrieved in designated spots known as containers. Card-based systems can work well within businesses such as factories, but for operations that use Kanban pull-based systems to deal with geographically diverse customers and suppliers, using physical cards to communicate replenishment presents challenges. Cards can be mislaid or destroyed, which means replenishment signals are lost, resulting in stock outages. Some businesses have implemented e-Kanban systems with electronic cards to deal with these challenges. There are many ways to configure a Kanban pull system, but the 4 basic Kanban pull steps keep the process flowing. The first step is to calculate the safe stock level of materials required. Safety stock is the amount of inventory carried in addition to that which is needed to meet expected demand. Next, calculate the lead time for replenishment of materials. Materials lead time encompasses the manufacture and transport time of materials from the supplying resource to the target workstation. Then, determine the batch size to identify how much product you need to produce in one continuous work process to satisfy customer demand. Finally, check and adjust levels of materials needed based on the requirements of the first 3 steps. Let's continue now by covering each of the Kanban pull steps in a bit more detail. The first step in Kanban pull is to calculate the minimum or safety stock level required in the process. Safety stock accommodates variations in actual demand, so there won't be an outage when actual usage exceeds forecasted demand. The more unpredictable the product demand, the larger the safety stock. The second step is to calculate the lead time for replenishment of materials. Known informally as shipping and handling, materials lead time can be as short as a few minutes or as long as months for specific or intricate components. The anticipated lead time is the sum of 4 factors, the first of which is the time it takes for you to place an order. The next component is the time it takes the supplier to process your order and to manufacture or retrieve and then pack the materials. Then, consider the transport time for the materials to travel from the supplier to your workstation. And the final component is the time it takes you to receive, unpack, and prepare the materials for use. The third step is to determine the batch size, how much product is being created. This will determine the manufacturing stock level and the manufacturing lead time. The batch size will be determined by how much product you have to produce to meet customer demand. Once you have determined how much stock you need, how long it will take to get materials, and how much product you need to produce, it's time for the last step. This final step is based on the information from the first 3 steps. You'll need to check and adjust levels of requested material, taking into account current stock, lead time, and batch size. Now, let's consider an example. A manufacturer of small electronics is introducing a new MP3 and video player for the holiday season. A Six Sigma team is working at the company's manufacturing plant to set up a Kanban pull system. Let's review how each Kanban pull step was used by the team to configure the system. Step 1 is to calculate the safe stock level of materials required. The team determines that it needs a safety stock of 1 week's worth of production materials to meet variation outside of expected demand. The second step is to calculate the lead time for replenishment of materials. The team calculates that the manufacture and transport time of components from the suppliers to the target workstations is 4 days. Then is Step 3, determine the batch size. To meet advance orders, the team determines that a batch size of 200,000 units will satisfy customer demand. And then the final step is to check and adjust levels. The team does final calculations to check and adjust levels of materials needed in light of the first 3 steps. These final levels determine the appropriate placement of pull cards in the process. So why use a Kanban pull system? There are a number of benefits that you could consider in answering this question. Firstly, it reduces overall inventory and reduces work in process. It also decreases cycle time and reduces order turnaround time. And the final 2 benefits are decreases in machine downtime and increases visibility of quality issues. There are also some challenges that come with a pull system. For Kanban pull to work, material must flow at a steady rate in a fixed path. Large variations in volume or product mix can interrupt the flow and undermine the system's performance. And it may not work when vast distances separate assembly plants and suppliers. Another obstacle can be unexpected variation in market trends. Since a pull system causes production to start only when there is a demand for a product, a lean organization must be quick in responding to the market. Waste elimination is important to the lean methodology. The 7 categories of waste are overproduction, unnecessary inventory, transport waste, process waste, rejects, waiting, and unnecessary motion. The four main waste elimination tools of Lean are 5S, Pokayoke, Standard Work, and Kanban Pull. 5S, or Sort, Straighten, Scrub, Standardize, and Sustain, is used to organize workspace and workflow. Pokayoke is a method of using simple devices to prevent errors from happening. Standard Work uses documentation to record and communicate standard methods for process implementation. Kanban Pull is a method for efficient replenishment of materials based on fulfilling customer demand. The four steps in Kanban Pull are calculating the safety stock level of materials required, calculating the lead time for replenishment of materials, determining the batch size, and checking and adjusting replenishment. Cycle time is one of the most important measures of efficiency in a lean organization. Cycle time for a process is the total length of time required to complete one cycle of that process. This includes not only time taken doing the actual work, but time spent preparing, waiting, moving, storing, reviewing, and reworking. In business, cycle time is a key issue because it has a direct impact on cost and delivery. Benefits of reducing cycle time include freeing resources, eliminating waste, reducing costs, improving customer satisfaction, and decreasing product time to market. It's important that organizations recognize the significance of cycle time. First, cycle time is an operational measure, and so is almost entirely within an organization's control. Second, cycle time has a major effect on productivity, which stimulates competitiveness and market share. You should be familiar with the concept of cycle time from your Greenbelt training. You can access the content Cycle Time Reduction after the video to refresh your knowledge on how to reduce cycle time. There are many ways to look at a cycle. At its simplest, a cycle is a series of events occurring in a regular sequence. What do you think of when you consider a cycle? In business, a cycle is an orderly process of change that returns to the point at which it began. In Lean Six Sigma, product lifecycle is one of the most widely used strategic decision-making concepts. If an organization is aware of how it fits into this cycle, it can take strategic control and increase profitability through process improvement. In lean organizations, two tools are commonly used to reduce cycle time: continuous flow manufacturing and single-minute exchange of dies. Continuous flow manufacturing, or CFM, is a time-based methodology that focuses on reducing defects by improving logistics. It's a no-nonsense approach that optimizes flow by turning materials into finished products as quickly as possible with no wasted effort. Continuous flow manufacturing works toward an ideal production cycle that is uninterrupted by quality issues, equipment malfunction, transportation difficulties, shipping and handling problems, or inventory uncertainties. Continuous flow manufacturing has a number of characteristics that make it valuable. Firstly, it delivers a flow of products to the customer with minimal delay and lowers the risk of losses through product damage, deterioration, or obsolescence. Then it also provides a mechanism to solve production problems and reduces expenditures for storage of inventory. And it also makes efficient use of floor space. Consider a product moving through a long production line. Any delays early in the process will delay later steps in the process. In a complicated process, upstream delays can cascade through the system, causing multiple time delay problems. One characteristic of continuous flow manufacturing is the use of units made up of their smallest logical level, either one piece or a small batch at a time. Right-sizing batches is important because batches that aren't the right size lead to queues, which lead to waiting, which ultimately leads to bottlenecks and delays, poor space and resource utilization, and longer cycle times. In a continuous flow manufacturing layout, a group of machines or workstations is called a cell. Production steps are arranged in a characteristic tight sequence that flows through a U-shaped cell arranged for optimum operability and maintainability. Inside a cell, each workstation is organized to achieve continuous flow and desired takt time. But a change in layout alone doesn't create continuous flow. It's important to provide training and encourage buy-in from employees and other process owners. A team approach throughout the process encourages workers to accept and to lead the improvement initiative. Let's consider an example now. A large manufacturing company that produces stock kitchen cabinets is working with a Six Sigma team to adapt its production facilities to continuous flow manufacturing. In the past, production has been plagued by quality problems, inconsistent work methods, large batch production, excessive inventory, and extensive non-value-added work. Let's review each adaptation to see what changes the company made. They start by using the right size batches. The team determines that the old large batch process causes inefficient parts flow because parts are spread over a large area, requiring workers to take unnecessary steps to retrieve what they need. In addition, specialized machinery is located away from the main production line, increasing inefficiency. A new workflow is designed that utilizes smaller batches. Then they use a series of U-shaped cells consisting of individual workstations to divide the production flow. Each cell is marked with new equipment and inventory locations. Material storage units are built into each cell. Next, the team creates buy-in. Team members talk to employees about the benefits of continuous flow manufacturing and work with them to design and implement the new system. Cell layouts are reviewed with process owners, and the employees are given the opportunity to provide additional input on the design of each workstation. And finally, they provide training. Training in new methods is given to each employee. Handbooks and documentation are provided at each workstation. Most organizations produce a range of products and services. This requires periodic changing of processes, routines, and tools and machinery. In a lean environment, changeover and setup time are considered non-value-added activities. Single-minute exchange of dies, or SMED, is a systematic approach to reducing machine setup and changeover times. The successful implementation of SMED is the key to quality improvement for any organization that produces, processes, or packages a variety of products with a single machine, line, or cell. SMED has a number of advantages over traditional management of cycle time. Why do you think that traditional methods are less advantageous than SMED? In traditional production line manufacturing setups, it's common practice to produce large lots of a particular type of product and then switch over to another product. This practice produces a large amount of inventory and associated waste. The phrase single-minute exchange of dies is a bit misleading. Single minute doesn't mean that all changes should take 1 minute, but rather that setups should take under 10 minutes, the number of minutes that can be expressed in a single digit. Nor does the approach apply only to dies, but to all processes that incorporate changeovers of some kind. The basic concept of SMED is that setup work adds no value to a product, and therefore setup should be reduced as much as possible. In a SMED setup, the time objective is always 0, meaning it doesn't interfere in any way with continuous flow. SMED aims to reduce the fixed cost associated with setup and allow for smaller batch sizes. This, in turn, will work toward the ultimate goal of cycle time reduction, the production of only what is demanded by the customer. There are 11 steps in the SMED process. The first 3 steps involve preparation. This is when you form your team, train your team in SMED, and study the setup or changeover process to determine waste. The next 6 steps in SMED involve implementation and are the most important in the process. These core steps are organize setup operations, eliminate waste, convert internal setups to external setups, improve internal setups, improve external setups, and develop a standard operating procedure. Let's cover the first 3 of the 6 core SMED steps in a bit more detail now. The first core step is to organize setup operations into waste, internal setups, and external setups. Waste is any motion that does not add value to the setup. Internal setups are operations that can only be performed while the machine is shut down. External setups are operations that can be performed without shutting down the machine. The second core step is to eliminate waste. Based on your study of the process, you'll have determined where wasteful steps and non-essential operations occur. Now's the time to eliminate that waste. In the third core step, you should convert internal setups to external setups. External tasks are tasks that can be done while the machine is running. Externalizing reduces downtime, the major cost associated with setups and changeover. Because internal setup tasks cause downtime, as many tasks as feasible should be classified as external. Let's review the remaining 3 core steps. The 4th core step is to improve internal setups. Examples in a manufacturing situation might include using a specially designed holder to organize tools, or using quick-release fasteners instead of screws and bolts. The 5th core step is to improve external setups. External setup time can be saved if a workspace is thoroughly organized. You could do this by using checklists to avoid omission and by implementing 5S. The 6th core step is to develop a standard operating procedure that will sustain the improvements made in the process by documenting the improved setup specifications and procedures. Consider this example of a consumer electronics manufacturer that offers a large number of choices and a high degree of customization options through its online store. This low volume and high product mix results in large inventories. Also, because of significant changeover time, certain products are produced only on certain days of the month, resulting in delays shipping products to consumers and retailers. To become a lean organization, the company decides to tackle changeover time using SMED. Let's review how the process improvement team at the electronics company implements each core step of the SMED. To organize setup operations, a review of each process is conducted and steps are classified as internal or external. The team determines which parts of the changeover process can be performed while the machines are still running, and which changes require the machines to be stopped. Then, eliminating waste, waiting time is decreased in the new process by avoiding backtracking. Workers begin the setup operation for each workstation as soon as the product had passed through, rather than waiting until it left the cell. Next is to convert internal setups to external setups. Dispensers containing adhesives are fitted with liners so they can be changed without the machines being shut down for cleaning. The 4th core step is to improve internal setups. Production is organized by commonality between setups to reduce the number of steps when changing over to a new production process. Next, they need to improve external setups. Machine parts used for each process are color-coded so that workers can quickly find the right tool to fit the machine for a particular process. And finally, to develop a standard operating procedure, the new setup processes are documented and sent to each workstation. The electronics company finds that reduced cycle time has many benefits. The primary benefit is faster time to market. Since the value of electronics declines rapidly over time, a shorter cycle time ensures less depreciation from the time products enter the manufacturing cycle to the time they reach the market. Other benefits are reduced inventory, more efficient use of tools and equipment, and lower human resource costs. The final 2 steps in SMED involve summation. This is when you evaluate the performance of setup reduction and, finally, prepare for the next setup reduction project. Large fluctuations in volume or product mix can interrupt the flow of a production process and undermine a system's performance. Heijunka is a production leveling tool used in Lean and Six Sigma implementations to evenly redistribute or level the workload on employees and machines in a production environment. It is similar to continuous flow and single-minute exchange of die, or SMED, in this regard. Rather than performing large volumes of work in batches based on immediate demand, Heijunka evenly distributes the work based on the type of work that needs to be done and the time frame in which it can be done. This prevents sudden spikes in production followed by downtime, which helps reduce cycle time, minimizes human error, and cuts costs. Heijunka aims to organize the flow of production processes to function more efficiently. To do this, Heijunka uses various components to reorganize workflows and production processes in a manner that both boosts efficiency and adapts to drastic and sudden fluctuations in demand. There are 5 key terms you need to be familiar with when implementing Heijunka. Takt time is the maximum time allowed to produce a product in order to meet demand. Takt time is used to steer the Heijunka implementation. Then the Heijunka box, which is a visual representation of workflow used in Heijunka to illustrate the type of leveling during a specific production schedule. Next, volume leveling. a production leveling approach that involves producing just enough goods to meet the long-term average demand during a particular production period. This means carrying just enough inventory to compensate for possible fluctuations in the expected demand, the stability of the production process, and the speed of shipping. Then is type leveling, which is a product leveling approach that involves carrying the minimum inventory needed for flexible changeovers. Operations essentially produce a new product daily. A Heijunka box is used to indicate the production flow and schedule. Finally, changeover time is the time taken to switch from one activity, process, routine, tool, or piece of machinery to the next within a lean production environment. Heijunka relies heavily on decreased changeover times because in a lean environment, changeover time is considered a non-value-add activity. The benefits of Heijunka can be grouped into three categories: predictability, flexibility, and stability. Let's discuss the benefits in more detail, starting with predictability. Volume and type leveling, along with takt time, assist in increasing predictability. As illustrated in the diagram, many production schedules are based on a build-to-order system, which means huge fluctuations in production according to customer demand, and there are often long changeovers in between bulk production processes. An unleveled production plan has an increased risk of defects and waste because changeovers don't add value and the use of labor and machinery is unbalanced. Heijunka aims to regulate the flow of production in a manner that is more predictable and controlled. Heijunka uses takt time to evenly distribute production volumes and types. Takt time helps to guide the Heijunka implementation, ensuring a more predictable level of demand, a regular work schedule, the even use of resources, and consistency in productivity and product flow. Heijunka helps ensure a more even distribution of work by leveling product volumes according to the product type, an anticipated average demand, and the expected production time. This helps improve organizational flexibility because a workflow can be adjusted ahead of schedule rather than just responding to an immediate customer demand. However, Heijunka requires a smooth changeover from one task or machine to the next in order to be optimal. Heijunka also improves stability. By leveling the demand to meet projected targets, you are able to ensure consistent product availability. This improves the flow of product and service delivery. Consider the example of a furniture manufacturer that receives orders for 30 chairs in 1 week, 12 chairs on Monday, 6 chairs on Tuesday, 3 chairs on Wednesday, 6 chairs on Thursday, and 3 chairs on Friday. If the company balances the workload by producing 6 chairs daily, they are able to fill all the orders by the end of the week without a sudden spike in production levels from one day to the next. As discussed, a Heijunka box is a visual representation of the planned activity for a specified time period. The Heijunka box consists of pigeonholes that represent equal time slots. Each row of slots represents an activity. The columns indicate the number of activities that should be completed in the time frame. Using takt time as a guide, the available work is allocated to each 2-hour time slot until each of the 5 slots are full. In this example, 2 instances of item A are produced, represented by the first column. It takes an hour to produce 1 instance of item A, and therefore no other work can be done during that 2-hour time slot. The second column contains 3 instances of item B that take 30 minutes to produce, equaling 90 minutes, and 2 instances of item C that takes 15 minutes to produce, equaling 30 minutes, thereby filling the 2-hour time slot in the second column. Columns 3 and 5 both contain 2 instances of item A, evenly filling the 2-hour slot each, whereas column 4 contains an instance of item A and B each, and 2 instances of item C. When combined, these instances fill the 2-hour production periods there as well. Consider a visual representation of Heijunka applied to a small bakery. The bakery needs to produce 4 types of baked goods throughout the day, each represented by a letter. W equals cupcakes, X equals bread, Y equals pies, and Z equals larger cakes. The unleveled process focuses on baking popular and smaller items like cupcakes and bread earlier and leaving larger products such as pies and large cakes for later. However, if the bakery opens at 8 o'clock a.m., there will only be 2 products for sale. A customer wanting to purchase a large cake at 8:30 a.m. would leave unsatisfied, and the bakery would have lost a sale and perhaps a potential future sales. Similarly, if they received an order to bake a specialty cake for delivery later in the day, or for 30 cupcakes for an event, the staff would be overloaded and may not be able to meet their daily target due to the special orders. If the bakery were to use Heijunka production leveling, it can produce smaller quantities of each product at regular intervals throughout the morning. A customer could buy any of the products on offer from 6:30 a.m. onward. Additionally, balancing the demand gives staff the flexibility they need to respond to any special orders they may receive during the workday. It is worth emphasizing that staff would need to change over from one activity to another with minimal effort for Heijunka to yield optimal results, which may require the use of other Lean Six Sigma initiatives. The prevention and reduction of waste while creating continuous flow is the key to a successful lean enterprise. In lean organizations, two tools are commonly used to reduce cycle time: continuous flow manufacturing and single-minute exchange of dies. Continuous flow manufacturing is a time-based methodology that focuses on reducing defects by improving logistics. In a continuous flow manufacturing layout, production steps are arranged in a tight sequence that flows through either a line or a U-shaped cell arranged for optimum operability. Single-minute exchange of dies, or SMED, is a systematic approach to reducing machine setup and changeover times. The 6 core steps in the SMED process are organize setup operations, eliminate waste, convert internal setups to external setups, improve internal setups, improve external setups, and develop a standard operating procedure. Heijunka is used in lean implementation to level production more evenly by distributing the work into a workflow rather than a demand-driven process. Key terms include takt time, a Heijunka box, volume and type leveling, and Kaizen is a Japanese term for continuous improvement. In Lean Six Sigma terms, it refers to a continuous improvement project that eliminates wastes and streamlines processes. Good Kaizen projects stress employees' ability to undertake creative problem-solving and continuous improvement. Kaizen is an efficient project-based approach that implements quality improvement once you've identified the constraints in a process. Kaizen is focused on continuous improvement using basic Lean Six Sigma tools to develop, assess, and implement solutions. There are different types of Kaizen activities, ranging from the development of solutions for manufacturing problems to streamlining the flow of work in an office. Kaizen fundamentally differs from traditional continuous improvement methodologies because it is action-based. Teams both develop and implement solutions by creating new processes or changing existing ones. Typically, a Kaizen initiative has 6 stages: state the problem and solution, gather and train your team, collect data, analyze the data, make improvement recommendations, and implement and monitor changes. Let's cover the stages of Kaizen in more detail now. In the first Kaizen stage, the team develops a statement outlining and supporting the problem, goals, objectives, and deliverables for the project. The purpose of conducting this stage is to make sure that team members, stakeholders, and customers understand the requirements and desired outcomes of the project. The purpose of the second stage of Kaizen is to gather and train your team. It's in this stage that project team members are chosen based on their individual talents and on their collective ability to work cohesively. Team members receive training for the specific tools and tasks needed during the project. Finally, a schedule is developed to ensure that key project milestones are implemented in a timely manner. In the third stage of Kaizen, team members collect data on which to base decisions that will allow them to manage the actual Kaizen event. Based on the gathered data, metrics are formed, and the current process is mapped through the use of various Lean and Six Sigma techniques. In the fourth stage, the team analyzes the data gathered in Stage 3 to identify areas for improvement, formulate ideas, determine the root cause of problems, and evaluate proposed improvements. During the fifth stage of Kaizen, the team makes improvement recommendations and ranks priorities based on the analyses of data completed in Stage 4. Recommendations are prioritized based on estimated financial savings and on the amount of waste eliminated. It's now that roles, responsibilities, requested resources, metrics, and measurements are revised for each process improvement. The sixth and final stage is the action stage. This is when the team communicates the plan and implements and monitors changes. Other stakeholders, such as suppliers or functional employees, are often involved in making these improvements. Regular update meetings are held, and progress is measured using metrics. Documentation is completed, a Kaizen storyboard is created, and the process improvements are assessed to determine if they can be migrated to other areas. You can access the job aid The Stages of Kaizen after the video to reference the stages of Kaizen. Kaizen projects are events that focus on improving the value stream. Typically, these projects unfold over weeks or months, but the Lean methodology also uses a technique called the Kaizen Blitz. In a Kaizen Blitz project, a small cross-functional team creates, tests, refines, and implements solutions to constraints in just a few days. The Blitz starts with a specific problem to solve and a goal that is small, clear, and achievable. For example, a property management company might target a reduction in energy consumption at a large office building. A Kaizen Blitz differs from a regular Kaizen event in that it's an intense, short-term project. Although a Kaizen Blitz follows the Kaizen methodology, it does so in a much shorter time, typically 3 to 5 days. A Blitz always has a narrow and specific objective so that it can be completed quickly and efficiently. Let's review a typical 5-day Kaizen Blitz. You and your team might spend day 1 planning, day 2 measuring and analyzing, day 3 brainstorming, day 4 implementing, and day 5 fine-tuning and confirming. On day 1, the project kickoff meeting communicates the purpose of the project to the team. The problem statement is created and the scope is narrowed and defined. Project ground rules are established for roles, responsibilities, workload, resources, and boundaries. A work plan is created to document project activities, estimate time and resources, and identify measures of progress. You and your team will decide which tools will be used to gather and analyze data. On day 2, team members begin to collect data and conduct interviews with workers. They directly observe the current process, take measurements, and identify items from the 7 categories of waste. A process map of the current work area or process is developed. Your team will continue to analyze data as it's gathered and will begin developing metrics for workspace use, distance traveled, throughput rates, and lead times for each step in the process. Ideas for waste elimination are prepared for presentation the next day. On day 3, you'll meet with your team to brainstorm improvement ideas for fixing the constraints and eliminating the waste identified on day 2. Each idea is evaluated in light of the collected data and the resources required to implement it. Tools such as affinity diagrams and checklists help the team reach consensus about which improvements to implement. Once the improvements have been determined, the team establishes what will be needed in terms of equipment, tools, templates, documentation, and work standards to carry out the improvement. On day 4, you'll incorporate the collected data and approved recommendations for process improvement into the project's action plan. Team members are assigned responsibilities, and the project work plan is expanded and updated. You'll also create a timeline that sequentially offers improvement actions. During the day, you and your team members will meet with operators and process owners to explain and demonstrate process changes and new procedures. The improvements are implemented, and then, throughout the day, you'll observe, evaluate, adjust, reobserve, reevaluate, and readjust processes in a refinement cycle. On day 5, you and your team refine, approve, and document process changes. Standard operating procedures are drafted and then tested to confirm that measurable improvement has been accomplished. Final refinements are made, and the process is documented as standard work. Changes that require time to implement are incorporated into a future action plan. Finally, the project is documented into a Kaizen storyboard for presentation to everyone impacted by the new processes. Now, let's follow along to find out, in practice, what happens on each day of a Kaizen Blitz. A Six Sigma team at a computer hardware company recently applied the theory of constraints to find problems in the manufacturing process. On day 1, the project kickoff takes place. The problem statement in this case is straightforward: a high defect level in the circuit boards. The team defines its task in a simple way: to make improvements that eliminate defects and optimize the work area for the circuit board assembly. The team creates an initial work plan and decides to use lean tools such as 5S, work diagrams, and process mapping to work with the data collected. On day 2, team members spend most of the day on the shop floor. They interview workers in the assembly area, observe them at work, take measurements, and check for waste. They create process maps from their observations and develop metrics from the data. Their creativity helps to determine where and when changes can be made. For example, one team member realized that a root cause of the problem was that workers do a lot of backtracking when retrieving inventory, which in turn creates a bottleneck. On day 3, team members brainstorm ideas for improving the circuit board process. Each person on the team is given equal opportunity to present ideas. Once team members agree on which improvements are efficient and cost-effective, they determine what is required to implement the solution. On day 4, the work plan is revised and expanded. A project timeline is created, and team members are assigned responsibilities. To cope with the bottleneck that was observed on day 2, a team member creates a new process map and an equipment layout diagram for the workstations. Later, the team meets with workers to discuss standard work. After going through the changes with process owners, the team leader revises and refines the equipment layout diagram. On day 5, the team completes final refinements and drafts standard work operating procedures for the process. Changes needing more time to take effect are put into a 30-day action plan. The team does final tests to compare results to the data gathered on day 2. The project Black Belt estimates a 43% reduction in rejects by month end. The team's final step is to share success with everyone by documenting the journey in a Kaizen storyboard. A Kaizen Blitz is a low-cost, hands-on process in which all team members are given equal responsibility and consideration. It can produce solid performance improvements in narrowly targeted areas and is an excellent tool to invigorate a process improvement team. But it isn't perfect in every situation. In a blitz, there's no time for prolonged analyses or second thoughts. Although small problems can be eliminated quickly, there's also the possibility that the big picture may be ignored and overall system functionality may suffer. A total quality improvement methodology requires time to become part of a business paradigm, and that can take months or years to fully implement. Kaizen is a continuous improvement project that stresses eliminating wastes and streamlining processes. The 6 stages of Kaizen are: state the problem and solution, gather and train your team, collect data, analyze the data, make improvement recommendations, and implement and monitor changes. Sometimes a highly focused short-term Kaizen project, called a Kaizen Blitz, will be conducted to make specific improvements to sharply targeted areas. A Kaizen Blitz typically lasts only 3 to 5 days. Systems are made up of many different steps. You could liken these steps to links in a chain where each link is connected to all the other links in a continuous flow. But what happens if you apply pressure to the chain? Eventually, it will break, and it will do so at only one place: the weakest link. Like a chain, a system is a set of processes and sub-processes in an interdependent relationship. The weakest link in a system is known as a constraint. The strength and performance of the system will depend upon the strength and performance of the constraining process. It's vital to identify and fix the constraint if you want to strengthen the system. You can access the content of The Theory of Constraints after the video to refresh your knowledge. The Theory of Constraints, or TOC, focuses on improving systems by fixing the weakest link, the system constraint. As soon as the constraint is fixed, it is no longer the weakest link. So the next weakest link becomes the constraining factor in the system, and the process starts again. You may be familiar with the TOC from your Greenbelt training. Constraints may be physical or procedural. Physical constraints include broken or obsolete equipment and are easy to identify because they usually have some visible element. Procedural constraints include changes in behavior or mindset and are often a lot more difficult to identify because they're entrenched in an organization's business culture. However, it's these procedural fixes that usually result in a larger degree of system improvement. The TOC can be illustrated by thinking about a group of hikers where one of the participants has different physical abilities and knowledge of the route. The path of the hike is equivalent to the journey of a product through a system, with the hikers representing workers or cells and the distance between the hikers representing investment in time. As the journey begins, the hikers seem evenly matched, but soon, the faster and more experienced hikers outpace the weaker ones, leaving them behind. Applying the TOC, the solution is to improve the pace of the constraining hikers. In Six Sigma, this is done by using Kaizen and other improvement methods. However, if the pace of the slowest hiker cannot be increased, then one must accept it and work to adjust the pace of overall system to avoid waiting and streamline the flow. One of the ways to do this is to put the slowest hiker, the constraint, at the head of the group and have the others match their pace to his. As the constraint grows more familiar with the route, he will pick up pace, and the new slowest hiker will take his place. This way, the group arrives at its destination as a whole and in the fastest time possible. The location of a constraint within a system is known as a bottleneck. In a bottleneck, the demand for service exceeds the capacity to serve. This means the throughput of the system is dependent on the throughput of the bottleneck. There are three critical performance measures of any production system. The first is throughput, or production rate, which is the rate at which a system generates output. Next is flow time, or lead time, which is the time required for a defined amount of work to be completed. And finally, the inventory is the money value of all assets, material, semi-finished and finished products, and parts locked within the system, waiting to be processed for customers. Little's law measures the impact of inventory on a system. It states the average amount of inventory in any system is equal to the average throughput multiplied by the average flow time. Put simply, it can tell you the amount of finished goods inventory produced by the system in a specified flow time and at a given rate, or how long it will take to produce the desired number of products at a given rate. Let's consider a workstation that's able to produce 100 parts per hour, with the average flow time being 20 hours. This means there will be an average of 2,000 parts, or 20 hours worth, of inventory in the system. But in a manufacturing situation, the impact of inventory has a great effect. Because of the linear relationship, increased inventory levels would result in increased flow time for the same throughput. But what happens if a bottleneck has slowed down the process? You can calculate the flow time from the inventory. If your inventory is now 3,000 parts with a throughput of 100 parts per hour, this means your flow time has increased to 30 hours. There are a number of techniques you can use to alleviate bottlenecks. The first is leaning, which is an umbrella term for the wide array of tools in the lean methodology. An example of leaning to alleviate a bottleneck would be to apply Kanban pull. Next, you can try standardizing, which means documenting work and doing it the same way every time. Standard work alleviates bottlenecks by saving time and preventing mistakes from being repeated. You can try foolproofing, also known as pokayoke. It alleviates bottlenecks by preventing errors. For example, a factory machine might be designed to input material only one way so that it can't jam. Flexible resourcing is another option. This involves the provision of skilled people in the right place at the right time for the required duration. It prevents bottlenecks by providing human resources with options for completing work in a process. For example, work could be assigned to full-time employees, but contractors could handle overflow on an as-needed basis. And a final technique is job leveling, an analysis of each person's role in the process to determine where improvement could be made. It prevents bottlenecks by making sure physical and human resources are evenly matched for maximum efficiency and effectiveness. An example of job leveling might be job sharing between two people with different skills. Overall Equipment Effectiveness, or OEE, is a benchmarking tool or metric that helps you gauge the various subcomponents of the manufacturing process and is used to measure actual improvements from Six Sigma initiatives. OEE indicates how well machines, production lines, and processes are performing. The primary goal of OEE is to assess how effective an organization's value-add equipment is in both manufacturing and non-manufacturing industries. It measures how effectively an organization converts its equipment usage time into output and highlights the areas with the most critical production losses. However, OEE has its limitations. By focusing on optimizing equipment use, factors such as material and labor are often overlooked. Companies can easily fall into the trap of placing one worker to one machine. A best practice for Six Sigma companies is to maintain a balance of materials, equipment, and labor. OEE can be used to pinpoint or highlight the areas with the most critical production losses. There are 3 losses OEE measurements take into consideration. The first is downtime. This indicates a loss of availability and refers to the time when a machine is expected to run but is inactive. Downtime includes setup time, machine breakdowns, and startups, and is a common culprit of availability losses. Downtime is anything that results in less than 100% availability and can also include line restraints and machine adjustments. The second is speed loss, which indicates a loss of performance and occurs when a machine is running at a slower speed than normal. Anything less than 100% indicates speed loss. Speed losses may result from idling and minor stoppages, or an operation that requires running at a reduced speed. And the third loss is defects, which is a loss of quality and ensues when a machine produces products that fail to meet the expected organizational and customer standards. Defect losses may be categorized as scrap and reworks or as startup losses. When applying OEE to a non-manufacturing environment, the focus shifts from equipment to value-add activities. Consider an insurance company that has asked you to assess the overall value-adding, or VA, effectiveness at their new call center. You would need to appraise the availability rate, performance rate, and service quality for a branch they recently opened. You could measure the VA availability by looking at the number of employees available to contact potential clients or take incoming calls. To measure VA performance, you could look at the actual service delivery output versus the target service delivery output. Finally, you would need to assess the quality of the service provided. In order to measure this, you would measure the actual service quality versus the expected service output. For example, were the employees polite, concise, and helpful? Did they follow the necessary steps and cover all relevant information? If the call center has a customer rating system, you can measure the target rating an employee should receive versus the rating given by clients. There are several benefits to OEE. For example, providing line managers with insight on facts and data regarding machinery, as well as gaining a better understanding of machinery. It also helps in making employees more aware of losses and fostering a sense of responsibility for equipment and machinery. Other benefits include giving feedback on how machinery can be improved and letting upper management know about the status of machinery. Calculating OEE depends on 3 variables: availability rate, performance rate, and quality rate. Availability is the time a machine is actually available for production. Performance is the actual output compared to the theoretically possible output. Quality is the amount of usable product in the output. Each of the 3 variables can be calculated using a formula. There are several formula variations. Organizations can adjust the factors according to their needs, combining multiple manufacturing issues and data points to provide tangible information about processes. The availability rate formula compares the operating time and the planned production time. The operating time doesn't include downtime. Planned production time doesn't include breaks. All breakdowns reduce the availability ratio, whether they are for preventive maintenance or a lack of operators. The availability rate is calculated by dividing operating time by planned production time. The availability rate can be improved through preventive maintenance to reduce or eliminate all kinds of stoppages. The quality rate formula takes into account the amount of the production that has to be discharged or scrapped. Factors that influence this ratio are the number of good units compared to the total units produced. Situations such as tool wear and production errors can certainly play a part in producing unacceptable units that require rework or scrapping. The quality rate is calculated by dividing good units by total units. Eliminating defects in the manufacturing process, especially during the production of a new product, improves the quality rate. The performance rate formula factors in the produced pieces, the operating time, and the target productivity rate. Another way to think about this is that the actual rate of production is multiplied by the standard or theoretical rate. A loss of production can occur with underutilization of machinery when the equipment is not run with full speed. The performance rate is calculated by first multiplying operating time by the target productivity rate. Then pieces produced is divided by the first value. Influences on the performance rate include speed reductions and minor stoppages. The OEE value is the product of the three factors of availability, performance, and quality. So the OEE tool can help you to methodically improve processes using basic, easy-to-handle measurements. It's a practical simplification to visualizing performance. The magic of OEE isn't that you have one number, it's that you have three numbers, all of which are useful individually in ever-changing production situations. If there were no losses from any factor, the OEE would be 100%, which is the ideal. However, in real life, losses occur in all areas. Consider a bolt manufacturer that has asked you to determine the availability rate, performance rate, and quality rate for its machines. Let's start by calculating availability. As you know, availability looks at the time available to run the machine versus the time the machine actually ran. If 7 hours were available to run a machine and it ran for 6 hours, you would calculate the availability rate by dividing the actual run time by the time available to run the machine. The availability rate for the machine would be 86%. Performance compares the actual output or pieces produced with what the equipment should be producing, determined as a product of operating time and the target rate. If, on a given day, a machine should produce at the target rate of 10 specialized bolts per hour, but only produced 85 in 10 hours, you would calculate the performance rate by dividing the actual amount produced by the amount it should produce. The performance rate is 85%. The OEE value also takes quality into account. If 80 out of 85 bolts are acceptable and 5 are rejects, the quality score is 94%. Once you have the three percentages, you simply multiply them together to get the OEE. In this example, the OEE is 69%. Alternative improvement tools include the theory of constraints and OEE. The theory of constraints states that a system is only as strong as its weakest link. When this weakness or constraint is fixed, the system becomes stronger. OEE indicates how well machines, production lines, and processes are performing in terms of availability, performance, and quality. So you've used some lean tools and techniques to generate potential solutions, and the next step is to implement them. But are the proposed solutions going to work? Can proposed solutions be further improved to optimize their chances of success? How will you demonstrate their value to stakeholders to gain important feedback before full-scale implementation? The implementation planning part of the improve phase is dedicated to answering these questions and making sure the solutions you implement will work. Six Sigma teams use what they've learned in the previous phases, define, measure, and analyze to plan winning solutions. Applying improvement tools and techniques, such as lean methods, helps ensure that the proposed solutions provide maximum improvement. Proving that proposed solutions are worth implementing, that they deliver the desired improvements, is an important requirement. As a Six Sigma Black Belt, you should evaluate proposed solutions on a small scale first before their full-scale implementation. You can develop implementation plans for proposed solutions, including pilot tests, simulations, solution evaluation, and demonstrations. Let's review each technique to learn how it can be used to evaluate proposed solutions. During a pilot test, the process is carried out as it would be once implemented. This is a real-world test done for a limited time on a limited scale. A simulation uses mathematical or computer-based models to test solutions. Simulations are built to mimic, as closely as possible, the improved process being implemented. Solution evaluation uses tasks that analyze the proposed solutions, the value they can deliver, and limitations, if any, and makes recommendations to increase their value. A demonstration involves executing the proposed process to show how it would change and improve the process. Demonstrations usually rely on one or more people showing how the new process will work. You may want to use pilot testing when you can implement the new process on a limited scale. This will give you real-world information on how well it works. Pilot tests always involve people and may involve design of experiments and hypothesis tests. As you prepare for and conduct a pilot test, certain best practices will help you get the most benefit out of the technique. When conducting a pilot test, there are 4 best practices that you should follow. It's important to prepare for the pilot test. You should always remain objective and provide help when appropriate. And it's also important to take good notes. The first best practice is to prepare for the pilot test. It also includes several best practices that should be followed. Let's review how each best practice will help you prepare for your pilot test. You may have to provide the necessary training if the participants are not familiar with elements of the proposed process. Otherwise, the pilot test will reflect that participants didn't know how to perform the process, not necessarily whether the process delivers the intended improvement. You'll need to set up the test by implementing the proposed process on a limited and controlled scale. Make sure everything needed to conduct the test is set up, such as any equipment, tools, or computers needed to participate in the test. And you'll need to prepare to administer the test by developing or gathering all the things you will need to administer the test. This may include a way to record the results and participant consent forms. Once you've prepared for the pilot test, you can conduct it. You should now follow the other best practices when conducting the pilot test, namely to remain objective, provide help when appropriate, and take good notes. Remaining objective is crucial to your efforts. Otherwise, your results can be unnecessarily skewed. Your job is to listen and watch, and to record what you are seeing and hearing. Remember to keep your comments neutral. Avoid making positive or negative remarks that may influence the participants' opinions or experiences. Part of remaining objective is showing respect for participants and their experience with the new process. Let's cover the 2 remaining best practices now. Providing help when appropriate means providing help only if it will help you learn more about the proposed process. Solving a participant's problems is counterproductive. It limits what you can learn about additional improvements that can or should be made. Instead, watch and listen carefully to collect valuable feedback. Encouraging participants to think out loud can also help you learn what works and what doesn't, or where the participant sees a better way to do things. Taking good notes means taking useful notes. Typically, the more specific you can be, the better. Where possible, record what participants did and said, preferably in their own words. Let's consider this example. Luke, a black belt, works at a call center and is working on a project to improve the process for escalating issues to a supervisor. Currently, the customer service representatives, or CSRs, must wait in queue to talk to a supervisor. This process prevents CSRs from moving on to a new call and provides no way to prioritize the issues. Luke is proposing a new process that will use a standardized E-form to describe the issue, assign priority, and escalate it to a supervisor. The Six Sigma team wants to test the new process before implementing it and replacing the current process. The CSRs participating in the pilot test were selected to represent a range of skill and experience levels and have been trained on the new process. Luke is doing a side-by-side assessment with Betty, one of the participating CSRs, as she tries to escalate an issue using the new process. Luke explains that he is there to watch and learn, and he encourages Betty to act as she would if he weren't there. He also asks her to place the customer on hold and think out loud as she follows the new process. Betty has trouble finding the E-form. Luke watches, listens, and takes detailed notes of what Betty is doing and saying. She looks where she thinks it logically should be, consults her online help directory, but can't find it anywhere. Just as she is about to call her support team for help, Luke interrupts and tells her where to find the E-form. In this situation, Luke applied all the best practices of conducting a pilot test. He remained objective, helped when necessary, and took good notes. Luke allowed Betty to attempt to find the E-form and only provided help when it was clear she was going to get the answer from her support team anyway. Luke knew that at this point, telling Betty where the form was wouldn't affect what she would do if he wasn't there. Luke was careful to remain objective and took notes on what Betty did and said. Not all of your improvement projects will be best suited for pilot testing. Some projects will lend themselves more to evaluation through simulation of the process. A simulation mimics the real-world application of the solution. It's usually developed using a mathematical or computer-based model to show what would happen if the proposed changes were implemented. Simulations may be an appropriate choice where a pilot test or demonstration would be too costly, time-consuming, dangerous, or is simply not possible. For example, you could use a simulation to test how a proposed change to shipping lanes would impact erosion on nearby shorelines. The simulation could be used to mimic the changes that would occur over time based on real-world data. A simulation can provide useful information if designed properly. Let's review the first few steps to take when conducting a simulation. First, define the proposed solution. Begin by clearly defining the problem the proposed solution is meant to solve. Without a clear understanding of the problem and what is understood as improvement, you have little hope of solving the problem. The second step is to collect information and design a simulation model. For the simulation to provide useful information, it must model the real process being improved. So, for the simulation to be effective, it must be designed using accurate data that is generated and collected from the real process, product, or system. The third step is to validate the planned simulation model. Here, you ensure that the scope of the simulation will provide enough information to properly address the problem or opportunity, and that the simulation accurately reflects the real process. Let's continue reviewing the steps of the simulation. In Step 4, you select your simulation method, mathematical or computer-based modeling, and then you program the simulation model. You can use a flowchart to help you identify what the simulation must do and how it must progress. After the simulation is built, the next step is to validate the programmed simulation model. You ensure the simulation model simulates what you need it to based on what you defined in Step 1. You also ensure it matches the planned simulation. Once you've validated the simulation model, you design, conduct, and analyze simulation experiments to find the best solution. This step includes identifying the variables you want to test, testing them, and analyzing the end results. In the final step, you document and present the simulation experiment results. You also ensure that the proposed solution works as intended or does what is required. Let's consider an example now. A city's transportation department wants to improve traffic flow at a busy intersection. During rush hour, the intersection gets congested and traffic backs up surrounding streets. The team decides to use a simulation to test solutions. First, it defines the proposed solution, alleviating the congestion in the affected area. Solutions the team will simulate include changing a one-way street to two-way during peak traffic and changing the timing of nearby traffic lights. Let's follow along now as the team conducts the rest of the simulation. To improve the traffic flow, the team needs accurate information about the current traffic situation. The Six Sigma team uses car counters and video surveillance to collect and record data. Next, the team reviews the planned simulation to ensure it will provide or consider all the relevant information needed to improve the situation. The team finds that it omitted a street that should be part of the simulation, so the team collects data about this street's present traffic flow. Now that the team is satisfied the simulator reflects the current traffic flow, it programs the computer-based simulator. All the data collected during Steps 2 and 3 is entered into the simulator, which then generates a model based on this data. Before beginning the experiments, the team needs to validate the programmed simulation model to ensure that what it planned in Step 3 really does mimic the real situation. Once the simulation is validated and the team knows it will generate accurate results, the team begins designing experiments. These experiments will test all the proposed solutions. Team members conduct and analyze the experiments, learning valuable information that will help them to choose the best solution to the problem. The final thing the team must do is document the simulation experiment results. Once documented, the results can be used to present the proposed solution to managers and colleagues in the transportation department. After following the 7 steps for conducting a simulation, the team is confident that it has planned and chosen the best solution. Now the transportation department can implement the new traffic pattern knowing it will work. Along with pilot tests and simulations, solution evaluation and demonstration can be used to optimize proposed solutions. Solution evaluation involves analyzing proposed solutions and the value they can deliver, identifying any limitations, and making recommendations to increase their value. Demonstrating proposed solutions to stakeholders can help you gain insight into whether the solution will work and, if not, how you can improve it. Solution evaluation analyzes the value added by a potential solution or solution component. At this point in the analysis process, the solution already exists and may even be in operation. Measuring solution performance can help you identify possible limitations so that you can address them and strengthen the value of the solution. There are 3 high-level tasks you perform during a solution evaluation. The team needs to measure solution performance, then assess limitations of the solution and of the organization, and finally recommend actions that can be taken to increase the value of the solution. Let's take a closer look at each task. Measuring solution performance has 2 phases. First, you need to find the best way to assess solution performance. The assessment tool may be in the form of a proof of concept or prototype, a beta test, or an operational release. An appropriate solution must align with organizational goals and objectives. Next, you run the assessment to measure the solution performance. A best practice for measuring solution performance is to make extensive notes and collect data to support any recommendations you may have. Assessing the limitations of the solution and the organization involves identifying aspects of the solution that do not meet the organization's objective. All aspects of the solution that do not produce the expected result need to be documented and addressed to ensure that the solution has minimal limitations. In the traffic flow example mentioned earlier, limitations would be any aspect of the solution that does not improve traffic flow or that causes new dangers to commuters. You will make recommendations based on the evaluation that will improve the solution and increase the value of it. Reconsider the example of the City Transportation Department and their attempts to improve traffic flow. In this example, the team conducts a solution evaluation by implementing the approved solution at one or more of the busy intersections. Running a pilot test or an operational release helps the team evaluate how effective the solution is at improving the flow of traffic at the selected intersections. Next, they use the findings to identify any limitations of the current solution and present recommendations to managers and colleagues in the transportation department. Demonstrations show how the proposed solution will improve the process. Typically, members of the Six Sigma team perform the demonstration, which may or may not involve a functional example. No standard method exists for conducting a demonstration. However, following some best practice steps can help you successfully conduct a demonstration. Let's now review the steps for conducting a demonstration. You need to explain how the current process or system works presently. The second step is to explain and demonstrate the current problem, or alternatively, the improvement to be made. Like providing a baseline when measuring, you must establish what the current performance is in order to know what an improvement is. In the third step, you explain and demonstrate the proposed change. This involves explaining how the process or system will be different, what must change to achieve improvement. Ensuring that all stakeholders understand the proposed change is vital. In the last step, you explain how implementing the change will improve the process or system. This is your evidence that the proposed change will provide the desired improvement. Remember, feedback from the stakeholders may provide useful insight into how the proposed solution is either inappropriate or could be further improved. During a demonstration, you can use a variety of techniques to explain solutions. For instance, when demonstrating a new machine, you may use reports with graphs to convey factual data and a 3D model to show its functioning. For a new manufacturing process, you could perform a walkthrough, explaining the proposed changes as you go. A demonstration may include a simulation or could involve executing the improved process. The technique you choose will depend on your industry, purpose, and what will be the most effective. Let's review Bill's situation. Bill, a black belt, works for a tractor-trailer manufacturer. A new regulation has been passed that lowers acceptable exhaust system emission levels. As a result, Bill and his team need to reduce the emission levels of their tractor-trailers to comply with the new regulation. The team has just developed a new catalytic converter, making changes in the current manufacturing process that it believes, once implemented, will allow the company to meet the new emission targets. Bill and his team decide that the best way to evaluate the new process is through demonstration of the new catalytic converter made using this process. Follow along to learn how Bill demonstrates the new process to a group of stakeholders, including the workers on the production line and the production managers. First, Bill explains that the catalytic converter produced using the current process results in tractor-trailers emitting 40% more emissions than allowed by new government regulation. Having explained the need for change and improvement, Bill tells the group that a change to the process used to manufacture the catalytic converter will help. To demonstrate the current problem, Bill runs an emissions test on a truck with a catalytic converter produced using the current manufacturing process. He then shows the group the results, which reflect the fact that currently the truck exceeds acceptable emission levels by 40%. Next, Bill has a worker replace the old converter with the new one. As this is done, Bill explains how the catalytic converter produced using the new process helps reduce emissions. After explaining and demonstrating the change to the manufacturing process, Bill goes over the outcome. A tractor-trailer equipped with a catalytic converter manufactured using the new process is subjected to an emissions test. Having programmed the results of the first tractor-trailer in as a baseline measurement, the new results clearly show a reduction of 40% in exhaust system emissions. Bill was able to explain the problem, the new process, and the improvement using a demonstration. Validation of improvements can also be demonstrated using analytical techniques, such as measurement system reanalysis, capability analysis, and hypothesis tests. You can access the content validating solutions after the video if you wish to review these techniques. You can test your solutions using pilot tests, simulations, and demonstrations to make sure they will achieve the desired process improvements. When deciding which technique to use, remember that pilot tests involve people and a real-world application of the new process. Simulations mimic the real-world process, and demonstrations rely on various techniques to explain and show how the new process will work and achieve improvement. Once you've selected a solution, it's important to evaluate your proposed solution. The 3 high-level tasks of a solution evaluation are to measure the solution's performance, assess its limitations, and recommend actions to increase its value.